Lemmas 4-11, propositions XL-XLII, comets. Lemma 4. That the comets are higher than the moon, and in the regions of the planets. As the comets were placed by astronomers above the moon, because they were found to have no diurnal parallax, so their annual parallax is a convincing proof of their descending into the regions of the planets. For all the comets which move in a direct course according to the order of the signs, about the end of their appearance become more than ordinarily slow or retrograde, if the earth is between them and the sun. And more than ordinarily swift, if the earth is approaching to a heliocentric opposition with them. Whereas, on the other hand, those which move against the order of the signs, towards the end of their appearance appear swifter than they ought to be, if the earth is between them and the sun. And slower, and perhaps retrograde, if the earth is in the other side of its orbit. And these appearances proceed chiefly from the diverse situations which the earth acquires in the course of its motion, after the same manner as it happens to the planets, which appear sometimes retrograde, sometimes more slowly, and sometimes more swiftly, progressive, according as the motion of the earth falls in with that of the planet, or is directed the contrary way. If the earth move the same way with the comet, but, by an angular motion about the sun, so much swifter that right lines drawn from the earth to the comet converge towards the parts beyond the comet seen from the earth, because of its slower motion, will appear retrograde. And even if the earth is slower than the comet, the motion of the earth being subducted, the motion of the comet will at least appear retarded. But if the earth tends the contrary way to that of the comet, the motion of the comet will from thence appear accelerated. And from this apparent acceleration, or retardation, or regressive motion, the distance of the comet may be inferred in this manner. Let Aries QA, Aries QB, Aries QC, be three observed longitudes of the comet about the time of its first appearing, and Aries QF its last observed longitude before its disappearing. Draw the right line ABC, whose parts AB, BC, intercepted between the right lines QA and QB, QB and QC, may be one to the other as the two times between the three first observations. Produce AC to G, so as AG may be to AB as the time between the first and last observation to the time between the first and second, and join QG. Now if the comet did move uniformly in a right line, and the earth either stood still, or was likewise carried forwards in a right line by an uniform motion, the angle Aries QG would be the longitude of the comet at the time of the last observation. The angle, therefore, FQG, which is the difference of the longitude, proceeds from the inequality of the motions of the comet and the earth. And this angle, if the earth and comet move contrary ways, is added to the angle Aries QG, and accelerates the apparent motion of the comet. But if the comet move the same way with the earth, it is subtracted, and either retards the motion of the comet, or perhaps renders it retrograde, as we have but now explained. This angle, therefore, proceeding chiefly from the motion of the earth, is justly to be esteemed the parallax of the comet. Neglecting, to wit, some little increment or decrement that may arise from the unequal motion of the comet in its orbit, and from this parallax we thus deduce the distance of the comet. Let S represent the sun, act the orbis magnus, of the earth's place in the first observation, C the place of the earth in the third observation, T the place of the earth in the last observation. And T Aries a right line drawn to the beginning of Aries. Set off the angle Aries TV equal to the angle Aries QF, that is, equal to the longitude of the comet at the time when the earth is in T, join AC, and produce it to G, so as AG may be to AC as AG to AC. And G will be the place at which the earth would have arrived in the time of the last observation, if it had continued to move uniformly in the right line AC. Wherefore, if we draw G Aries parallel to T Aries, and make the angle Aries GV equal to the angle Aries QG, this angle Aries GV will be equal to the longitude of the comet seen from the place G. And the angle TVG will be the parallax which arises from the earth's being transferred from the place G into the place T. And therefore V will be the place of the comet in the plane of the ecliptic. And this place V is commonly lower than the orb of Jupiter. The same thing may be deduced from the incurvation of the way of the comets. For these bodies move almost in great circles, while their velocity is great. But about the end of their course, when that part of their apparent motion which arises from the parallax bears a greater proportion to their whole apparent motion, they commonly deviate from those circles, and when the earth goes to one side, they deviate to the other. And this deflection, because of its corresponding with the motion of the earth, must arise chiefly from the parallax, and the quantity thereof is so considerable, as, by my computation, to place the disappearing comets a good deal lower than Jupiter. Whence it follows that when they approach nearer to us in their perigees and perihelions they often descend below the orbs of Mars and the inferior planets. The near approach of the comets is farther confirmed from the light of their heads. For the light of a celestial body, illuminated by the sun, and receding to remote parts, is diminished in the quadruplicate proportion of the distance. To wit, in one duplicate proportion, on account of the increase of the distance from the sun, and in another duplicate proportion, on account of the decrease of the apparent diameter. Wherefore if both the quantity of light and the apparent diameter of a comet are given, its distance will be also given. By taking the distance of the comet to the distance of a planet in the direct proportion of their diameters and the reciprocal subduplicate proportion of their lights. Thus, in the comet of the year 1682, Mr. Flamsteed observed with a telescope of 16 feet, and measured with a micrometer, the least diameter of its head, 2 feet 0 inches. But the nucleus or star in the middle of the head scarcely amounted to the 10th part of this measure, and therefore its diameter was only 11 inch or 12. But in the light and splendor of its head it surpassed that of the comet in the year 1680, and might be compared with the stars of the first or second magnitude. Let us suppose that Saturn with its ring was about 4 times more lucid. And because the light of the ring was almost equal to the light of the globe within, and the apparent diameter of the globe is about 21 inch. And therefore the united light of both globe and ring would be equal to the light of a globe whose diameter is 30 inch, it follows that the distance of the comet was to the distance of Saturn as 1 to inversely, and 12 to 30 directly. That is, as 24 to 30, or 4 to 5. Again, the comet in the month of April 1665, as Hevelius informs us, excelled almost all the fixed stars in splendor, and even Saturn itself, as being of a much more vivid color. For this comet was more lucid than that other which had appeared about the end of the preceding year, and had been compared to the stars of the first magnitude. The diameter of its head was about 6 foot. But the nucleus, compared with the planets by means of a telescope, was plainly less than Jupiter, and sometimes judged less, sometimes judged equal, to the globe of Saturn within the ring. Since, then, the diameters of the heads of the comets seldom exceed 8 foot or 12, and the diameter of the nucleus or central star is but about 1/10 or perhaps 15th part of the diameter of the head. It appears that these stars are generally of about the same apparent magnitude with the planets. But in regard that their light may be often compared with the light of Saturn, yea, and sometimes exceeds it, it is evident that all comets in their perihelions must either be placed below or not far above Saturn. And they are much mistaken who remove them almost as far as the fixed stars, for if it was so, the comets could receive no more light from our sun than our planets do from the fixed stars. So far we have gone, without considering the obscuration which comets suffer from that plenty of thick smoke which encompasseth their heads, and through which the heads always shew dull, as through a cloud. For by how much the more a body is obscured by this smoke, by so much the more near it must be allowed to come to the sun, that it may vie with the planets in the quantity of light which it reflects. Whence it is probable that the comets descend far below the orb of Saturn, as we proved before from their parallax. But, above all, the thing is evinced from their tails, which must be owing either to the sun's light reflected by a smoke arising from them, and dispersing itself through the ether, or to the light of their own heads. In the former case, we must shorten the distance of the comets, lest we be obliged to allow that the smoke arising from their heads is propagated through such a vast extent of space, and with such a velocity and expansion as will seem altogether incredible. In the latter case, the whole light of both head and tail is to be ascribed to the central nucleus. But, then, if we suppose all this light to be united and condensed within the disk of the nucleus, certainly the nucleus will by far exceed Jupiter itself in splendor, especially when it emits a very large and lucid tail. If, therefore, under a less apparent diameter, it reflects more light, it must be much more illuminated by the sun, and therefore much nearer to it, and the same argument will bring down the heads of comets sometimes within the orb of Venus, viz. When, being hid under the sun's rays, they emit such huge and splendid tails, like beams of fire, as sometimes they do. For if all that light was supposed to be gathered together into one star, it would sometimes exceed not one Venus only, but a great many such united into one. Lastly, the same thing is inferred from the light of the heads, which increases in the recess of the comets from the earth towards the sun, and decreases in their return from the sun towards the earth. For so the comet of the year 1665, by the observations of Hevelius, from the time that it was first seen, was always losing of its apparent motion, and therefore had already passed its perigee. But yet the splendor of its head was daily increasing, till, being hid under the sun's rays, the comet ceased to appear. The comet of the year 1683, by the observations of the same Hevelius, about the end of July, when it first appeared, moved at a very slow rate, advancing only about 40 or 45 minutes in its orb in a day's time. But from that time its diurnal motion was continually upon the increase, till September 4, when it arose to about 5 degrees, and therefore, in all this interval of time, the comet was approaching to the earth. Which is likewise proved from the diameter of its head, measured with a micrometer. For, August 6, Hevelius found it only 6 feet 5 inches, including the coma, which, September 2 he observed to be 9 feet 7 inches, and therefore its head appeared far less about the beginning than towards the end of the motion. Though about the beginning, because nearer to the sun, it appeared far more lucid than towards the end, as the same Hevelius declares. Wherefore in all this interval of time, on account of its recess from the sun, it decreased in splendor, notwithstanding its access towards the earth. The comet of the year 1618, about the middle of December, and that of the year 1680, about the end of the same month, did both move with their greatest velocity, and were therefore then in their perigees. But the greatest splendor of their heads was seen 2 weeks before, when they had just got clear of the sun's rays, and the greatest splendor of their tails a little more early, when yet nearer to the sun. The head of the former comet, according to the observations of Cysatus, December 1, appeared greater than the stars of the first magnitude. And, December 16, then in the perigee, it was but little diminished in magnitude, but in the splendor and brightness of its light a great deal. January 7, Kepler, being uncertain about the head, left off observing. December 12, the head of the latter comet was seen and observed by Mr. Flamsteed, when but 9 degrees distant from the sun, which is scarcely to be done in a star of the third magnitude. December 15 and 17, it appeared as a star of the third magnitude, its luster being diminished by the brightness of the clouds near the setting sun. December 26, when it moved with the greatest velocity, being almost in its perigee, it was less than the mouth of Pegasus, a star of the third magnitude. January 3, it appeared as a star of the fourth. January 9, as one of the fifth. January 13, it was hid by the splendor of the moon, then in her increase. January 25, it was scarcely equal to the stars of the seventh magnitude. If we compare equal intervals of time on one side and on the other from the perigee, we shall find that the head of the comet, which at both intervals of time was far, but yet equally, removed from the earth, and should have therefore shone with equal splendor, appeared brightest on the side of the perigee towards the sun, and disappeared on the other. Therefore, from the great difference of light in the one situation and in the other, we conclude the great vicinity of the sun and comet in the former. For the light of comets uses to be regular, and to appear greatest when the heads move fastest, and are therefore in their perigees, excepting in so far as it is increased by their nearness to the sun. Core 1. Therefore the comets shine by the sun's light, which they reflect. Core 2. From what has been said, we may likewise understand why comets are so frequently seen in that hemisphere in which the sun is, and so seldom in the other. If they were visible in the regions far above Saturn, they would appear more frequently in the parts opposite to the Sun. For such as were in those parts would be nearer to the Earth, whereas the presence of the Sun must obscure and hide those that appear in the hemisphere in which he is. Yet, looking over the history of comets, I find that 4 or 5 times more have been seen in the hemisphere towards the Sun than in the opposite hemisphere. Besides, without doubt, not a few, which have been hid by the light of the Sun, for comets descending into our parts neither emit tails, nor are so well illuminated by the Sun, as to discover themselves to our naked eyes, until they are come nearer to us than Jupiter. But the far greater part of that spherical space, which is described about the Sun with so small an interval, lies on that side of the Earth which regards the Sun. And the comets in that greater part are commonly more strongly illuminated, as being for the most part nearer to the Sun. Core 3. Hence also it is evident that the celestial spaces are void of resistance. For though the comets are carried in oblique paths, and sometimes contrary to the course of the planets, yet they move every way with the greatest freedom, and preserve their motions for an exceeding long time, even where contrary to the course of the planets. I am out in my judgment if they are not a sort of planets revolving in orbits returning into themselves with a perpetual motion. For, as to what some writers contend, that they are no other than meteors, led into this opinion by the perpetual changes that happen to their heads, it seems to have no foundation. For the heads of comets are encompassed with huge atmospheres, and the lowermost parts of these atmospheres must be the densest, and therefore it is in the clouds only, not in the bodies of the comets themselves, that these changes are seen. Thus the Earth, if it was viewed from the planets, would, without all doubt, shine by the light of its clouds, and the solid body would scarcely appear through the surrounding clouds. Thus also the belts of Jupiter are formed in the clouds of that planet, for they change their position one to another, and the solid body of Jupiter is hardly to be seen through them. And much more must the bodies of comets be hid under their atmospheres, which are both deeper and thicker. Proposition XL. Theorem XX. That the comets move in some of the conic sections, having their foci in the center of the Sun. And by radii drawn to the Sun describe areas proportional to the times. This proposition appears from Core 1, Prop. 13, Book 1, compared with Prop. 8, 12, and 13, Book 3. Core 1. Hence if comets are revolved in orbits returning into themselves, those orbits will be ellipses, and their periodic times be to the periodic times of the planets in the sesquiplicate proportion of their principal axes. And therefore the comets, which for the most part of their course are higher than the planets, and upon that account describe orbits with greater axes, will require a longer time to finish their revolutions. Thus if the axis of a comet's orbit was 4 times greater than the axis of the orbit of Saturn, the time of the revolution of the comet would be to the time of the revolution of Saturn, that is, to 30 years, as 4, or 8, to 1. And would therefore be 240 years. Core 2. But their orbits will be so near to parabolas, that parabolas may be used for them without sensible error. Core 3. And, therefore, by Core 7, Prop. 16, Book 1, the velocity of every comet will always be to the velocity of any planet, supposed to be revolved at the same distance in a circle about the Sun. Nearly in the subduplicate proportion of double the distance of the planet from the center of the Sun to the distance of the comet from the Sun's center, very nearly. Let us suppose the radius of the orbis manus, or the greatest semi-diameter of the ellipsis which the Earth describes, to consist of 100 million parts. And then the Earth by its mean diurnal motion will describe 172,0212 of those parts, and 716,751 by its horary motion. And therefore the comet, at the same mean distance of the Earth from the Sun, with a velocity which is to the velocity of the Earth as to 1, would by its diurnal motion describe 243,2747 parts, and 1013641 parts by its horary motion. But at greater or less distances both the diurnal and horary motion will be to this diurnal and horary motion in the reciprocal subduplicate proportion of the distances, and is therefore given. Core 4. Wherefore if the latus rectum of the parabola is quadruple of the radius of the orbis magnus, and the square of that radius is supposed to consist of 100 million parts, the area which the comet will daily describe by a radius drawn to the Sun will be 1216373 parts, and the horary area will be 5068214 parts. But, if the latus rectum is greater or less in any proportion, the diurnal and horary area will be less or greater in the subduplicate of the same proportion reciprocally. Lemma v. To find a curved line of the parabolic kind which shall pass through any given number of points. Let those points be A, B, C, D, E, F, and K. And from the same to any right line HN, given in position, let fall as many perpendiculars AH, BI, CK, DL, EM, FN, and K. B. 2B. 3B. 4B. 5B. C. 2C. 3C. 4C. D. 2D. 3D. E. 2E. F. Case 1. If HI, IK, KL, and K. The intervals of the points H, I, K, L, M, N, and K, are equal, take B, 2B, 3B, 4B, 5B, and K, the first differences of the perpendiculars AH, BI, CK, and K, their second differences C, 2C, 3C, 4C, and K, their third, D, 2D, 3D, and K. That is to say, so as AH, B may be equals B, BI, CK equals 2B, CK, DL equals 3B, DL plus EM equals 4B, EM plus FN equals 5B, and K, then B, 2B equals C, and K, and so on to the last difference, which is here F. Then, erecting any perpendicular RS, which may be considered as an ordinate of the curve required, in order to find the length of this ordinate, suppose the intervals HI, IK, KL, LM, and K to be units, and let AH equals A, HS equals P, 1/2 P into, IS equals Q, 1/3 Q into plus SK equals R, 1/4 R into plus SL equals S, 1/5S into plus SM equals T, proceeding, to wit, to me, the last perpendicular but one, and prefixing negative signs before the terms HS, IS, and K, which lie from S towards A, and affirmative signs before the terms SK, SL, and K, which lie on the other side of the point S, and, observing well the signs, RS will be equals A plus BP plus CQ plus DR plus ES plus FT plus and K. Case 2. But if HI, IK, and K, the intervals of the points H, I, K, L, and K, are unequal, take B, 2B, 3B, 4B, 5B, and K, the first differences of the perpendiculars AH, BI, CK, and K, divided by the intervals between those perpendiculars, C, 2C, 3C, 4C, and K. Their second differences, divided by the intervals between every 2D, 2D, 3D, and K, their third differences, divided by the intervals between every 3E, 2E, and K, their fourth differences, divided by the intervals between every 4. And so forth, that is, in such manner, that may be, and K, then, and K, then, and K. And those differences being found, let AH be equals A, HS equals P, P into, IS equals Q, Q into plus SK equals R, R into plus SL equals S, S into plus SM equals T. Proceeding, to wit, to me, the last perpendicular but one, and the ordinate RS will be equals A plus BP plus CQ plus DR plus ES plus FT plus and K. Core. Hence the areas of all curves may be nearly found. For if some number of points of the curve to be squared are found, and a parabola be supposed to be drawn through those points, the area of this parabola will be nearly the same with the area of the curvilinear figure proposed to be squared, but the parabola can be always squared geometrically by methods vulgarly known. Lemma 6. Certain observed places of a comet being given, to find the place of the same to any intermediate given time. Let hi, ik, kl, lm, in the preceding fig, represent the times between the observations. Ha, ib, kc, ld, mi, 5 observed longitudes of the comet, and hs the given time between the first observation and the longitude required. Then if a regular curve ABCDE is supposed to be drawn through the points A, B, C, D, E, and the ordinate Rs is found out by the preceding lemma, Rs will be the longitude required. After the same method, from 5 observed latitudes, we may find the latitude to a given time. If the differences of the observed longitudes are small, suppose of 4 or 5 degrees, 3 or 4 observations will be sufficient to find a new longitude and latitude. But if the differences are greater, as of 10 or 20 degrees, 5 observations ought to be used. Lemma 7. Through a given point P to draw a right line BC, whose parts PB, PC, cut off by 2 right lines AB, AC, given in position, may be one to the other in a given proportion. From the given point P suppose any right line PD to be drawn to either of the right lines given, as AB, and produce the same towards AC, the other given right line, as far as E, so as PE may be to PD in the given proportion. Let EC be parallel to AD. Draw CPB, and PC will be to PB as PE to PD. QEF. Lemma 8. Let ABC be a parabola, having its focus in S. By the chord AC bisected in I cut off the segment ABCI, whose diameter is I mu and vertex mu. In I mu produce take mu O equal to 1/2 of I mu. Join OS, and produce it to psi, so as S psi may be equal to 2 so. Now, supposing a comet to revolve in the arc CBA, draw xi b, cutting AC in E. I say, the point E will cut off from the chord AC the segment AE, nearly proportional to the time. For if we join EO, cutting the parabolic arc ABC in Y, and draw μx touching the same arc in the vertex mu, and meeting EO in X, the curvilinear area XA will be to the curvilinear area ASIA as AE to AC. And, therefore, since the triangle ASE is to the triangle ASC in the same proportion, the whole area ASEXA will be to the whole area ASIA as AE to AC. But, because XIO is to SO as 3 to 1, and EO to XO in the same proportion, SX will be parallel to EB, and, therefore, joining BX, the triangle SEB will be equal to the triangle XEB. Wherefore if to the area ASEXA we add the triangle EXB, and from the sum subduct the triangle SEB, there will remain the area ASPXA, equal to the area ASEXA, and therefore in proportion to the area ASIA as AE to AC. But the area ASBIA is nearly equal to the area ASPXA, and this area ASBIA is to the area ASIA as the time of description of the arc AB to the time of description of the whole arc AC. And, therefore, AE is to AC nearly in the proportion of the times. QED. Core. When the point B falls upon the vertex mu of the parabola, AE is to AC accurately in the proportion of the times. Scholium. If we join mu xi cutting AC in delta, and in it take xi-n in proportion to mu b as 27 miles to 16 mu, and draw bn, this bn will cut the chord AC, in the proportion of the times, more accurately than before. But the point n is to be taken beyond or on this side the point psi, according as the point B is more or less distant from the principal vertex of the parabola than the point mu. Lemma 9. The right lines I mu and mu m, and the length, are equal among themselves. For 4s mu is the latus rectum of the parabola belonging to the vertex mu. Lemma x. Produce s mu to n and p, so as mu n may be 1/3 of mu I, and sp may be to sn as sn to s mu. And in the time that a comet would describe the arc ac, if it was supposed to move always forwards with the velocity which it hath in a height equal to sp, it would describe a length equal to the chord ac. For if the comet with the velocity which it hath in mu was in the said time supposed to move uniformly forward in the right line which touches the parabola in mu, The area which it would describe by a radius drawn to the points would be equal to the parabolic area asca. And therefore the space contained under the length described in the tangent and the length s mu would be to the space contained under the lengths AC and SM as the area asca to the triangle ASC, that is, as SN to SM. Wherefore AC is to the length described in the tangent as S mu to Sn. But since the velocity of the comet in the height sp, by course 6, prop. 16. Book I, is to the velocity of the same in the height s mu in the reciprocal subduplicate proportion of sp to s mu, that is, in the proportion of s mu to Sn. The length described with this velocity will be to the length in the same time described in the tangent as s mu to Sn. Wherefore since AC, and the length described with this new velocity, are in the same proportion to the length described in the tangent, they must be equal betwixt themselves. QED. Sur. Therefore a comet, with that velocity which it hath in the height s mu plus 2/3 I mu, would in the same time describe the chord AC nearly. Lemma 11. If a comet void of all motion was let fall from, the height Sn, or s mu plus 1/3 I mu, towards the sun, and was still impelled to the sun by the same force uniformly continued by which it was impelled at first, the same. In 1/2 of that time in which it might describe the arc AC in its own orbit, would in descending describe a space equal to the length I mu. For in the same time that the comet would require to describe the parabolic arc AC, it would, by the last lemma, with that velocity which it hath in the height sp, describe the chord AC, and, therefore, by course 7, prop. 16, Book 1, if it was in the same time supposed to revolve by the force of its own gravity in a circle whose semi-diameter was sp, it would describe an arc of that circle, the length of which would be to the chord of the parabolic arc AC in the subduplicate proportion of 1 to 2. Wherefore if with that weight, which in the height sp it hath towards the sun, it should fall from that height towards the sun, it would, by core 9, prop. 16, Book 1, in half the said time describe a space equal to the square of half the said chord applied to quadruple the height sp, that is, it would describe the space. But since the weight of the comet towards the sun in the height Sn is to the weight of the same towards the sun in the height sp as sp to s mu, the comet, by the weight which it hath in the height Sn, in falling from that height towards the sun, would in the same time describe the space. That is, a space equal to the length I mu or mu m. QED. Proposition XLI. Problem 21. From 3 observations given to determine the orbit of a comet moving in a parabola. This being a problem of very great difficulty, I tried many methods of resolving it, and several of these problems, the composition whereof I have given in the first book, tended to this purpose. But afterwards I contrived the following solution, which is something more simple. Select 3 observations distant one from another by intervals of time nearly equal. But let that interval of time in which the comet moves more slowly be somewhat greater than the other, so, to wit, that the difference of the times may be to the sum of the times as the sum of the times to about 600 days. Or that the point E may fall upon M nearly, and may err therefrom rather towards I than towards A. If such direct observations are not at hand, a new place of the comet must be found, by Lem. 6. Let S represent the sun. T, tau, 3 places of the earth in the orbis magnus, Ta, Tb, tau c, 3 observed longitudes of the comet, v the time between the first observation and the second, w the time between the second and the third. X the length which in the whole time v plus w. The comet might describe with that velocity which it hath in the mean distance of the earth from the sun, which length is to be found by core 3, prop. XL, Book 3. And TV a perpendicular upon the chord t tau. In the mean observed longitude Tb take at pleasure the point B, for the place of the comet in the plane of the ecliptic. And from thence, towards the sun S, draw the line B, which may be to the perpendicular TV as the content under SB and ST superscript 2 to the cube of the hypotenuse of the right-angled triangle, whose sides are SB. and the tangent of the latitude of the comet in the second observation to the radius tb. And through the point E, by Lemma 7, draw the right line AEC, whose parts AE and EC, terminating in the right lines TA and tau C, may be one to the other as the times V and W, then A and C will be nearly the places of the comet in the plane of the ecliptic in the first and third observations, if B was its place rightly assumed in the second. Upon AC, bisected in I, erect the perpendicular to. Through B draw the obscure line by parallel to AC, join the obscure line C, cutting AC in lambda, and complete the parallelogram I lambda mu. Take I sigma equal to 3 I lambda. And through the sun S draw the obscure line sigmas I equal to 3S sigma plus 3 I lambda. Then, cancelling the letters A, E, C, I, from the point B towards the point psi, draw the new obscure line B, which may be to the former B in the duplicate proportion of the distance bs to the quantity s mu plus 1/3 I lambda. And through the point E draw again the right line AEC by the same rule as before, that is, so as its parts AE and EC may be one to the other as the times V and W between the observations. Thus A and C will be the places of the comet more accurately. Upon AC, bisected in I, erect the perpendiculars AM, CN, IO, of which AM and CN may be the tangents of the latitudes in the first and third observations, to the radii TA and tau C. Join MN, cutting IO in O. Draw the rectangular parallelogram II lambda mu, as before. In IA produced take ID equal to S mu plus 2/3 I lambda. Then in MN, towards N, take MP, which may be to the above found length x in the subduplicate proportion of the mean distance of the Earth from the Sun, or of the semi-diameter of the orbis magnus, to the distance OD. If the point P fall upon the point N, B, and C, will be 3 places of the comet, through which its orbit is to be described in the plane of the ecliptic. But if the point P falls not upon the point N, in the right line AC take CG equal to NP, so as the points G and P may lie on the same side of the line NC. By the same method as the points E, A, C, G, were found from the assumed point B, from other points B and beta assumed at pleasure, find out the new points E, A, C, G, and epsilon, alpha, kappa, gamma. Then through G, G, and gamma, draw the circumference of a circle GG gamma, cutting the right line tau C in Z, and Z will be one place of the comet in the plane of the ecliptic. And in AC, AC, alpha kappa, taking AF, AF, alpha phi, equal respectively to CG, CG, kappa gamma. Through the points F, F, and phi, draw the circumference of a circle FF phi, cutting the right line at an X, and the point X will be another place of the comet in the plane of the ecliptic. And at the points X and Z, erecting the tangents of the latitudes of the comet to the radii Tx and tau Z, 2 places of the comet in its own orbit will be determined. Lastly, if, by Prop. 19. Book 1, to the focus S a parabola is described passing through those 2 places, this parabola will be the orbit of the comet. QEI. The demonstration of this construction follows from the preceding lemmas, because the right line AC is cut in E in the proportion of the times, by Lem. 7, as it ought to be, by Lem. 8, and B, by Lem. 11. Is a portion of the right line BS or BZI in the plane of the ecliptic, intercepted between the arc ABC and the chord AEC, and MP, by chord Lem. X. Is the length of the chord of that arc, which the comet should describe in its proper orbit between the first and third observation, and therefore is equal to Mn, providing B is a true place of the comet in the plane of the ecliptic. But it will be convenient to assume the points B, B, beta, not at random, but nearly true. If the angle AQT, at which the projection of the orbit in the plane of the ecliptic cuts the right line TB, is rudely known, at that angle with BT draw the obscure line AC, which may be to 4/3 t tau in the subduplicate proportion of SQ, to ST. And, drawing the right line SEB so as its part EB may be equal to the length VT, the point B will be determined, which we are to use for the first time. Then, cancelling the right line AC, and drawing a new AC according to the preceding construction, and, moreover, finding the length MP, in TB take the point B, by this rule, that, if TA and tau C intersect each other in Y, the distance YB may be to the distance YB in a proportion compounded of the proportion of MP to MN, and the subduplicate proportion of SB to SB. And by the same method you may find the third point beta, if you please to repeat the operation the third time, but if this method is followed, 2 operations generally will be sufficient. For if the distance BB happens to be very small, after the points F, F, and G, G, are found, draw the right lines FF and GG, and they will cut TA and tau C in the points required, X and Z. Example. Let the comet of the year 1680 be proposed. The following table shews the motion thereof, as observed by Flamsteed, and calculated afterwards by him from his observations, and corrected by Dr. Halley from the same observations. 1680, December 12. 21. 24. 26. 29. 30. 1681, Jan. 5. 9. 10. 13. 25. 30. February 2nd. 5. Time. Suns. Longitude. Comets. Apar. True. Longitude. Lat N. H. 4.46. 6.32 1/2. 6.12. 5.14. 7.55. 8.02. 5.51. 6.49. 5.54. 6.56. 7.44. 8.07. 6.20. 6.50. H. 4.46.0. 6.36.59. June 17, 52. 5.20. 44. August 3, 02. August 10, 26. June 1, 38. 7.00.53. June 6, 10. July 8, 55. 7.58.42. August 21, 53. 6.34.51. July 4, 41. Degree. Capricorn 1.51.23. November 6, 44. September 14, 26. September 16, 22. 19.19.43. 20.21.09. 26.22.18. Aquarius 0.29.02. January 27, 43. 4.33.20. 16.45.36. 21.49.58. 24.46.59. 27.49.51. Degree. Capricorn 6.32. 30. Aquarius May 8, 12. 18.49.23. 28.24.13. Pisces October 13, 41. 17.38.20. Aries 8.48.53. 18.44.04. 20.40.50. 25.59.48. Taurus 9.35.0. 13.19.51. 15.13.53. 16.59.06. Degree. 8.25, 0. 21.42.13. 25.235. 27.00.52. September 28, 58. November 28, 53. 26.15, 7. November 24, 56. 23.43.52. 22.17.28. 17.56.30. 16.42. 18. 16.04, 1. 15.27, 3. To these you may add some observations of mine. 1681, February 25. 27. March 1st. 2. 5. 7. 9. AP. Time. Comets. Longitude. Lat N. H. 8.30. 8.15. 11, 0. 8, 0. 11.30. 9.30. 8. 30. Degree. Taurus 26.18.35. April 27, 30. 27.52.42. December 28, 48. 29.18, 0. Gemini 0. 4, 0. 0, 43. 4. Degree. 12.46.46. 12.36.12. December 23, 40. December 19, 38. December 3, 16. 11.57, 0. 11.45. 52. These observations were made by a telescope of 7 feet, with a micrometer and threads placed in the focus of the telescope. By which instruments we determined the positions both of the fixed stars among themselves, and of the comet in respect of the fixed stars. Let A represent the star of the 4th magnitude in the left heel of Perseus, Bayer's Omicron, be the following star of the 3rd magnitude in the left foot, Bayer's Zeta, C a star of the 6th magnitude, Bayer's N, in the heel of the same foot, and D, E, F, G, H, I, K, L, M, N, O, Z, Alpha, Beta, Gamma, Delta, other smaller stars in the same foot. And let P, P, Q, R, S, T, V, X, represent the places of the comet in the observations above set down, and, reckoning the distance AB of 807/12 parts, AC was 52 and a quarter of those parts, BC, 585/6, AD, 575/12, BD, 826/11, CD, 23 2/3, AE, 294/7, CE, 57 1/2. DE, 491112, AI, 277/12, by, 521/6, CI, 367/12, D, 535/11, AK, 38 2/3, BK, 43, CK, 315/9, FK, 29, FB, 23, FC, 36 1/4, AH, 186/7, DH, 507/8, BN, 465/12, CN, 31 1/3, BL, 455/12, NL, 315/7. HO was to HI as 7 to 6, and, produced, did pass between the stars D and E, so as the distance of the star D from this right line was 1/6 CD. LM was to LN as 2 to 9, and, produced, did pass through the star H. Thus were the positions of the fixed stars determined in respect of one another. Mr. Pound has since observed a second time the positions of those fixed stars amongst themselves, and collected their longitudes and latitudes according to the following table. The fixed stars, their longitudes, latitude, north, the Fixed stars. Their longitudes. Latitude. North. A. B. C. E. F. G. H. I. K. Degree. Taurus 26.41.50. 28.40.23. 27.58.30. 26.27.17. 28.28.37. 26.56, 8. November 27th, 45. 27.25, 2. 27.42, 7. Degree. Taurus 12. 8.36. November 17th, 54. 12.40.25. 12.52, 7. 11.52. 22. April 14th, 58. 12.2, 1. 11.53.11. 11.53.26. L. M. N. Z. Alpha. Beta. Gamma. Delta. Degree. Taurus 29.33.34. 29.18.54. 28.48.29. 29.44.48. 29.52, 3. Gemini 0. 8.23. 0.40.10. 1, 3.20. Degree. 12, 7.48. 12, 7.20. 12.31, 9. 11.57.13. 11.55.48. 11.48.53. 11.55.18. 11.30. 42. The positions of the comet to these fixed stars were observed to be as follow. Friday, February 25th, OS at 8½ h. p.m. The distance of the comet in P from the star E was less than 3/13 AE, and greater than 1/5 AE, and therefore nearly equal to 3/14 AE, and the angle ape was a little obtuse, but almost right. For from A, letting fall a perpendicular on PE. The distance of the comet from that perpendicular was 1/5 PE. The same night, at 9½ h, the distance of the comet in P from the star E was greater than AE, and less than AE, and therefore nearly equal to of AE, or 8/39 AE. But the distance of the comet from the perpendicular let fall from the star A upon the right line PE was 4/5 PE. Sunday, February 27th, 8¼ h. p.m. The distance of the comet in Q from the star O was equal to the distance of the stars O and H. And the right line QO produced passed between the stars K and B. I could not, by reason of intervening clouds, determine the position of the star to greater accuracy. Tuesday, March 1st, 11 h. p.m. The comet in R lay exactly in a line between the stars K and C, so as the part CR of the right line CRK was a little greater than 1/3 CK, and a little less than 1/3 CK plus 1/8 CR, and therefore equals 1/3 CK plus 1/16 CR, or 16/45 CK. Wednesday, March 2nd, 8 h. p.m. The distance of the comet in S from the star C was nearly 4/9 FC, the distance of the star F from the right line CS produced was 1/24 FC, and the distance of the star B from the same right line was 5 times greater than the distance of the star F. And the right line NS produced passed between the stars H and I 5 or 6 times nearer to the star H than to the star I. Saturday, March 5th, 11½ h. p.m. When the comet was in T, the right line MT was equal to half a milliliter, and the right line LT produced passed between B and F 4 or 5 times nearer to F than to B. Cutting off from BF a fifth or sixth part thereof towards F, and MT produced passed on the outside of the space BF towards the star B 4 times nearer to the star B than to the star F. M was a very small star, scarcely to be seen by the telescope, but the star L was greater, and of about the 8th magnitude. Monday, March 7th, 9½ h. p.m. The comet being in V, the right line VA produced did pass between B and F, cutting off, from BF towards F, 1/10 of BF, and was to the right line V beta as 5 to 4. And the distance of the comet from the right line alpha beta was 1/2 V beta. Wednesday, March 9th, 8½ h. p.m. The comet being in X, the right line gamma X was equal to 1/4 gamma delta, and the perpendicular let fall from the star delta upon the right gamma X was 2/5 of gamma delta. The same night, at 12 h. The comet being in Y, the right line gamma Y was equal to 1/3 of gamma delta, or a little less, as perhaps 5/16 of gamma delta, and a perpendicular let fall from the star delta on the right line gamma Y was equal to about 1/6 or 1/7 gamma delta. But the comet being then extremely near the horizon, was scarcely discernible, and therefore its place could not be determined with that certainty as in the foregoing observations. From these observations, by constructions of figures and calculations, I deduced the longitudes and latitudes of the comet, and Mr. Pound, by correcting the places of the fixed stars, hath determined more correctly the places of the comet, which correct places are set down above. Though my micrometer was none of the best, yet the errors in longitude and latitude, as derived from my observations, scarcely exceed 1 minute. The comet, according to my observations, about the end of its motion, began to decline sensibly towards the north, from the parallel which it described about the end of February. Now, in order to determine the orbit of the comet out of the observations above described, I selected those 3 which Flamsteed made, December 21st, January 5th, and January 25th. From which I found St of 9842 1 parts, and Vt of 455, such as the semi-diameter of the orbis magnus contains 10,000. Then, for the first observation, assuming Tb of 5,657 of those parts, I found Sb 9747, B for the first time 412, S mu 9503, I lambda 413, B for the second time 421, OD 10186, X 8528, 4, PM 8450, MN 8475, NP 25. From whence, by the second operation, I collected the distance Tb 5640, and by this operation I at last deduced the distances Tx 4775 and Tau Z 11322. From which, limiting the orbit, I found its descending node in Cancer, and ascending node in Capricorn 1 degree 53. The inclination of its plane to the plane of the ecliptic 61 degrees 20 1/3, the vertex thereof, or the perihelion of the comet, distant from the node 8 degrees 38, and in Sagittarius 27 degrees 43 minutes, with latitude 7 degrees 34 minutes south, its lattice rectum 236.8. And the diurnal area described by a radius drawn to the Sun 93585, supposing the square of the semi-diameter of the orbis magnus 100000000, that the comet in this orbit moved directly according to the order of the signs, and on December 8 d.00 h.04 foot p. M was in the vertex or perihelion of its orbit. All which I determined by scale and compass, and the chords of angles, taken from the table of natural signs, in a pretty large figure, in which, to wit, the radius of the orbis magnus, consisting of 10,000 parts, was equal to 16 1/3 inches of an English foot. Lastly, in order to discover whether the comet did truly move in the orbit so determined, I investigated its places in this orbit partly by arithmetical operations, and partly by scale and compass, to the times of some of the observations. As may be seen in the following table. The comets. St. From Sun. Longitude. Computed. Latitude. Computed. Longitude. Observed. Latitude. Observed. Diff. Low. Diff. Lat. December 12th. 29. February 5th. March 5th. 2792. 8403. 16669. 21737. Capricorn 6 degree point 32 foot. Pisces 13.13 2/3. Taurus 17.00. 29.19 3/4. 8 degree point 18 1/2. 28.00. 15. 29 and 2/3. 12. 4. Capricorn 6 degrees 31 1/2. Pisces 13.11. Taurus 16.597/8. 29.206/7. 8 degree point 26. 28.101/12. 15.272/5. 12.3 +1/2. +1. +2. +0. -1. -7 1/2. -101 of 12. +2 1/4. +1/2. But afterwards Dr. Halley did determine the orbit to a greater accuracy by an arithmetical calculus than could be done by linear descriptions. And, retaining the place of the nodes in Cancer and Capricorn 1 degree 53 minutes, and the inclination of the plane of the orbit to the ecliptic 61 degrees 20 1/3, as well as the time of the comets being in perihelio, December 8D.00H. 04 foot, he found the distance of the perihelion from the ascending node measured in the comet's orbit 9 degrees 20 minutes, and the ludus rectum of the parabola 2430 parts, supposing the mean distance of the Sun from the Earth to be 100,000 parts. And from these data, by an accurate arithmetical calculus, he computed the places of the comet to the times of the observations as follows. The comets. True time. Dist from the Sun. Longitude. Computed. Latitude. Computed. Errors in long. Lat. D.H. December 4th, 46. June 21st, 37. June 24th, 18. May 26th, 20. 29.8, 3. August 30th, 10. January 5.3.1.1/2. 9.7, 0. 10.6, 6. 13.7, 9. July 25th, 59. August 30th, 22. February 6th, 35. 5.7.4.1/2. August 25th, 41. March May 11th, 39. 28,025. 61,076. 70,008. 75,576. 84,021. 86,661. 101,440. 110,959. 113,162. 120,000. 145,370. 155,303. 160,951. 166,686. 202,570. 216,205. Degree. Capricorn June 29th, 25. Aquarius May 6th, 30. 18.48.20. 28.22.45. Pisces December 13th, 40. 17.40.5. Aries 8.49.49. 18.44.36. 20.41.0. 26.0.21. Taurus 9.33.40. 13.17.41. November 15th, 11. 16. 58.55. 26.15.46. 29.18.35. Degree. 8.26.0 Bor. 21.43.20. 25.22.40. January 27th, 36. October 28th, 10. November 28th, 20. 26.15.15. December 24th, 54. 23.44.10. 22.17.30. 17.57.55. 16.42.7. April 16th, 15. 15.29.13. 12.48.0. May 15th, 40. Minus 3.5. Minus 1.42. Minus 1.3. Minus 1.28. Plus 1.59. Plus 1.45. Plus 0.56. Plus 0.32. 0.10. 0.33. Minus 1. 20. Minus 2.10. Minus 2.42. Minus 0.41. Minus 2.49. Plus 0.35. Minus 2.0. Plus 1.7. Minus 0.25. Plus 0.44. Plus 0.12. Minus 0.33. Plus 0.8. 0.58. Plus 0.18. Plus 0.2. Plus 1.25. Minus 0.11. Plus 0.14. Plus 2.0. Plus 1.10. Plus 2.14. This comet also appeared in the November before, and at Coburg, in Saxony, was observed by Mr. Gottfried Kirch, on the 4th of that month, on the 6th and 11th o.s., from its positions to the nearest fixed stars observed with sufficient accuracy, sometimes with a 2 feet, and sometimes with a 10 feet telescope. From the difference of longitudes of Coburg and London, 11 degree, and from the places of the fixed stars observed by Mr. Pound, Dr. Halley has determined the places of the comet as follows. November 3, 17h. 2 foot, apparent time at London, the comet was in Leo 29 degrees, 51, with 1 degree, 17 feet 45 inches latitude north. November 5. 15h.58 foot, the comet was in Virgo 3 degrees 23 minutes, with 1 degree 6 minutes nordal. Lat. November 10, 16h. 31 foot, the comet was equally distant from 2 stars in Leo which are Sigma and Tau in Bayer, but it had not quite touched the right line that joins them, but was very little distant from it. In Flamsteed's catalogue this star Sigma was then in Virgo 14 degrees 15 minutes, with 1 degree, 41 lat. North nearly, and Tau in Virgo 17 degrees 3½, with 0 degrees, 34 lat. South, and the middle point between those stars was Virgo 15 degrees 39½, with 0 degrees 33½ lat. North. Let the distance of the comet from that right line be about 10 foot or 12, and the difference of the longitude of the comet and that middle point will be 7, and the difference of the latitude nearly 7½. And thence it follows that the comet was in Virgo 15 degrees 32 minutes, with about 26 foot lat. North. The first observation from the position of the comet with respect to certain small fixed stars had all the exactness that could be desired. The second also was accurate enough. In the third observation, which was the least accurate, there might be an error of 6 or 7 minutes, but hardly greater. The longitude of the comet, as found in the first and most accurate observation, being computed in the aforesaid parabolic orbit, comes out Leo 29 degrees 30 minutes 22 seconds, its latitude north 1 degree 25 minutes 7 seconds, and its distance from the Sun 115546. Moreover, Dr. Halley, observing that a remarkable comet had appeared 4 times at equal intervals of 575 years, that is, in the month of September after Julius Caesar was killed, and CHR 531, in the consulate of Lampadius and Orestes, and CHR 1106, in the month of February, and at the end of the year 1680. And that with a long and remarkable tail, except when it was seen after Caesar's death, at which time, by reason of the inconvenient situation of the earth, the tail was not so conspicuous. Set himself to find out an elliptic orbit whose greater axis should be 138.2957 parts, the mean distance of the earth from the sun containing 10,000 such. In which orbit a comet might revolve in 575 years. And, placing the ascending node in Cancer 2 degrees 2 minutes, the inclination of the plane of the orbit to the plane of the ecliptic in an angle of 61 degrees 6 minutes 48 seconds, the perihelion of the comet in this plane in Sagittarius 22 degrees 44 minutes 25 seconds, the equal time of the perihelion December 7d. 23h.9 foot, the distance of the perihelion from the ascending node in the plane of the ecliptic 9 degrees 17 minutes 35 seconds, and its conjugate axis 184812, he computed the motions of the comet in this elliptic orbit. The places of the comet, as deduced from the observations, and as arising from computation made in this orbit, may be seen in the following table. True time. Longitudes. Observed. Latitude. North. OBS. Longitude. Computed. Latitude. Computed. Errors in. Long. Lat. D.H. November-March 16th, 47. May 15th, 37. October 16th, 18. 16.17.00. 18.21.34. 20.17.0. 23.17.5. December 4th, 46. June 21st, 37. June 24th, 18. May 26th, 21. 29.8.3. August 30th, 10. January 5.6.11 half. 9.7.7. 10.6.6. 13.7.9. July 25th, 59. August 30th, 22. February 6th, 35. 5.7. 4.5. August 25th, 41. March January 11th, 10. May 11th, 39. September 8th, 38. Degree. Leo 29.51.0. Virgo 3.23.0. 15.32.0. Capricorn 6.32.30. Aquarius 5. 8.12. 18.49.23. 28.24.13. Pisces October 13th, 41. 17.38.0. Aries 8.48.53. 18.44.4. 20.40.50. 25.59.48. Taurus 9.35. 0. 13.19.51. 15.13.53. 16.59, 6. 26.18.35. 27.52.42. 29. 18, 0. Gemini 0.43.4. Degree. January 17, 45. 1.6, 0. 0.27, 0. 8.28, 0. 21.42.13. 25.23, 5. 27, 0.52. 28, 9.58. November 28, 53. 26.15, 7. November 24, 56. 23.43.32. 22.17.28. 17.56.30. 16.42.18. 16, 4. 1. 15.27, 3. 12.46.46. December 23, 40. 12, 3.16. 11.45.52. Degree. Leo 29.51.22. Virgo 3. 24.32. 15.33, 2. Libra August 16, 45. 18.52.15. October 28, 36. Scorpio 13.22.42. Capricorn 6.31.20. Aquarius 5. 6.14. 18.47.30. 28.21.42. Pisces November 13, 14. 17.38.27. Aries 8.48.51. 18.43.51. 20.40.23. 26, 0. 8. Taurus 9.34.11. 13.18.25. November 15, 59. 16.59.17. 26.16.59. 27.51.47. 29.20.11. Gemini 0.42. 43. Degree. 1, 17, 32n. 1, 6. 9. 0.25, 7. 0.53, 7s. January 26, 54. 1.53.35. 2.29, 0. 8.29, 6n. 21.44.42. 25.23.35. 27, 2. 1. October 28, 38. November 28, 37. 26.14.57. December 24, 17. 23.43.25. 22.16.32. 17.56, 6. 16.40, 5. 16, 2.17. 15.27, 0. 12.45.22. December 22, 28. 12, 2.50. 11.45. 35. Plus 0.22. Plus 1.32. Plus 1.2. Minus 1.10. Minus 1.58. Minus 1.53. Minus 2.31. Plus 0, 33. Plus 0.7. Minus 0.2. Minus 0.13. Minus 0.27. Plus 0.20. Dash 0, 49. minus 1.23, minus 1.54, plus 0.11, minus 1.36, minus 0.55, plus 2.11, minus 0.21, minus 0.13, plus 0.9, minus 1.53, plus 1.6, plus 2.29, plus 0.30, plus 1.9, plus 0.40, minus 0.16, minus 0.10, plus 0.21, minus 0.7, minus 0.56, minus 0.24, minus 2.13, minus 1.54, minus 0, 3, minus 1.24, minus 1.12, minus 0.26, minus 0, 17. The observations of this comet from the beginning to the end agree perfectly with the motion of the comet in the orbit just now described as the motions of the planets do with the theories from whence they are calculated. And by this agreement plainly evince that it was one and the same comet that appeared all that time, and also that the orbit of that comet is here rightly defined. In the foregoing table we have omitted the observations of November 16, 18, 20. And 23, as not sufficiently accurate, for at those times several persons had observed the comet. November 17, O.S., Pontius and his companions, at 6h. In the morning at Rome, that is, 5h. 10 foot at London, by threads directed to the fixed stars, observed the comet in Libra 8 degrees 30 minutes, with latitude 0 degrees 40 south. Their observations may be seen in a treatise which Pontius published concerning this comet. Celius, who was present, and communicated his observations in a letter to Cassini, saw the comet at the same hour in Libra 8 degrees 30 minutes, with latitude 0 degrees 30 south. It was likewise seen by Galicius at the same hour at Avignon, that is, at 5h. 42-foot morning at London, in Libra 8 degrees without latitude. But by the theory the comet was at that time in Libra 8 degrees 16 minutes 45 seconds, and its latitude was 0 degrees 53 minutes 7 seconds south. November 18, at 6h. 30 foot in the morning at Rome, that is, at 5h. 40 foot at London, Pontius observed the comet in Libra 13 degrees 30, with latitude 1 degree 20 minutes south, and Celius in Libra 13 degrees 30 minutes, with latitude 1 degree 00 south. But at 5h. 30 foot in the morning at Avignon, Galicius saw it in Libra 13 degrees 0 minutes, with latitude 1 degree 00 south. In the University of La Flèche, in France, at 5h. In the morning, that is, at 5h. 9 at London, it was seen by P. Engo, in the middle between two small stars, one of which is the middle of the three which lie in a right line in the southern hand of Virgo, Bayer's Psi, and the other is the outmost of the wing, Bayer's Theta. Whence the comet was then in Libra 12 degrees 46 minutes with latitude 50 foot south. And I was informed by Dr. Halley, that on the same day at Boston in New England, in the latitude of 42.5 degrees at 5h. In the morning, that is, at 9h. 44 foot in the morning at London, the comet was seen near Libra 14 degrees, with latitude 1 degree 30 south. November 19, at 4.5h. At Cambridge, the comet, by the observation of a young man, was distant from Spica Virgo about 2 degrees towards the northwest. Now the spike was at that time in Libra 19 degrees 23 minutes 47 seconds, with latitude 2 degrees 1 minute 59 seconds south. The same day, at 5h. In the morning, at Boston in New England, the comet was distant from Spica Virgo 1 degree, with the difference of 40 foot in latitude. The same day, in the island of Jamaica, it was about 1 degree distant from Spica Virgo. The same day, Mr. Arthur Storer, at the river Patuxent, near Hunting Creek, in Maryland, in the confines of Virginia, in lat. 38 1/2 degree, at 5 in the morning, that is, at 10 h. At London, saw the comet above Spica Virgo, and very nearly joined with it, the distance between them being about 3/4 degree. And from these observations compared, I conclude, that at 9 h. 44 foot at London the comet was in Libra 18 degrees 50 minutes, with about 1 degree 25 minutes latitude south. Now by the theory the comet was at that time in Libra 18 degrees 52 minutes 15 seconds, with 1 degree 26 minutes 54 seconds lat. South. November 20th, Montanari, Professor of Astronomy at Padua, at 6 h. In the morning at Venice, that is, 5h.10 at London, saw the comet in Libra 23 degrees, with latitude 1 degree 30 minutes south. The same day, at Boston, it was distant from Spica Virgo by about 4 degrees of longitude east, and therefore was in Libra 23 degrees 24 minutes nearly. November 21, Pontius and his companions, at 7:14 h. In the morning, OB served the comet in Libra 27 degrees 50 minutes, with latitude 1 degree 16 minutes south, Celius, in Libra 28 degree, P. Ango at 5 h. In the morning, in Libra 27 degrees 45 minutes, Montanari in Libra 27 degrees 51 minutes. The same day, in the island of Jamaica, it was seen near the beginning of Scorpio, and of about the same latitude with Spica Virgo, that is, 2 degrees 2 minutes. The same day, at 5 h. Morning, at Balasore, in the East Indies, that is, at 11 h. 20 foot of the night preceding at London, the distance of the comet from Spica Virgo was taken 7 degrees 35 minutes to the east. It was in a right line between the spike and the balance, and therefore was then in Libra 26 degrees 58 minutes, with about 1 degree 11 minutes lat. South, and after 5 hours. 40 foot, that is, at 5 h. Morning at London, it was in Libra 28 degrees 12 minutes, with 1 degree 16 minutes lat. South. Now by the theory the comet was then in Libra 28 degrees 10 minutes 36 seconds, with 1 degree 53 minutes 35 seconds lat. South. November 22nd, the comet was seen by Montanari in Scorpio 2 degrees 33 minutes. But at Boston in New England, it was found in about Scorpio 3 degrees, and with almost the same latitude as before, that is, 1 degree 30 minutes. The same day, at 5 h. Morning at Balasore, IHE comet was observed in Scorpio 1 degree 50 minutes, and therefore at 5 h. Morning at London, the comet was Scorpio 3 degrees 5 minutes nearly. The same day, at 6:30 h. In the morning at London, Dr. Hooke observed it in about Scorpio 3 degrees 30 minutes, and that in the right line which passeth through Spica Virgo and Coeur Leonis. Not, indeed, exactly, but deviating a little from that line towards the north. Montanari likewise observed, that this day, and some days after, a right line drawn from the comet through Spica passed by the south side of Coeur Leonis at a very small distance therefrom. The right line through Coeur Leonis and Spica Virgo did cut the ecliptic in Virgo 3 degrees 46 minutes at an angle of 2 degrees 51 minutes, and if the comet had been in this line and in Scorpio 3 degrees, its latitude would have been 2 degrees 26 minutes. But since Hooke and Montanari agree that the comet was at some small distance from this line towards the north, its latitude must have been something less. On the 20th, by the observation of Montanari, its latitude was almost the same with that of Spica Virgo, that is, about 1 degree 30 minutes. But by the agreement of Hooke, Montanari, and Ango, the latitude was continually increasing, and therefore must now, on the 22d, be sensibly greater than 1 degree 30 minutes. And, taking a mean between the extreme limits but now stated, 2 degrees 26 minutes and 1 degree 30 minutes, the latitude will be about 1 degree 58 minutes. Hooke and Montanari agree that the tail of the comet was directed towards Spica Virgo, declining a little from that star towards the south according to Hooke, but towards the north according to Montanari. And, therefore, that declination was scarcely sensible, and the tail, lying nearly parallel to the equator, deviated a little from the opposition of the sun towards the north. November 23, O.S., at 5h. Morning, at Nuremberg, that is, at 4:30 h. At London, Mr. Zimmermann saw the comet in Scorpio 8 degrees 8 minutes, with 2 degrees 31 minutes south lat. Its place being collected by taking its distances from fixed stars. November 24, before sunrising, the comet was seen by Montanari in Scorpio 12 degrees 52 minutes on the north side of the right line through Scior Leonis and Spica Virgo, and therefore its latitude was something less than 2 degrees 38 minutes. And since the latitude, as we said, by the concurring observations of Montanari, Engo, and Hooke, was continually increasing, therefore, it was now, on the 24th, something greater than 1 degree 58 minutes. And, taking the mean quantity, may be reckoned 2 degrees 18 minutes, without any considerable error. Pontius and Gelasius will have it that the latitude was now decreasing, and Cellius, and the observer in New England, that it continued the same, viz. of about 1 degree, or 1/2 degree. The observations of Pontius and Cellius are more rude, especially those which were made by taking the azimuths and altitudes, as are also the observations of Gelasius. Those are better which were made by taking the position of the comet to the fixed stars by Montanari, Hooke, Engo, and the observer in New England, and sometimes by Pontius and Cellius. The same day, at 5h. Morning, at Balasore, the comet was observed in Scorpio 11 degrees 45 minutes, and, therefore, at 5h. Morning at London, was in Scorpio 13 degrees nearly. And, by the theory, the comet was at that time in Scorpio 13 degrees 22 minutes 2 seconds. November 25, before sunrise, Montanari observed the comet in Scorpio 17 3/4 nearly, and Cellius observed at the same time that the comet was in a right line between the bright star in the right thigh of Virgo and the southern scale of Libra. And this right line cuts the comet's way in Scorpio 18 degrees 36 minutes. And, by the theory, the comet was in Scorpio 18 1/3 degree nearly. From all this it is plain that these observations agree with the theory, so far as they agree with one another. And by this agreement it is made clear that it was one and the same comet that appeared all the time from November 4 to March 9. The path of this comet did twice cut the plane of the ecliptic, and therefore was not a right line. It did cut the ecliptic not in opposite parts of the heavens, but in the end of Virgo and beginning of Capricorn, including an arc of about 98 degrees, and therefore the way of the comet did very much deviate from the path of a great circle. For in the month of November it declined at least 3 degrees from the ecliptic towards the south. And in the month of December following it declined 29 degrees from the ecliptic towards the north. The two parts of the orbit in which the comet descended towards the sun, and ascended again from the sun, declining one from the other by an apparent angle of above 30 degrees, as observed by Montanari. This comet travelled over 9 signs, to wit, from the last degree of Leo to the beginning of Gemini, beside the sign of Leo, through which it passed before it began to be seen. And there is no other theory by which a comet can go over so great a part of the heavens with a regular motion. The motion of this comet was very unequable, for about the 20th of November it described about 5 degrees a day. Then its motion being retarded between November 26 and December 12, to wit, in the space of 15½ days, it described only 40 degrees. But the motion thereof being afterwards accelerated, it described near 5 degrees a day, till its motion began to be again retarded. And the theory which justly corresponds with a motion so unequable, and through so great a part of the heavens, which observes the same laws with the theory of the planets, and which accurately agrees with accurate astronomical observations, cannot be otherwise than true. And, thinking it would not be improper, I have given a true representation of the orbit which this comet described, and of the tail which it emitted in several places, in the annexed figure, protracted in the plane of the trajectory. In this scheme ABC represents the trajectory of the comet, D the sun DE the axis of the trajectory, DF the line of the nodes, gh the intersection of the sphere of the orbis magnus with the plane of the trajectory, I the place of the comet November 4, n. 1680, k the place of the same November 11th, l the place of the same November 19th, m its place December 12th, n its place December 21st, o its place December 29th, p its place January 5th following, q its place January 25th, r its place February 5th, south its place February 25th, t its place March 5th, and v its place March 9th. In determining the length of the tail, I made the following observations. November 4th and 6th, the tail did not appear. November 11th, the tail just begun to shew itself, but did not appear above half a degree long through a 10-feet telescope. November 17th, the tail was seen by Pontius more than 15 degrees long. November 18, in New England, the tail appeared 30 degrees long, and directly opposite to the Sun, extending itself to the planet Mars, which was then in Virgo, 9 degrees 54 minutes, November 19th. In Maryland, the tail was found 15 degrees or 20 degrees long, December 10th, by the observation of Mr. Flamsteed. The tail passed through the middle of the distance intercepted between the tail of the serpent of Ophiuchus and the star Delta in the south wing of Aquila, and did terminate near the stars A, Omega, B, in Bayer's tables. Therefore the end of the tail was in Capricorn 19½ degree, with latitude about 34 1/4 degree north. December 11th, it ascended to the head of Sagitta, Bayer's Alpha, Beta, terminating in Capricorn 26 degrees 43 minutes, with latitude 38 degrees 34 minutes north. December 12, it passed through the middle of Sagitta, nor did it reach much farther, terminating in Aquarius 4 degrees, with latitude 42 1/2 degree north nearly. But these things are to be understood of the length of the brighter part of the tail. For with a more faint light, observed, too, perhaps, in a serener sky, at Rome, December 12, 5h. 40 foot, by the observation of Pontius, the tail arose to 10 degrees above the rump of the swan, and the side thereof towards the west and towards the north was 45, distant from this star. But about that time the tail was 3 degrees broad towards the upper end. And therefore the middle thereof was 2 degrees 15 distant from that star towards the south, and the upper end was Pisces in 22 degrees, with latitude 61 degrees north, and thence the tail was about 70 degrees long. December 21, it extended almost to Cassiopeia's chair, equally distant from Beta and from Skeeter, so as its distance from either of the two was equal to the distance of the one from the other, and therefore it did terminate in Aries 24 degrees, with latitude 47 1/2 degree. December 29, it reached to a contact with Skeet on its left, and exactly filled up the space between the two stars in the northern foot of Andromeda, being 54 degrees in length, and therefore terminated in Taurus 19 degrees, with 35 degrees of latitude. Jan. 5, it touched the star Pi in the breast of Andromeda on its right side, and the star Mu of the girdle on its left, and, according to our observations, was 40 degrees long, but it was curved, and the convex side thereof lay to the south. And near the head of the comet it made an angle of 4 degrees with the circle which passed through the Sun and the comet's head, but towards the other end it was inclined to that circle in an angle of about 10 degrees or 11 degree. And the chord of the tail contained with that circle an angle of 8 degrees. January 13th, the tail terminated between Alamec and Algol, with a light that was sensible enough, but with a faint light it ended over against the star Kappa in Perseus's side. The distance of the end of the tail from the circle passing through the Sun and the comet was 3 degrees 50 minutes, and the inclination of the chord of the tail to that circle was 8 1/2 degree. January 25th and 26th. It shone with a faint light to the length of 6 degrees or 7 degree. And for a night or two after, when there was a very clear sky, it extended to the length of 12 degrees, or something more, with a light that was very faint and very hardly to be seen. But the axis thereof was exactly directed to the bright star in the eastern shoulder of Auriga, and therefore deviated from the opposition of the Sun towards the north by an angle of 10 degrees. Lastly, February 10, with a telescope I observed the tail 2 degrees long, for that fainter light which I spoke of did not appear through the glasses. But Pontius writes, that, on February 7, he saw the tail 12 degrees long. February 25, the comet was without a tail, and so continued till it disappeared. Now if one reflects upon the orbit described, and duly considers the other appearances of this comet, he will be easily satisfied that the bodies of comets are solid, compact, fixed, and durable, like the bodies of the planets. For if they were nothing else but the vapors or exhalations of the Earth, of the Sun, and other planets, this comet, in its passage by the neighborhood of the Sun, would have been immediately dissipated. For the heat of the Sun is as the density of its rays, that is, reciprocally as the square of the distance of the places from the Sun. Therefore, since on December 8, when the comet was in its perihelion, the distance thereof from the center of the Sun was to the distance of the Earth from the same as about 6 to 1,000. The Sun's heat on the comet was at that time to the heat of the summer sun with us as 1,000,000 to 36, or as 28,000 to 1. But the heat of boiling water is about 3 times greater than the heat which dry earth acquires from the summer sun, as I have tried. And the heat of red-hot iron, if my conjecture is right, is about 3 or 4 times greater than the heat of boiling water. And therefore the heat which dry earth on the comet, while in its perihelion, might have conceived from the rays of the sun, was about 2,000 times greater than the heat of red-hot iron. But by so fierce a heat, vapors and exhalations, and every volatile matter, must have been immediately consumed and dissipated. This comet, therefore, must have conceived an immense heat from the sun, and retained that heat for an exceeding long time. For a globe of iron of an inch in diameter, exposed red-hot to the open air, will scarcely lose all its heat in an hour's time. But a greater globe would retain its heat longer in the proportion of its diameter. Because the surface, in proportion to which it is cooled by the contact of the ambient air, is in that proportion less in respect of the quantity of the included hot matter. And therefore a globe of red-hot iron equal to our Earth, that is, about 40 million feet in diameter, would scarcely cool in an equal number of days, or in above 50,000 years. But I suspect that the duration of heat may, on account of some latent causes, increase in a yet less proportion than that of the diameter, and I should be glad that the true proportion was investigated by experiments. It is farther to be observed, that the comet in the month of December, just after it had been heated by the sun, did emit a much longer tail, and much more splendid, than in the month of November before, when it had not yet arrived at its perihelion. And, universally, the greatest and most fulgent tails always arise from comets immediately after their passing by the neighborhood of the sun. Therefore the heat received by the comet conduces to the greatness of the tail, from whence, I think I may infer, that the tail is nothing else but a very fine vapor, which the head or nucleus of the comet emits by its heat. But we have had 3 several opinions about the tails of comets, for some will have it that they are nothing else but the beams of the sun's light transmitted through the comets' heads, which they suppose to be transparent. Others, that they proceed from the refraction which light suffers in passing from the comet's head to the earth. And, lastly, others, that they are a sort of clouds or vapor constantly rising from the comets' heads, and tending towards the parts opposite to the sun. The first is the opinion of such as are yet unacquainted with optics. For the beams of the sun are seen in a darkened room only in consequence of the light that is reflected from them by the little particles of dust and smoke which are always flying about in the air. And, for that reason, in air impregnated with thick smoke, those beams appear with great brightness, and move the sense vigorously. In a yet finer air they appear more faint, and are less easily discerned. But in the heavens, where there is no matter to reflect the light, they can never be seen at all. Light is not seen as it is in the beam, but as it is thence reflected to our eyes. For vision can be no otherwise produced than by rays falling upon the eyes. And, therefore, there must be some reflecting matter in those parts where the tails of the comets are seen, for otherwise, since all the celestial spaces are equally illuminated by the sun's light, no part of the heavens could appear with more splendor than another. The second opinion is liable to many difficulties. The tails of comets are never seen variegated with those colors which commonly are inseparable from refraction. And the distinct transmission of the light of the fixed stars and planets to us is a demonstration that the ether or celestial medium is not endowed with any refractive power, for as to what is alleged, that the fixed stars have been sometimes seen by the Egyptians environed with a coma or capitalidium, because that has but rarely happened, it is rather to be ascribed to a casual refraction of clouds. And so the radiation and scintillation of the fixed stars to tin refractions both of the eyes and air, for upon laying a telescope to the eye, those radiations and scintillations immediately disappear. By the tremulous agitation of the air and ascending vapors, it happens that the rays of light are alternately turned aside from the narrow space of the pupil of the eye. But no such thing can have place in the much wider aperture of the object glass of a telescope, and hence it is that a scintillation is occasioned in the former case, which ceases in the latter. And this cessation in the latter case is a demonstration of the regular transmission of light through the heavens, without any sensible refraction. But, to obviate an objection that may be made from the appearing of no tail in such comets as shine but with a faint light, as if the secondary rays were then too weak to affect the eyes. And for that reason it is that the tails of the fixed stars do not appear, we are to consider, that by the means of telescopes the light of the fixed stars may be augmented above 100-fold, and yet no tails are seen. That the light of the planets is yet more copious without any tail, but that comets are seen sometimes with huge tails, when the light of their heads is but faint and dull. For so it happened in a comet of the year 1680, when in the month of December it was scarcely equal in light to the stars of the second magnitude, and yet emitted a notable tail, extending to the length of 40 degrees, 50 degrees, 60 degrees, or 70 degrees, and upwards. And afterwards, on the 27th and 28th of January, when the head appeared but us a star of the 7th magnitude, yet the tail, as we said above, with a light that was sensible enough, though faint, was stretched out to 6 or 7 degrees in length. And with a languishing light that was more difficultly seen, even to 12 degrees, and upwards. But on the 9th and 10th of February, when to the naked eye the head appeared no more, through a telescope I viewed the tail of 2 degrees in length. But farther, if the tail was owing to the refraction of the celestial matter, and did deviate from the opposition of the sun, according to the figure of the heavens, that deviation in the same places of the heavens should be always directed towards the same parts. But the comet of the year 1680, December 28 d.81 h. p.m., at London, was seen in Pisces 8 degrees 41 minutes, with latitude north 28 degrees 6 minutes, while the sun was in Capricorn 18 degrees 26 minutes. And the comet of the year 1577, December 29 d. was in Pisces 8 degrees 41 minutes, with latitude north 28 degrees 40 minutes, and the sun, as before, in about Capricorn 18 degrees 26 minutes. In both cases the situation of the earth was the same, and the comet appeared in the same place of the heavens. Yet in the former case the tail of the comet, as well by my observations as by the observations of others, deviated from the opposition of the sun towards the north by an angle of 4½ degrees. Whereas in the latter there was, according to the observations of Tycho, a deviation of 21 degrees towards the south. The refraction, therefore, of the heavens being thus disproved, it remains that the phenomena of the tails of comets must be derived from some reflecting matter. And that the tails of comets do arise from their heads, and tend towards the parts opposite to the sun, is farther confirmed from the laws which the tails observe. As that, lying in the planes of the comet's orbits which pass through the sun, they constantly deviate from the opposition of the sun towards the parts which the comet's heads in their progress along these orbits have left. That to a spectator, placed in those planes, they appear in the parts directly opposite to the sun, but, as the spectator recedes from those planes, their deviation begins to appear, and daily becomes greater. That the deviation, caeteris paribus, appears less when the tail is more oblique to the orbit of the comet, as well as when the head of the comet approaches nearer to the sun. Especially if the angle of deviation is estimated near the head of the comet. That the tails which have no deviation appear straight, but the tails which deviate are likewise bended into a certain curvature. That this curvature is greater when the deviation is greater, and is more sensible when the tail, cateris paribus, is longer, for in the shorter tails the curvature is hardly to be perceived. That the angle of deviation is less near the comet's head, but greater towards the other end of the tail. And that because the convex side of the tail regards the parts from which the deviation is made, and which lie in a right line drawn out infinitely from the sun through the comet's head. And that the tails that are long and broad, and shine with a stronger light, appear more resplendent and more exactly defined on the convex than on the concave side. Upon which accounts it is plain that the phenomena of the tails of comets depend upon the motions of their heads, and by no means upon the places of the heavens in which their heads are seen. And that, therefore, the tails of comets do not proceed from the refraction of the heavens, but from their own heads, which furnish the matter that forms the tail. For, as in our air, the smoke of a heated body ascends either perpendicularly if the body is at rest, or obliquely if the body is moved obliquely, so in the heavens, where all bodies gravitate towards the sun, smoke and vapor must, as we have already said, ascend from the sun, and either rise perpendicularly if the smoking body is at rest, or obliquely if the body, in all the progress of its motion, is always leaving those places from which the upper or higher parts of the vapor had risen before. And that obliquity will be least where the vapor ascends with most velocity, to wit, near the smoking body, when that is near the sun. But, because the obliquity varies, the column of vapor will be incurvated. And because the vapor in the preceding sides is something more recent, that is, has ascended something more late from the body, it will therefore be something more dense on that side, and must on that account reflect more light, as well as be better defined. I add nothing concerning the sudden uncertain agitation of the tails of comets, and their irregular figures, which authors sometimes describe, because they may arise from the mutations of our air, and the motions of our clouds, in part obscuring those tails. Or, perhaps, from parts of the Via Lactea, which might have been confounded with and mistaken for parts of the tails of the comets as they passed by. But that the atmospheres of comets may furnish a supply of vapor great enough to fill so immense spaces, we may easily understand from the rarity of our own air. For the air near the surface of our earth possesses a space 850 times greater than water of the same weight, and therefore a cylinder of air 850 feet high is of equal weight with a cylinder of water of the same breadth, and but 1 foot high. But a cylinder of air reaching to the top of the atmosphere is of equal weight with a cylinder of water about 33 feet high, and, therefore, if from the whole cylinder of air the lower part of 850 feet high is taken away, the remaining upper part will be of equal weight with a cylinder of water 32 feet high, and from thence, and by the hypothesis, confirmed by many experiments, that the compression of air is as the weight of the incumbent atmosphere, and that the force of gravity is reciprocally as the square of the distance from the center of the earth, raising a calculus, by Sr. Prop. XX, Book 2, I found, that, at the height of one semi-diameter of the earth, reckoned from the earth's surface, the air is more rare than with us in a far greater proportion than of the whole space within the orb of Saturn to a spherical space of 1 inch in diameter. And therefore if a sphere of our air of but 1 inch in thickness was equally rarefied with the air at the height of one semi-diameter of the earth from the earth's surface, it would fill all the regions of the planets to the orb of Saturn, and far beyond it. Wherefore since the air at greater distances is immensely rarefied, and the coma or atmosphere of comets is ordinarily about 10 times higher, reckoning from their centers, than the surface of the nucleus, and the tails rise yet higher, they must therefore be exceedingly rare. And though, on account of the much thicker atmospheres of comets, and the great gravitation of their bodies towards the sun, as well as of the particles of their air and vapors mutually one towards another, it may happen that the air in the celestial spaces and in the tails of comets is not so vastly rarefied. Yet from this computation it is plain that a very small quantity of air and vapor is abundantly sufficient to produce all the appearances of the tails of comets. For that they are, indeed, of a very notable rarity appears from the shining of the stars through them. The atmosphere of the earth, illuminated by the sun's light, though but of a few miles in thickness, quite obscures and extinguishes the light not only of all the stars, but even of the moon itself. Whereas the smallest stars are seen to shine through the immense thickness of the tails of comets, likewise illuminated by the sun, without the least diminution of their splendor. Nor is the brightness of the tails of most comets ordinarily greater than that of our air, an inch or two in thickness, reflecting in a darkened room the light of the sunbeams let in by a hole of the window shutter. And we may pretty nearly determine the time spent during the ascent of the vapor from the comet's head to the extremity of the tail, by drawing a right line from the extremity of the tail to the sun, and marking the place where that right line intersects the comet's orbit, for the vapor that is now in the extremity of the tail, if it has ascended in a right line from the sun, must have begun to rise from the head at the time when the head was in the point of intersection. It is true, the vapor does not rise in a right line from the sun, but, retaining the motion which it had from the comet before its ascent, and compounding that motion with its motion of ascent, arises obliquely. And, therefore, the solution of the problem will be more exact, if we draw the line which intersects the orbit parallel to the length of the tail. Or rather, because of the curvilinear motion of the comet, diverging a little from the line or length of the tail. And by means of this principle I found that the vapor which, January 25th, was in the extremity of the tail, had begun to rise from the head before December 11th, and therefore had spent in its whole ascent 45 days. But that the whole tail which appeared on December 10th had finished its ascent in the space of the 2 days then elapsed from the time of the comet's being in its perihelion. The vapor, therefore, about the beginning and in the neighborhood of the sun rose with the greatest velocity, and afterwards continued to ascend with a motion constantly retarded by its own gravity. And the higher it ascended, the more it added to the length of the tail, and while the tail continued to be seen, it was made up of almost all that vapor which had risen since the time of the comet's being in its perihelion. Nor did that part of the vapor which had risen first, and which formed the extremity of the tail, cease to appear, till its too great distance, as well from the sun, from which it received its light, as from our eyes, rendered it invisible. Whence also it is that the tails of other comets which are short do not rise from their heads with a swift and continued motion, and soon after disappear, but are permanent and lasting columns of vapors and exhalations, which, ascending from the heads with a slow motion of many days, and partaking of the motion of the heads which they had from the beginning, continue to go along together with them through the heavens. From whence again we have another argument proving the celestial spaces to be free, and without resistance, since in them not only the solid bodies of the planets and comets, but also the extremely rare vapors of comets' tails, maintain their rapid motions with great freedom, and for an exceeding long time. Kepler ascribes the ascent of the tails of the comets to the atmospheres of their heads, and their direction towards the parts opposite to the sun to the action of the rays of light carrying along with them the matter of the comets' tails. And without any great incongruity we may suppose, that, in so free spaces, so fine a matter as that of the ether may yield to the action of the rays of the sun's light, though those rays are not able sensibly to move the gross substances in our parts, which are clogged with so palpable a resistance. Another author thinks that there may be a sort of particles of matter endowed with a principle of levity, as well as others are with a power of gravity. That the matter of the tails of comets may be of the former sort, and that its ascent from the sun may be owing to its levity. But, considering that the gravity of terrestrial bodies is as the matter of the bodies, and therefore can be neither more nor less in the same quantity of matter, I am inclined to believe that this ascent may rather proceed from the rarefaction of the matter of the comet's tails. The ascent of smoke in a chimney is owing to the impulse of the air with which it is entangled. The air rarefied by heat ascends, because its specific gravity is diminished, and in its ascent carries along with it the smoke with which it is engaged. And why may not the tail of a comet rise from the sun after the same manner? For the sun's rays do not act upon the mediums which they pervade otherwise than by reflection and refraction. And those reflecting particles heated by this action, heat the matter of the ether which is involved with them. That matter is rarefied by the heat which it acquires, and because, by this rarefaction, the specific gravity with which it tended towards the sun before is diminished, it will ascend therefrom. and carry along with it the reflecting particles of which the tail of the comet is composed. But the ascent of the vapors is further promoted by their circumgyration about the sun, in consequence whereof they endeavor to recede from the sun, while the sun's atmosphere and the other matter of the heavens are either altogether quiescent, or are only moved with a slower circumgyration derived from the rotation of the sun. And these are the causes of the ascent of the tails of the comets in the neighborhood of the sun, where their orbits are bent into a greater curvature. And the comets themselves are plunged into the denser and therefore heavier parts of the sun's atmosphere, upon which account they do then emit tails of an huge length. For the tails which then arise, retaining their own proper motion, and in the meantime gravitating towards the sun, must be revolved in ellipses about the sun in like manner as the heads are, and by that motion must always accompany the heads, and freely adhere to them. For the gravitation of the vapors towards the sun can no more force the tails to abandon the heads, and descend to the sun, than the gravitation of the heads can oblige them to fall from the tails. They must by their common gravity either fall together towards the sun, or be retarded together in their common ascent therefrom. And, therefore, whether from the causes already described, or from any others, the tails and heads of comets may easily acquire and freely retain any position one to the other, without disturbance or impediment from that common gravitation. The tails, therefore, that rise in the perihelion positions of the comets will go along with their heads into far remote parts, and together with the heads will either return again from thence to us, after a long course of years, or rather will be there rarefied, and by degrees quite vanish away. For afterwards, in the descent of the heads towards the sun, new short tails will be emitted from the heads with a slow motion. And those tails by degrees will be augmented immensely, especially in such comets as in their perihelion distances descend as low as the sun's atmosphere, for all vapor in those free spaces is in a perpetual state of rarefaction and dilatation. And from hence it is that the tails of all comets are broader at their upper extremity than near their heads. And it is not unlikely but that the vapor, thus perpetually rarefied and dilated, may be at last dissipated and scattered through the whole heavens, and by little and little be attracted towards the planets by its gravity, and mixed with their atmosphere. For as the seas are absolutely necessary to the constitution of our earth, that from them, the sun, by its heat, may exhale a sufficient quantity of vapors, which, being gathered together into clouds, may drop down in rain, for watering of the earth, and for the production and nourishment of vegetables. Or, being condensed with cold on the tops of mountains, as some philosophers with reason judge, may run down in springs and rivers. So for the conservation of the seas, and fluids of the planets, comets seem to be required, that, from their exhalations and vapors condensed, the wastes of the planetary fluids spent upon vegetation and putrefaction, and converted into dry earth, may be continually supplied and made up. For all vegetables entirely derive their growths from fluids, and afterwards, in great measure, are turned into dry earth by putrefaction, and a sort of slime is always found to settle at the bottom of putrefied fluids. And hence it is that the bulk of the solid earth is continually increased, and the fluids, if they are not supplied from without, must be in a continual decrease, and quite fail at last. I suspect, moreover, that it is chiefly from the comets that spirit comes, which is indeed the smallest but the most subtle and useful part of our air, and so much required to sustain the life of all things with us. The atmospheres of comets, in their descent towards the sun, by running out into the tails, are spent and diminished, and become narrower, at least on that side which regards the sun. And in receding from the sun, when they less run out into the tails, they are again enlarged, if Hevelius has justly marked their appearances. But they are seen least of all just after they have been most heated by the sun, and on that account then emit the longest and most resplendent tails. And, perhaps, at the same time, the nuclei are environed with a denser and blacker smoke in the lowermost parts of their atmosphere, for smoke that is raised by a great and intense heat is commonly the denser and blacker. Thus the head of that comet which we have been describing, at equal distances both from the sun and from the earth, appeared darker after it had passed by its perihelion than it did before. For in the month of December it was commonly compared with the stars of the third magnitude, but in November with those of the first or second. And such as saw both appearances have described the first as of another and greater comet than the second. For, November 19, this comet appeared to a young man at Cambridge, though with a pale and dull light, yet equal to Spica Virginis. And at that time it shone with greater brightness than it did afterwards. And Montanari, November 20, St. Vet. Observed it larger than the stars of the first magnitude, its tail being then 2 degrees long. And Mr. Storer, by letters which have come into my hands, writes, that in the month of December, when the tail appeared of the greatest bulk and splendor, the head was but small, and far less than that which was seen in the month of November before sunrising. And, conjecturing at the cause of the appearance, he judged it to proceed from there being a greater quantity of matter in the head at first, which was afterwards gradually spent. And, which farther makes for the same purpose, I find, that the heads of other comets, which did put forth tails of the greatest bulk and splendor, have appeared but obscure and small. For in Brazil, March 5, 1668, 7 p.m., St. N.P. Valentinus Astancius saw a comet near the horizon, and towards the southwest, with a head so small as scarcely to be discerned, but with a tail above measure splendid, so that the reflection thereof from the sea was easily seen by those who stood upon the shore. And it looked like a fiery beam extended 23 degrees in length from the west to south, almost parallel to the horizon. But this excessive splendor continued only 3 days, decreasing apace afterwards. And while the splendor was decreasing, the bulk of the tail increased, whence in Portugal it is said to have taken up 1/4 of the heavens, that is, 45 degrees, extending from west to east with a very notable splendor. Though the whole tail was not seen in chose parts, because the head was always hid under the horizon, and from the increase of the bulk and decrease of the splendor of the tail, it appears that the head was then in its recess from the sun, and had been very near to it in its perihelion, as the comet of 1680 was. And we read, in the Saxon Chronicle, of a like comet appearing in the year 1106, the star whereof was small and obscure, as that of 1680, but the splendor of its tail was very bright, and like a huge fiery beam stretched out in a direction between the east and north, as Hevelius has it also from Simeon, the monk of Durham. This comet appeared in the beginning of February, about the evening, and towards the southwest part of heaven, from whence, and from the position of the tail, we infer that the head was near the sun. Matthew Paris says, it was distant from the sun by about a cubit, from 3 of the clock, rather 6, till 9, putting forth a long tail. Such also was that most resplendent comet described by Aristotle, Lib 1, Meteor. 6. The head whereof could not be seen, because it had set before the sun, or at least was hid under the sun's rays, but next day it was seen as well as might be, for, having left the sun but a very little way, it set immediately after it. And the scattered light of the head, obscured by the too great splendor of the tail, did not yet appear. But afterwards, as Aristotle says, when the splendor of the tail was now diminished, the head of the comet recovered its native brightness, and the splendor of its tail reached now to a third part of the heavens, that is, to 60 degrees. This appearance was in the winter season, and 4. Olymp. 101, and, rising to Orion's girdle, it there vanished away. It is true that the comet of 1618, which came out directly from under the sun's rays with a very large tail, seemed to equal, if not to exceed, the stars of the first magnitude. But, then, abundance of other comets have appeared yet greater than this, that put forth shorter tails, some of which are said to have appeared as big as Jupiter, others as big as Venus, or even as the moon. We have said, that comets are a sort of planets revolved in very eccentric orbits about the sun. And as, in the planets which are without tails, those are commonly less which are revolved in lesser orbits, and nearer to the sun. So in comets it is probable that those which in their perihelion approach nearer to the sun generally of less magnitude, that they may not agitate the sun too much by their attractions. But as to the transverse diameters of their orbits, and the periodic times of their revolutions, I leave them to be determined by comparing comets together which after long intervals of time return again in the same orbit. In the meantime, the following proposition may give some light in that inquiry. Proposition 42. Problem 22. To correct the comet's trajectory found as above. Operation 1. Assume that position of the plane of the trajectory which was determined according to the preceding proposition, and select 3 places of the comet, deduced from very accurate observations, and at great distances one from the other. Then suppose A to represent the time between the first observation and the second, and B the time between the second and the third, but it will be convenient that in one of those times the comet be in its perigee, or at least not far from it. From those apparent places find, by trigonometric operations, the 3 true places of the comet in that assumed plane of the trajectory. Then through the places found, and about the center of the Sun as the focus, describe a conic section by arithmetical operations, according to Prop. XXII, Book 1. Let the areas of this figure which are terminated by radii drawn from the Sun to the places found be D and E, to wit, D the area between the first observation and the second, and E the area between the second and third. And let T represent the whole time in which the whole area D plus E should be described with the velocity of the comet found by Prop. 16, Book 1. Op. 2. Retaining the inclination of the plane of the trajectory to the plane of the ecliptic, let the longitude of the nodes of the plane of the trajectory be increased by the addition of 20 or 30 minutes, which call p. Then from the aforesaid 3 observed places of the comet let the 3 true places be found, as before, in this new plane. As also the orbit passing through those places, and the 2 areas of the same described between the 2 observations, which call D and E, and let T be the whole time in which the whole area D plus E should be described. Op. 3. Retaining the longitude of the nodes in the first operation, let the inclination of the plane of the trajectory to the plane of the ecliptic be increased by adding their 2 20-foot or 30, which call Q. Then from the aforesaid 3 observed apparent places of the comet let the 3 true places be found in this new plane, as well as the orbit passing through them, and the 2 areas of the same described between the observation, which call delta and epsilon. And let tau be the whole time in which the whole area delta plus epsilon should be described. Then taking C to 1 as A to B, and G to 1 as D to E, and G to 1 as D to E, and gamma to 1 as delta to epsilon, let S be the true time between the first observation and the third. And, observing well the signs plus and dash, let such numbers m and n be found out as will make 2g, 2c, equals mg, mg plus n gamma, and 2t, 2s equals mt plus n tau. And if, in the first operation, I represents the inclination of the plane of the trajectory to the plane of the ecliptic, and k the longitude of either node, then I plus nq will be the true inclination of the plane of the trajectory to the plane of the ecliptic, and k plus mp the true longitude of the node. And, lastly, if in the first, second, and third operations, the quantities r, and ρ, represent the parameters of the trajectory, and the quantities 1/L, 1/L, 1/λ, the transverse diameters of the same. Then r plus Mr plus nρ, nr will be the true parameter, and will be the true transverse diameter of the trajectory which the comet describes. And from the transverse diameter given the periodic time of the comet is also given. QEI. But the periodic times of the revolutions of comets, and the transverse diameters of their orbits, cannot be accurately enough determined but by comparing comets together which appear at different times. If, after equal intervals of time, several comets are found to have described the same orbit, we may thence conclude that they are all but one and the same comet revolved in the same orbit. And then from the times of their revolutions the transverse diameters of their orbits will be given, and from those diameters the elliptic orbits themselves will be determined. To this purpose the trajectories of many comets ought to be computed, supposing those trajectories to be parabolic. For such trajectories will always nearly agree with the phenomena, as appears not only from the parabolic trajectory of the comet of the year 1680, which I compared above with the observations, but likewise from that of the notable comet which appeared in the year 1664 and 1665, and was observed by Hevelius, who, from his own observations, calculated the longitudes and latitudes thereof, though with little accuracy. But from the same observations Dr. Halley did again compute its places, and from those new places determined its trajectory, finding its ascending node in Gemini 21 degrees 13 minutes 55 seconds, the inclination of the orbit to the plane of the ecliptic 21 degrees 18 minutes 40 seconds. The distance of its perihelion from the node, estimated in the comet's orbit, 49 degrees 27 minutes 30 degrees, its perihelion in Leo 8 degrees 40 minutes 30 seconds, with heliocentric latitude south 16 degrees 1 minute 45 seconds, the comet to have been in its perihelion November 24 d.1 h.52 p.m. Equal time at London, or 13 h.8 foot at Danzig, O.S., and that the lattice rectum of the parabola was 410,286 such parts as the Sun's mean distance from the Earth is supposed to contain 100000. And how nearly the places of the comet computed in this orbit agree with the observations, will appear from the annexed table, calculated by Dr. Halley. Apar. Time. At Danzig. The observed distances of the comet from. The observed places. The places. Computed in. The orb. December. D. H. 3, 18, 29 1/2. The lion's heart. The virgin spike. Degree. 46.24.20. 22.52.10. Long Libra. Lat S. Degree. 7. 1.00. 21.39.0. Libra. Degree. July 1st, 29. 21.38.50. 4.18.11/2. The lion's heart. The virgin spike. 46.2.45. 23.52.40. Long Libra. Lat S. 6.15.0. 22.24.0. Libra. 6.16.5. 22.24.0. July 17th, 48. The lion's heart. The virgin spike. 44. 48.0. 27.53.40. Long Libra. Lat S. 3.6.0. 25.22.0. Libra. March 7th, 33. 25.21.40. July 17th, 48. The lion's heart. Orion's right shoulder. 53.15.15. 45.43.30. Long Leo. Lat S. 2.56.0. 49.25.0. Leo. 2.56.0. 49.25.0. 19.9. 25. Procyon. Bright star of whale's jaw. 35.13.50. 52.56.0. Long Gemini. Lat S. 28.40.30. 45.48.0. Gemini. 28.43.0. 45.46.0. 20.9.53 Procyon. Bright star of whale's jaw. 40.49.0. 40.04.0. Long Gemini. Lat S. 13.03.0. 39.54.0. Gemini. 13.5. 0. 39.5.0. 21.9.91 Orion's right shoulder. Bright star of whale's jaw. 26.21.25. 29.28.0. Long Gemini. Lat S. 2.16.0. 33.41.0. Gemini. February 18, 30. 33.39.40. 22.9.0. Orion's right shoulder. Bright star of whale's jaw. 29.47.0. 20.29. 30. Long Taurus. Lat S. 24.24.0. 27.45.0. Taurus. 24.27.0. 27.46.0. July 26, 58. The bright star of Aries. Aldebaran. 20.20.0. 26.44.0. Long Taurus. Lat S. 9.0.0. 12.36.0. Taurus. September 2, 28. 12.34.13. 27.6. 45. The bright star of Aries. Aldebaran. 20.45.0. 28.10.0. Long Taurus. Lat S. July 5, 40. 10.23.0. Taurus. July 8, 45. October 23, 13. July 28, 39. The bright star of Aries. Pallalicium. 18.29.0. 29.37.0. Long Taurus. Lat S. May 24, 45. August 22, 50. Taurus. 5.27. 52. August 23, 37. 31.6.45. Andromeda's girdle. Pallalicium. 30.48.10. 32.53.30. Long Taurus. Lat S. February 7, 40. 4.13.0. Taurus. February 8, 20. April 16, 25. January 1665. 7:37 1/2. Andromeda's girdle. Pallalicium. 25.11.0. December 25, 37. Long Aries. Lat N. 28.24. 47. 0.54.0. Aries. 28.24.0. 0.53.0. 13.7.0. Andromeda's head. Pallalicium. July 28, 10. 38.55.20. Long Aries. Lat N. June 27, 54. March 6, 50. Aries. June 27, 39. March 7, 40. July 24, 29. Andromeda's girdle. Pallalicium. 20.32.15. 40.5.0. Long Aries. Lat N. 26.29.15. May 25, 50. Aries. 26.28.50. 5.26.0. February. July 8, 37. Long Aries. Lat N. April 27, 46. July 3, 29. Aries. 27.24.55. July 3, 15. August 22, 46. Long Aries. Lat. N. 28.29.46. August 12, 36. Aries. 28.29.58. August 10, 25. March. 1.8. 16. Long Aries. Lat. N. 29.18.15. 8.36.26. Aries. 29.18.20. 8.36.12. July 8, 37. Long Taurus. Lat. N. 0.2.48. 8.56.30. Taurus. 0.2.42. 8.56. 56. In February, the beginning of the year 1665, the first star of Aries, which I shall hereafter call Gamma, was in Aries 28 degrees 30 minutes 15 seconds, with 7 degrees 8 minutes 58 seconds north lat. The second star of Aries was in Aries 29 degrees 17 minutes 18 seconds, with 8 degrees 28 minutes 16 seconds north lat. And another star of the seventh magnitude, which I call A, was in Aries 28 degrees 24 minutes 45 seconds, with 8 degrees 28 minutes 33 seconds north lat. The comet February 7D.7 h.30 foot at Paris, that is, February 7D.8 h.30 at Danzig, O.S. made a triangle with those stars Gamma and A, which was right-angled in Gamma, and the distance of the comet from the star Gamma was equal to the distance of the stars Gamma and A, that is, 1 degree 19 minutes 46 seconds of a great circle. And therefore in the parallel of the latitude of the star Gamma it was 1 degree 20 minutes 26 seconds. Therefore if from the longitude of the star Gamma there be subducted the longitude 1 degree 20 minutes 26 seconds, there will remain the longitude of the comet Aries 27 degrees 9 minutes 49 seconds. M. Auzout, from this observation of his, placed the comet in Aries 27 degrees 0 minutes, nearly, and, by the scheme in which Dr. Hooke delineated its motion, it was then in Aries 26 degrees 59 minutes 24 seconds. I place it in Aries 27 degrees 4 minutes 46 seconds, taking the middle between the two extremes. From the same observations, M. Auzout made the latitude of the comet at that time 7 degrees and 4 foot or 5 to the north. But he had done better to have made it 7 degrees 3 minutes 29 seconds, the difference of the latitudes of the comet and the star Gamma being equal to the difference of the longitude of the stars Gamma and A. February 22D.7 h.30 foot at London, that is, February 22D. 8 h. 46 foot at Danzig, the distance of the comet from the star A, according to Dr. Hooke's observation, as was delineated by himself in a scheme, and also by the observations of M. Auzout, delineated in like manner by M. Petit, was a fifth part of the distance between the star A and the first star of Aries, or 15 feet 57 inches, and the distance of the comet from a right line joining the star A and the first of Aries was a fourth part of the same fifth part, that is, 4 foot. And therefore the comet was in Aries 28 degrees 29 minutes 46 seconds, with 8 degrees 12 minutes 36 seconds north lat. March 1st, 7h at London, that is, March 1st, 8h.16 foot at Danzig. The comet was observed near the second star in Aries, the distance between them being to the distance between the first and second stars in Aries, that is, to 1 degree 33 minutes, as 4 to 45, according to Drive Hooke, or as 2 to 23 according to M. Godignes. And, therefore, the distance of the comet from the second star in Aries was 8 feet 16 inches according to Dr. Hooke, or 8 feet 5 inches according to M. Godignes, or, taking a mean between both, 8 feet 10 inches. But, according to M. Godignes, the comet had gone beyond the second star of Aries about a fourth or a fifth part of the space that it commonly went over in a day, to wit, about 1 foot 35 inches, in which he agrees very well with M. Auzout, or, according to Dr. Hooke, not quite so much, as perhaps only 1 foot. Wherefore if to the longitude of the first star in Aries we add 1 foot, and 8 feet 10 inches to its latitude, we shall have the longitude of the comet Aries 29 degrees 18 minutes, with 8 degrees 36 minutes 26 seconds north lat. March 7th, 7h. 30 foot at Paris, that is, March 7th, 8h.37 at Danzig. From the observations of M. Ozout, the distance of the comet from the second star in Aries was equal to the distance of that star from the star A, that is, 52.29 inch. And the difference of the longitude of the comet and the second star in Aries was 45 foot or 46, or, taking a mean quantity, 45 feet 30 inches, and therefore the comet was in Taurus 0 degrees 2 minutes 48 seconds. From the scheme of the observations of M. Ozout, constructed by M. Petit, Hevelius collected the latitude of the comet 8 degrees 54 minutes. But the engraver did not rightly trace the curvature of the comet's way towards the end of the motion, and Hevelius, in the scheme of M. Ozout's observations which he constructed himself, corrected this irregular curvature, and so made the latitude of the comet 8 degrees 55 minutes 30 seconds. And, by farther correcting this irregularity, the latitude may become 8 degrees 56, or 8 degrees 57 minutes. This comet was also seen March 9th, and at that time its place must have been in Taurus 0 degrees 18 minutes, with 9 degrees 3½ north lat. Nearly. This comet appeared 3 months together, in which space of time it travelled over almost 6 signs, and in one of the days thereof described almost 20 degrees. Its course did very much deviate from a great circle, bending towards the north, and its motion towards the end from retrograde became direct. And, notwithstanding its course was so uncommon, yet by the table it appears that the theory, from beginning to end, agrees with the observations no less accurately than the theories of the planets usually do with the observations of them, but we are to subduct about 2 foot when the comet was swiftest. Which we may effect by taking off 12 inch from the angle between the ascending node and the perihelion, or by making that angle 49 degrees 27 minutes 18 seconds. The annual parallax of both these comets, this and the preceding, was very conspicuous, and by its quantity demonstrates the annual motion of the Earth in the Orbis Magnus. This theory is likewise confirmed by the motion of that comet, which in the year 1683 appeared retrograde, in an orbit whose plane contained almost a right angle with the plane of the ecliptic, and whose ascending node, by the computation of Dr. Halley, was in Virgo 23 degrees 23 minutes, the inclination of its orbit to the ecliptic 83 degrees 11 minutes, its perihelion in Gemini 25 degrees 29 minutes 30 seconds, its perihelion distance from the Sun 56,020 of such parts as the radius of the Orbis Magnus contains 100,000. And the time of its perihelion July 2d.3h.50 foot. And the places thereof, computed by Dr. Halley in this orbit, are compared with the places of the same observed by Mr. Flamsteed, in the following table. 1683. EQ, time. Sun's place. Comets. Long com. Lat nor. Comput. Comets. Long obst. Lat nor. Observed. Diff. Long. Diff. Lat. D. H. July December 13th, 55. November 15th, 15. October 17th, 20. 23.13.40. 25.14.5. 31.9.42. 31.14.55. August February 14th, 56. April 10th, 49. 6.10. 9. September 10th, 26. 15.14.1. 16.15.10. 18.15.44. 22.14.44. 23.15.52. 26.16, 2. Degree. Leo January 2nd, 30. 2.53.12. 4.45.45. 10.38.21. 12.35.28. September 18, 22. 18.21.53. 20.17.16. February 22, 50. 23.56.45. 26.50.52. Virgo 2.47.13. 3.48, 2. 5.45.33. 9.35.49. 10.36.48. 13.31.10. Degree. Cancer 13. 5.42. 11.37.48. 10, 7. 6. May 10, 27. March 27, 53. Gemini 27.55. 3. 27.41, 7. 25.29.32. 23.18.20. 20.42.23. 16.7.57. March 30th, 48. 0.43, 7. Taurus 24.52.53. 11, 7.14. 7, 2.18. Aries 24.45.31. Degree. 29.28.13. 29.34, 0. 29.33.30. 28.51.42. 24.24.47. 26.22.52. 26.16.57. 25.16.19. October 24th, 49. 22. 17, 5. 20, 6.37. 11.37.33. 9.34.16. May 11th, 15. South. May 16th, 58. 8.17, 9. 16.38, 0. Degree. Cancer 13. 6.42. 11.39.43. 10, 8.40. May 11th, 30. 3.27, 0. Gemini 27.54.24. 27.41, 8. 25.28.46. 23.16.55. 20.40.32. 16, 5.55. March 26, 18. 0.41.55. Taurus 24.49. 5. November 7th, 12. 7, 1.17. Aries 24.44. 00. Degree. 29.28.20. 29.34.50. 29.34, 0. 28.50.28. 28.23.40. 26.22.25. 26.14.50. 25.17.28. December 24th, 19. 22.49, 5. 20, 6.10. 11.32, 1. 9.34.13. 5, 9.11. South. May 16th, 58. August 16th, 41. 16.38.20. Plus 1.00. Plus 1.55. plus 1.34, plus 1.03, 0.53, 0.39, plus 0, 1, 0.46, 1.25, 1, 51, 2, 2, 4.30, 1.12, 3.48, 0, 2, 1, 1, 1.31, plus 0.07, plus 0.50, plus 0.30, 1.14, minus 1, 7, 0.27, 2, 7, plus 1, 9, plus 1.30, plus 2, 0, 0.27, 5.32, 0, 3, 2, 4, minus 0, 3, 0.28, plus 0, 20. This theory is yet farther confirmed by the motion of that retrograde comet which appeared in the year 1682. The ascending node of this, by Dr. Halley's computation, was in Taurus 21 degrees 16 minutes 30 seconds. The inclination of its orbit to the plane of the ecliptic 17 degrees 56 minutes 0 seconds, its perihelion in Aquarius 2 degrees 52 minutes 50 seconds, its perihelion distance from the Sun 58,328 parts, of which the radius of the Orbis Magnus contains 100,000. The equal time of the comets being in its perihelion September 4D.7H.39. And its places, collected from Mr. Flamsteed's observations, are compared with its places computed from our theory in the following table. 1682. App. Time. Sun's place. Comets. Long comp. Lat nor. Comp. Com long. Observed. Lat nor. Observe. Diff. Long. Diff. Lat. D. H. August 19.16.38. 20.15.38. 21, 8.21. 22, 8. 8. August 29, 20. 30, 7.45. September 1st. 7.33. 4, 7.22. 5, 7.32. 8, 7. 16. 9, 7.26. Degree. Virgo 7. 0, 7. 7.5552. 8.36.14. 9.33.55. 16.22.40. 17.19.41. 19.16, 9. November 22nd, 28. October 23rd, 29. 26, 5.58. 27, 5. 9. Degree. Leo 18.1428. 24.46.23. 29.37.15. Virgo June 29, 53. Libra 12.37.54. 1536. 1. 20.30.53. 25.42, 0. 27, 0.46. 29.58.44. Scorpio 0.44. 10. Degree. 25.50, 7. 26.14.42. 26.20, 3. 26, 8.42. 18.37.47. 17.26.43. 15.130. December 23, 48. 11.33.08. September 26, 46. 8.49.10. Degree. Leo 18.14.40. 24.46.22. 29.38.02. Virgo 6.30. 3. Libra 12.37.49. 15.35.18. 20.27, 4. 25.40.58. 26.59.24. 29.58.45. Scorpio 0.44. 4. Degree. 25.49.55. December 26, 52. 26.17.37. 26, 7.12. 18.34, 5. 17.27.17. 15, 9.49. 12.22, 0. 11.33.51. September 26, 43. 8.48.25. 0.12. Plus 0. 1. 0.47. 0.10. Plus 0. 5. Plus 0.43. Plus 3.49. Plus 1. 2. Plus 1.22. 0.1. Plus 0. 6. Plus 0.12. Plus 1.50. Plus 2.26. Plus 1.30. Plus 3.42. 0. 34. Plus 3.11. Plus 1.48. 0.43. Plus 0. 3. Plus 0.45. This theory is also confirmed by the retrograde motion of the comet that appeared in the year 1723. The ascending node of this comet, according to the computation of Mr. Bradley, Savilian professor of astronomy at Oxford, was in Aries 14 degrees 16 minutes. The inclination of the orbit to the plane of the ecliptic 49 degrees 59 minutes. Its perihelion was in Taurus 12 degrees 15 minutes 20 seconds. Its perihelion distance from the Sun 998,651 parts, of which the radius of the Orbis Magnus contains 1,000,000, and the equal time of its perihelion September 16d 16h.10 foot. The places of this comet computed in this orbit by Mr. Bradley, and compared with the places observed by himself, his uncle Mr. Pound, and Dr. Halley, may be seen in the following table. 1723. EQ, time. Comets. Long OBS. Lat Nor. OBS. Comets. Lon. Com. Lat Nor. Comp. Diff. Lon. Diff. Lat. D. H. October 9.8. 5. October 6, 21. December 7, 22. August 14, 57. June 15, 35. June 21, 22. 22, 6.24. 24.8, 2. August 29, 56. June 30, 20. November May 5, 53. 8.7, 6. June 14, 20. July 20, 45. December July 6, 45. Degree. Aquarius July 22, 15. 6.41.12. 5.39.58. 4.59.49. 4.47.41. 4, 2.32. 3.59, 2. 3.55. 29. 3.56.17. 3.58, 9. April 16, 30. April 29, 36. 5, 2.16. 5.42.20. 8, 4.13. Degree. 5, 2. 0. 7.44.13. 11.55, 0. 14.43.50. 15.40.51. 19.41.49. 20, 8.12. 20.55.18. 22.20.27. 22.32.28. 23.38.33. 24, 4.30. 24.48.46. 25.24.45. 26.54.18. Degree. Aquarius, July 21, 26. 6.41.42. 5.40.19. 5. 0.37. 4.47.45. 4, 2.21. 3.59.10. 3.55.11. 3.56.42. 3.58.17. April 16, 23. April 29, 54. 5, 2.51. 5.43.13. 8, 3.55. Degree. 5, 2.47. 7.43.18. 11.54.55. 14.44, 1. 15.40.55. 19.42, 3. 20, 8.17. 20.55, 9. 22.20.10. 22.32.12. 23.38, 7. 24, 4.40. 24.48.16. 25.25.17. 26.53. 42. Plus 49. 50. 21. 48. 4. Plus 11. 8. Plus 18. 25. 8. Plus 7. 18. 35. 53. Plus 18. 47. Plus 55. Plus 5. 11. 4. 14. 5. Plus 9. Plus 17. Plus 16. Plus 26. 10. Plus 30. 32. Plus 36. From these examples it is abundantly evident that the motions of comets are no less accurately represented by our theory than the motions of the planets commonly are by the theories of them. And, therefore, by means of this theory, we may enumerate the orbits of comets, and so discover the periodic time of a comet's revolution in any orbit. Whence, at last, we shall have the transverse diameters of their elliptic orbits and their aphelion distances. That retrograde comet which appeared in the year 1607 described an orbit whose ascending node, according to Dr. Halley's computation, was in Taurus 20 degrees 21 minutes, and the inclination of the plane of the orbit to the plane of the ecliptic 17 degrees 2 minutes, whose perihelion was in Aquarius 2 degrees 16 minutes. And its perihelion distance from the Sun 58,680 of such parts as the radius of the Orbis Magnus contains 100,000, and the comet was in its perihelion October 16d.3h.50 foot. Which orbit agrees very nearly with the orbit of the comet which was seen in 1682. If these were not two different comets, but one and the same, that comet will finish one revolution in the space of 75 years. And the greater axis of its orbit will be to the greater axis of the Orbis Magnus as to 1, or as 1778 to 100, nearly. And the aphelion distance of this comet from the Sun will be to the mean distance of the Earth from the Sun as about 35 to 1. From which data it will be no hard matter to determine the elliptic orbit of this comet. But these things are to be supposed on condition, that, after the space of 75 years, the same comet shall return again in the same orbit. The other comets seem to ascend to greater heights, and to require a longer time to perform their revolutions. But, because of the great number of comets, of the great distance of their aphelions from the Sun, and of the slowness of their motions in the aphelions, they will, by their mutual gravitations, disturb each other. So that their eccentricities and the times of their revolutions will be sometimes a little increased, and sometimes diminished. Therefore we are not to expect that the same comet will return exactly in the same orbit, and in the same periodic times. It will be sufficient if we find the changes no greater than may arise from the causes just spoken of. And hence a reason may be assigned why comets are not comprehended within the limits of a zodiac, as the planets are, but, being confined to no bounds, are with various motions dispersed all over the heavens. Namely, to this purpose, that in their aphelions, where their motions are exceedingly slow, receding to greater distances one from another, they may suffer less disturbance from their mutual gravitations, and hence it is that the comets which descend the lowest, and therefore move the slowest in their aphelions, ought also to ascend the highest. The comet which appeared in the year 1680 was in its perihelion less distant from the Sun than by a sixth part of the Sun's diameter. And because of its extreme velocity in that proximity to the Sun, and some density of the Sun's atmosphere, it must have suffered some resistance and retardation. And therefore, being attracted something nearer to the Sun in every revolution, will at last fall down upon the body of the Sun. Nay, in its aphelion, where it moves the slowest, it may sometimes happen to be yet farther retarded by the attractions of other comets, and in consequence of this retardation descend to the Sun. So fixed stars, that have been gradually wasted by the light and vapors emitted from them for a long time, may be recruited by comets that fall upon them. And from this fresh supply of new fuel those old stars, acquiring new splendor, may pass for new stars. Of this kind are such fixed stars as appear on a sudden, and shine with a wonderful brightness at first, and afterwards vanish by little and little. Such was that star which appeared in Cassiopeia's chair, which Cornelius Gemma did not see upon the 8th of November, 1572, though he was observing that part of the heavens upon that very night, and the sky was perfectly serene. But the next night, November 9th, he saw it shining much brighter than any of the fixed stars, and scarcely inferior to Venus in splendor. Tycho Brahe saw it upon the 11th of the same month, when it shone with the greatest luster. And from that time he observed it to decay by little and little, and in 16 months' time it entirely disappeared. In the month of November, when it first appeared, its light was equal to that of Venus. In the month of December its light was a little diminished, and was now become equal to that of Jupiter. In January 1573 it was less than Jupiter, and greater than Sirius. And about the end of February and the beginning of March became equal to that star. In the months of April and May it was equal to a star of the second magnitude, in June, July, and August, to a star of the third magnitude. In September, October, and November, to those of the fourth magnitude, in December and January 1574 to those of the fifth, in February to those of the sixth magnitude, and in March it entirely vanished. Its color at the beginning was clear, bright, and inclining to white, afterwards it turned a little yellow, and in March 1573 it became ruddy, like Mars or Aldebaran, in May it turned to a kind of dusky whiteness, like that we observe in Saturn. And that color it retained ever after, but growing always more and more obscure. Such also was the star in the right foot of Serpentarius, which Kepler's scholars first observed September 30th, OS. 1604, with a light exceeding that of Jupiter, though the night before it was not to be seen, and from that time it decreased by little and little, and in 15 or 16 months entirely disappeared. Such a new star appearing with an unusual splendor is said to have moved Hipparchus to observe, and make a catalogue of, the fixed stars. As to those fixed stars that appear and disappear by turns, and increase slowly and by degrees, and scarcely ever exceed the stars of the third magnitude, they seem to be of another kind, which revolve about their axes, and, having a light and a dark side, shew those two different sides by turns. The vapors which arise from the sun, the fixed stars, and the tails of the comets, may meet at last with, and fall into, the atmospheres of the planets by their gravity, and there be condensed and turned into water and humid spirits. And from thence, by a slow heat, pass gradually into the form of salts, and sulfurs, and tinctures, and mud, and clay, and sand, and stones, and coral, and other terrestrial substances. General Scholium. The hypothesis of vortices is pressed with many difficulties. That every planet by a radius drawn to the sun may describe areas proportional to the times of description, the periodic times of the several parts of the vortices should observe the duplicate proportion of their distances from the sun. But that the periodic times of the planets may obtain the sesquiplicate proportion of their distances from the sun, the periodic times of the parts of the vortex ought to be in the sesquiplicate proportion of their distances. That the smaller vortices may maintain their lesser revolutions about Saturn, Jupiter, and other planets, and swim quietly and undisturbed in the greater vortex of the sun, the periodic times of the parts of the sun's vortex should be equal. But the rotation of the sun and planets about their axes, which ought to correspond with the motions of their vortices, recede far from all these proportions. The motions of the comets are exceedingly regular, are governed by the same laws with the motions of the planets, and can by no means be accounted for by the hypothesis of vortices. For comets are carried with very eccentric motions through all parts of the heavens indifferently, with a freedom that is incompatible with the notion of a vortex. Bodies projected in our air suffer no resistance but from the air. Withdraw the air, as is done in Mr. Boyle's vacuum, and the resistance ceases, for in this void a bit of line down and a piece of solid gold descend with equal velocity. And the parity of reason must take place in the celestial spaces above the earth's atmosphere, in which spaces, where there is no air to resist their motions, all bodies will move with the greatest freedom. And the planets and comets will constantly pursue their revolutions in orbits given in kind and position, according to the laws above explained. But though these bodies may, indeed, persevere in their orbits by the mere laws of gravity, yet they could by no means have at first derived the regular position of the orbits themselves from those laws. The 6 primary planets are revolved about the sun in circles concentric with the sun, and with motions directed towards the same parts, and almost in the same plane. 10 moons are revolved about the earth, Jupiter and Saturn, in circles concentric with them, with the same direction of motion, and nearly in the planes of the orbits of those planets. But it is not to be conceived that mere mechanical causes could give birth to so many regular motions, since the comets range over all parts of the heavens in very eccentric orbits. For by that kind of motion they pass easily through the orbs of the planets, and with great rapidity. And in their aphelions, where they move the slowest, and are detained the longest, they recede to the greatest distances from each other, and then suffer the least disturbance from their mutual attractions. This most beautiful system of the sun, planets, and comets, could only proceed from the counsel and dominion of an intelligent and powerful being. And if the fixed stars are the centers of other like systems, these, being formed by the likewise counsel, must be all subject to the dominion of one. Especially since the light of the fixed stars is of the same nature with the light of the sun, and from every system light passes into all the other systems, and lest the systems of the fixed stars should, by their gravity, fall on each other mutually, he hath placed those systems at immense distances one from another. This being governs all things, not as the soul of the world, but as Lord over all, and on account of his dominion he is wont to be called Lord God Pi Alpha Nu Tau Omicron Kappa Rho Tau Omega Rho, or universal ruler, for God is a relative word, and has a respect to servants. And deity is the dominion of God not over his own body, as those imagine who fancy God to be the soul of the world, but over servants. The supreme God is a being eternal, infinite, absolutely perfect. But a being, however perfect, without dominion, cannot be said to be Lord God, for we say, my God, your God, the God of Israel, the God of gods, and Lord of lords. But we do not say, my eternal, your eternal, the eternal of Israel, the eternal of gods. We do not say, my infinite, or my perfect. These are titles which have no respect to servants. The word God one usually signifies Lord. But every Lord is not a God. It is the dominion of a spiritual being which constitutes a God. A true, supreme, or imaginary dominion makes a true, supreme, or imaginary God. And from his true dominion it follows that the true God is a living, intelligent, and powerful being, and, from his other perfections, that he is supreme or most perfect. He is eternal and infinite, omnipotent and omniscient. That is, his duration reaches from eternity to eternity, his presence from infinity to infinity. He governs all things, and knows all things that are or can be done. He is not eternity or infinity, but eternal and infinite. He is not duration or space, but he endures and is present. He endures forever, and is everywhere present, and by existing always and everywhere, he constitutes duration and space. Since every particle of space is always, and every indivisible moment of duration is everywhere, certainly the Maker and Lord of all things cannot be never and nowhere. Every soul that has perception is, though in different times and in different organs of sense and motion, still the same indivisible person. There are given successive parts in duration, coexistent parts in space, but neither the one nor the other in the person of a man, or his thinking principle, and much less can they be found in the thinking substance of God. Every man, so far as he is a thing that has perception, is one and the same man during his whole life, in all and each of his organs of sense. God is the same God, always and everywhere. He is omnipresent not virtually only, but also substantially. For virtue cannot subsist without substance. In him too are all things contained and moved, yet neither affects the other. God suffers nothing from the motion of bodies, bodies find no resistance from the omnipresence of God. It is allowed by all that the supreme God exists necessarily, and by the same necessity he exists always and everywhere. Whence also he is all similar, all eye, all ear, all brain, all arm, all power to perceive, to understand, and to act. But in a manner not at all human, in a manner not at all corporeal, in a manner utterly unknown to us. As a blind male has no idea of colors, so have we no idea of the manner by which the all-wise God perceives and understands all things. He is utterly void of all body and bodily figure, and can therefore neither be seen, nor heard, nor touched, nor ought he to be worshipped under the representation of any corporeal thing. We have ideas of his attributes, but what the real substance of any thing is we know not. In bodies, we see only their figures and colors, we hear only the sounds, we touch only their outward surfaces, we smell only the smells, and taste the savors. But their inward substances are not to be known either by our senses, or by any reflex act of our minds, much less, then, have we any idea of the substance of God. We know him only by his most wise and excellent contrivances of things, and final causes. We admire him for his perfections, but we reverence and adore him on account of his dominion, for we adore him as his servants. And a God without dominion, providence, and final causes, is nothing else but fate and nature. Blind metaphysical necessity, which is certainly the same always and everywhere, could produce no variety of things. All that diversity of natural things which we find suited to different times and places could arise from nothing but the ideas and will of a being necessarily existing. But, by way of allegory, God is said to see, to speak, to laugh, to love, to hate, to desire, to give, to receive, to rejoice, to be angry, to fight, to frame, to work, to build. For all our notions of God are taken from the ways of mankind by a certain similitude, which, though not perfect, has some likeness, however. And thus much concerning God. To discourse of whom from the appearances of things, does certainly belong to natural philosophy. Hitherto we have explained the phenomena of the heavens and of our sea by the power of gravity, but have not yet assigned the cause of this power. This is certain, that it must proceed from a cause that penetrates to the very centers of the sun and planets, without suffering the least diminution of its force. That operates not according to the quantity of the surfaces of the particles upon which it acts, as mechanical causes used to do, but according to the quantity of the solid matter which they contain. And propagates its virtue on all sides to immense distances, decreasing always in the duplicate proportion of the distances. Gravitation towards the sun is made up out of the gravitations towards the several particles of which the body of the sun is composed. And in receding from the sun decreases accurately in the duplicate proportion of the distances as far as the orb of Saturn, as evidently appears from the quiescence of the aphelions of the planets. Nay, and even to the remotest aphelions of the comets, if those aphelions are also quiescent. But hitherto I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses. For whatever is not deduced from the phenomena is to be called an hypothesis, and hypotheses, whether metaphysical or physical, whether of occult qualities or mechanical, have no place in experimental philosophy. In this philosophy particular propositions are inferred from the phenomena, and afterwards rendered general by induction. Thus it was that the impenetrability, the mobility, and the impulsive force of bodies, and the laws of motion and of gravitation, were discovered. And to us it is enough that gravity does really exist, and act according to the laws which we have explained, and abundantly serves to account for all the motions of the celestial bodies, and of our sea. And now we might add something concerning a certain most subtle spirit which pervades and lies hid in all gross bodies. By the force and action of which spirit the particles of bodies mutually attract one another at near distances, and cohere, if contiguous, and electric bodies operate to greater distances, as well repelling as attracting the neighboring corpuscles. And light is emitted, reflected, refracted, inflected, and heats bodies. And all sensation is excited, and the members of animal bodies move at the command of the will, namely, by the vibrations of this spirit, mutually propagated along the solid filaments of the nerves, from the outward organs of sense to the brain. And from the brain into the muscles. But these are things that cannot be explained in few words, nor are we furnished with that sufficiency of experiments which is required to an accurate determination and demonstration of the laws by which this electric and elastic spirit operates. End of the mathematical principles. The system of the world. It was the ancient opinion of not a few, in the earliest ages of philosophy, that the fixed stars stood immovable in the highest parts of the world, that under the fixed stars the planets were carried about the sun. That the earth, as one of the planets, described an annual course about the sun, while by a diurnal motion it was in the meantime revolved about its own axis. And that the sun, as the common fire which served to warm the whole, was fixed in the center of the universe. This was the philosophy taught of old by Philolaus, Aristarchus of Samos, Plato in his riper years, and the whole sect of the Pythagoreans, and this was the judgment of Anaximander, more ancient than any of them. And of that wise king of the Romans, Numa Pompilius, who, as a symbol of the figure of the world with the sun in the center, erected a temple in honor of Vesta, of a round form, and ordained perpetual fire to be kept in the middle of it. The Egyptians were early observers of the heavens, and from them, probably, this philosophy was spread abroad among other nations. For from them it was, and the nations about them, that the Greeks, a people of themselves more addicted to the study of philology than of nature, derived their first, as well as soundest, notions of philosophy. And in the Vestal ceremonies we may yet trace the ancient spirit of the Egyptians. For it was their way to deliver their mysteries, that is, their philosophy of things above the vulgar way of thinking, under the veil of religious rites and hieroglyphic symbols. It is not to be denied but that Anaxagoras, Democritus, and others, did now and then start up, who would have it that the earth possessed the center of the world. And that the stars of all sorts were revolved towards the west about the earth quiescent in the center, some at a swifter, others at a slower rate. However, it was agreed on both sides that the motions of the celestial bodies were performed in spaces altogether free and void of resistance. The whim of solid orbs was of a later date, introduced by Eudoxus, Callippus, and Aristotle. When the ancient philosophy began to decline, and to give place to the new prevailing fictions of the Greeks. But, above all things, the phenomena of comets can by no means consist with the notion of solid orbs. The Chaldeans, the most learned astronomers of their time, looked upon the comets, which of ancient times before had been numbered among the celestial bodies, as a particular sort of planets, which, describing very eccentric orbits, presented themselves to our view only by turns, viz. once in a revolution, when they descended into the lower parts of their orbits. And as it was the unavoidable consequence of the hypothesis of solid orbs, while it prevailed, that the comets should be thrust down below the moon. So no sooner had the late observations of astronomers restored the comets to their ancient places in the higher heavens, but these celestial spaces were at once cleared of the encumbrance of solid orbs, which by these observations were broke into pieces, and discarded forever. Whence it was that the planets came to be retained within any certain bounds in these free spaces, and to be drawn off from the rectilinear courses, which, left to themselves, they should have pursued, into regular revolutions in curvilinear orbits, are questions which we do not know how the ancients explained. And probably it was to give some sort of satisfaction to this difficulty that solid orbs were introduced. The later philosophers pretend to account for it either by the action of certain vortices, as Kepler and Descartes, or by some other principle of impulse or attraction, as Borelli, Hooke, and others of our nation, for, from the laws of motion, it is most certain that these effects must proceed from the action of some force or other. But our purpose is only to trace out the quantity and properties of this force from the phenomena, p. 218, and to apply what we discover in some simple cases as principles, by which, in a mathematical way, we may estimate the effects thereof in more involved cases. For it would be endless and impossible to bring every particular to direct and immediate observation. We said, in a mathematical way, to avoid all questions about the nature or quality of this force, which we would not be understood to determine by any hypothesis. And therefore call it by the general name of a centripetal force, as it is a force which is directed towards some center, and as it regards more particularly a body in that center, we call it circumsolar, circumterrestrial, circumjovial. And in like manner in respect of other central bodies. That by means of centripetal forces the planets may be retained in certain orbits, we may easily understand, if we consider the motions of projectiles, page 75, 76, 77. For a stone projected is by the pressure of its own weight forced out of the rectilinear path, which by the projection alone it should have pursued, and made to describe a curved line in the air. And through that crooked way is at last brought down to the ground, and the greater the velocity is with which it is projected, the farther it goes before it falls to the earth. We may therefore suppose the velocity to be so increased, that it would describe an arc of 1, 2, 5, 10, 100, 1,000 miles before it arrived at the earth, till at last, exceeding the limits of the earth, it should pass quite by without touching it. Let AFB represent the surface of the earth, see its center, VD, V, VF, the curved lines which a body would describe, if projected in an horizontal direction from the top of an high mountain successively with more and more velocity, page 400. And, because the celestial motions are scarcely retarded by the little or no resistance of the spaces in which they are performed, to keep up the parity of cases, let us suppose either that there is no air about the earth, or at least that it is endowed with little or no power of resisting. And for the same reason that the body projected with a less velocity describes the lesser arc Vd, and with a greater velocity the greater arc Ve, and, augmenting the velocity, it goes farther and farther to F and G. If the velocity was still more and more augmented, it would reach at last quite beyond the circumference of the earth, and return to the mountain from which it was projected. And since the areas which by this motion it describes by a radius drawn to the center of the earth are, by Prop. 1, Book 1, Princip. Math. Proportional to the times in which they are described, its velocity, when it returns to the mountain, will be no less than it was at first, and, retaining the velocity, it will describe the same curve over and over, by the same law. But if we now imagine bodies to be projected in the directions of lines parallel to the horizon from greater heights, as of 5, 10, 100, 1000, or more miles, or rather as many semi-diameters of the Earth, those bodies, according to their different velocity, and the different force of gravity in different heights, will describe arcs either concentric with the Earth, or variously eccentric, and go on revolving through the heavens in those trajectories, just as the planets do in their orbs. As when a stone is projected obliquely, that is, any way but in the perpendicular direction, the perpetual deflection thereof towards the Earth from the right line in which it was projected is a proof of its gravitation to the Earth, no less certain than its direct descent when only suffered to fall freely from rest. So the deviation of bodies moving in free spaces from rectilinear paths, and perpetual deflection therefrom towards any place, is a sure indication of the existence of some force which from all quarters impels those bodies towards that place. And as, from the supposed existence of gravity, it necessarily follows that all bodies about the Earth must press downwards, and therefore must either descend directly to the Earth, if they are let fall from rest, or at least perpetually deviate from right lines towards the Earth, if they are projected obliquely. So from the supposed existence of a force directed to any center, it will follow, by the like necessity, that all bodies upon which this force acts must either descend directly to that center, or at least deviate perpetually towards it from right lines, if otherwise they should have moved obliquely in these right lines. And how from the motions given we may infer the forces, or from the forces given we may determine the motions, is shown in the 2 first books of our Principles of Philosophy. If the Earth is supposed to stand still, and the fixed stars to be revolved in free spaces in the space of 24 hours, it is certain the forces by which the fixed stars are retained in their orbs are not directed to the Earth, but to the centers of the several orbs, that is, of the several parallel circles, which the fixed stars, declining to one side and the other from the equator, describe daily. Also that by radii drawn to the centers of those orbs the fixed stars describe areas exactly proportional to the times of description. Then, because the periodic times are equal, by Core 3, Prop. 4, Book 1, it follows that the centripetal forces are as the radii of the several orbs, and that they will perpetually revolve in the same orbs. And the like consequences may be drawn from the supposed diurnal motion of the planets. That forces should be directed to no body on which they physically depend, but to innumerable imaginary points in the axis of the Earth, is an hypothesis too incongruous. It is more incongruous still that those forces should increase exactly in proportion of the distances from this axis, for this is an indication of an increase to immensity, or rather to infinity. Whereas the forces of natural things commonly decrease in receding from the fountain from which they flow. But, what is yet more absurd, neither are the areas described by the same star proportional to the times, nor are its revolutions performed in the same orb, for as the star recedes from the neighboring pole, both areas and orb increase. And from the increase of the area it is demonstrated that the forces are not directed to the axis of the Earth. And this difficulty, Core 1, Prop. 2, arises from the twofold motion that is observed in the fixed stars, one diurnal round the axis of the Earth, the other exceedingly slow round the axis of the ecliptic. And the explication thereof requires a composition of forces so perplexed and so variable, that it is hardly to be reconciled with any physical theory. That there are centripetal forces actually directed to the bodies of the Sun, of the Earth, and other planets, I thus infer. The Moon revolves about our Earth, and by radii drawn to its center, p. 390, describes areas nearly proportional to the times in which they are described, as is evident from its velocity compared with its apparent diameter. For its motion is slower when its diameter is less, and therefore its distance greater, and its motion is swifter when its diameter is greater. The revolutions of the satellites of Jupiter about that planet are more regular, page 386. For they describe circles concentric with Jupiter by equable motions, as exactly as our senses can distinguish. And so the satellites of Saturn are revolved about this planet with motions nearly, p. 387, circular and equable, scarcely disturbed by any eccentricity hitherto observed. That Venus and Mercury are revolved about the Sun, is demonstrable from their moon-like appearances, page 388. When they shine with a full face, they are in those parts of their orbs which in respect of the Earth lie beyond the Sun; when they appear half full, they are in those parts which lie over against the Sun. When horned, in those parts which lie between the Earth and the Sun, and sometimes they pass over the Sun's disk, when directly interposed between the Earth and the Sun. And Venus, with a motion almost uniform, describes an orb nearly circular and concentric with the Sun. But Mercury, with a more eccentric motion, makes remarkable approaches to the Sun, and goes off again by turns. But it is always swifter as it is near to the Sun, and therefore by a radius drawn to the Sun still describes areas proportional to the times. Lastly, that the Earth describes about the Sun, or the Sun about the Earth, by a radius from the one to the other, areas exactly proportional to the times, is demonstrable from the apparent diameter of the Sun compared with its apparent motion. These are astronomical experiments, from which it follows, by Prop. 1, 2, 3, in the first book of our Principles, and their corollaries, p. 212, 213, 214, that there are centripetal forces actually directed either accurately or without considerable error, to the centers of the Earth, of Jupiter, of Saturn, and of the Sun. In Mercury, Venus, Mars, and the lesser planets, where experiments are wanting, the arguments from analogy must be allowed in their place. That those forces, p. 212, 213, 214, decrease in the duplicate proportion of the distances from the center of every planet, appears by Course 6, Prop. 4, Book I, for the periodic times of the satellites of Jupiter are one to another, p. 386, 387, in the sesquiplicate proportion of their distances from the center of this planet. This proportion has been long ago observed in those satellites, and Mr. Flamsteed, who had often measured their distances from Jupiter by the micrometer, and by the eclipses of the satellites, wrote to me, that it holds to all the accuracy that possibly can be discerned by our senses. And he sent me the dimensions of their orbits taken by the micrometer, and reduced to the mean distance of Jupiter from the Earth, or from the Sun, together with the times of their revolutions. As follows. The greatest elongation of the satellites from the center of Jupiter as seen from the Sun. The periodic times of their revolutions. First, 2d, 3d, fourth, 1, 3, 4, 8, 48, 01, 46, 13 and a half. Or 108, 181, 186, 493 and a half. D. 1, 3, 7, 16, H. 18, 13, 03, 18, 28, 17, 59, 5, 36, 54, 36, 13. Whence the sesquiplicate proportion may be easily seen. For example, the 16d18h. 5 feet 13 inches is to the time 1d.18h.28 foot 36 inches 493 and a half, to 108, neglecting those small fractions which, in observing, cannot be certainly determined. Before the invention of the micrometer, the same distances were determined in semi-diameters of Jupiter thus. Distance of the first 2d, 3d, fourth, by Galileo, Simon Marius, Cassini. Borelli. More exactly. 6. 6. 5. 5 and 2/3. 10. 10. 8. 8 and 2/3. 16. 16. 13. 14. 28. 26. 23. 24 and 2/3. After the invention of the micrometer. By Townley. Flamsteed. More accurately by the eclipses. 551. 531. 5578. 878. 885. 8876. 1347. 1398. 14159. 24. 72. 2423. 24,903. And the periodic times of those satellites, by the observations of Mr. Flamsteed, are 1D.18H.28 foot 36 inch 3D.13H.17 54, 7D.3H.59 36, 16D.18H.5 13, as above. And the distances thence computed are 5,578, 8,878, 14,168, 24,968, accurately agreeing with the distances by observation. Cassini assures us, p. 388, 389, that the same proportion is observed in the circumsaturnal planets. But a longer course of observations is required before we can have a certain and accurate theory of those planets. In the circumsolar planets, Mercury and Venus, the same proportion holds with great accuracy, according to the dimensions of their orbs, as determined by the observations of the best astronomers. That Mars is revolved about the Sun is demonstrated from the phases which it shews, and the proportion of its apparent diameters, page 388, 389, and 390. For from its appearing full near conjunction with the Sun, and gibbous in its quadratures, it is certain that it surrounds the Sun. And since its diameter appears about 5 times greater when in opposition to the Sun than when in conjunction therewith, and its distance from the Earth is reciprocally as its apparent diameter, that distance will be about 5 times less when in opposition to than when in conjunction with the Sun. But in both cases its distance from the Sun will be nearly about the same with the distance which is inferred from its gibbous appearance in the quadratures. And as it encompasses the Sun at almost equal distances, but in respect of the Earth is very unequally distant, so by radii drawn to the Sun it describes areas nearly uniform. But by radii drawn to the Earth, it is sometimes swift, sometimes stationary, and sometimes retrograde. That Jupiter, in a higher orb than Mars, is likewise revolved about the Sun, with a motion nearly equable, as well in distance as in the areas described, I infer thus. Mr. Flamsteed assured me, by letters, that all the eclipses of the innermost satellite which hitherto have been well observed do agree with his theory so nearly, as never to differ therefrom by 2 minutes of time. That in the outmost the error is little greater, in the outmost but 1, scarcely 3 times greater. That in the innermost but 1 the difference is indeed much greater, yet so as to agree as nearly with his computations as the moon does with the common tables. And that he computes those eclipses only from the mean motions corrected by the equation of light discovered and introduced by Mr. Romer. Supposing, then, that the theory differs by a less error than that of 2 from the motion of the outmost satellite as hitherto described, and taking as the periodic time 16d. 18h. 5 feet 13 inches to 2 in time, so is the whole circle or 360 degrees to the arc 1 foot 48 inches, the error of Mr. Flamsteed's computation, reduced to the satellite's orbit, will be less than 1 foot 48 inches. That is, the longitude of the satellite, as seen from the center of Jupiter, will be determined with a less error than 1 foot 48 inches. But when the satellite is in the middle of the shadow, that longitude is the same with the heliocentric longitude of Jupiter, and, therefore, the hypothesis which Mr. Flamsteed follows, viz. the Copernican, as improved by Kepler, and, as to the motion of Jupiter, lately corrected by himself, rightly represents that longitude within a less error than 1 foot 48 inches. But by this longitude, together with the geocentric longitude, which is always easily found, the distance of Jupiter from the Sun is determined, which must, therefore, be the very same with that which the hypothesis exhibits. For that greatest error of 1 foot 48 inches that can happen in the heliocentric longitude is almost insensible, and quite to be neglected, and perhaps may arise from some yet undiscovered eccentricity of the satellite. But since both longitude and distance are rightly determined, it follows of necessity that Jupiter, by radii drawn to the Sun, describes areas so conditioned as the hypothesis requires, that is, proportional to the times. And the same thing may be concluded of Saturn from his satellite, by the observations of Mr. Huygens and Dr. Halley, though a longer series of observations is yet wanting to confirm the thing, and to bring it under a sufficiently exact computation. For if Jupiter was viewed from the Sun, it would never appear retrograde nor stationary, as it is seen sometimes from the Earth, but always to go forward with a motion nearly uniform, page 389. And from the very great inequality of its apparent geocentric motion, we infer, by Prop. 3 Cor 4, that the force by which Jupiter is turned out of a rectilinear course, and made to revolve in an orb, is not directed to the center of the Earth. And the same argument holds good in Mars and in Saturn. Another center of these forces is therefore to be looked for, by Prop. 2 and 3, and the corollaries of the latter, about which the areas described by radii intervening may be equable. And that this is the Sun, we have proved already in Mars and Saturn nearly, but accurately enough in Jupiter. It may be all-edged that the Sun and planets are impelled by some other force equally and in the direction of parallel lines. But by such a force, by Cor 6 of the laws of motion, no change would happen in the situation of the planets one to another, nor any sensible effect follow, but our business is with the causes of sensible effects. Let us, therefore, neglect every such force as imaginary and precarious, and of no use in the phenomena of the heavens, and the whole remaining force by which Jupiter is impelled will be directed, by Prop. 3, Cor. 1, to the center of the Sun. The distances of the planets from the Sun come out the same, whether, with Tycho, we place the Earth in the center of the system, or the Sun with Copernicus, and we have already proved that these distances are true in Jupiter. Kepler and Boole-Aldus have, with great care, page 388, determined the distances of the planets from the Sun, and hence it is that their tables agree best with the heavens. And in all the planets, in Jupiter and Mars, in Saturn and the Earth, as well as in Venus and Mercury, the cubes of their distances are as the squares of their periodic times, and therefore, by Cor 6, Prop. 4, the centripetal circumsolar force throughout all the planetary regions decreases in the duplicate proportion of the distances from the Sun. In examining this proportion, we are to use the mean distances, or the transverse semi-axes of the orbits, by Prop. 15, and to neglect those little fractions, which, in defining the orbits, may have arisen from the insensible errors of observation, or may be ascribed to other causes which we shall afterwards explain. And thus we shall always find the said proportion to hold exactly. For the distances of Saturn, Jupiter, Mars, the Earth, Venus, and Mercury, from the Sun, drawn from the observations of astronomers, are, according to the computation of Kepler, as the numbers 95100, 519650, 152350, 100000, 72400, 38,806. By the computation of Boole-Aldus, as the numbers 954193, 522520, 152350, 100000, 72398, 38585, and from the periodic times they come out 953806, 520116, 152399, 100000, 72333, 38710. Their distances, according to Kepler and Boole-Aldus, scarcely differ by any sensible quantity, and where they differ most the distances drawn from the periodic times, fall in between them. That the circumterrestrial force likewise decreases in the duplicate proportion of the distances, I infer thus. The mean distance of the Moon from the center of the Earth, is, in semi-diameters of the Earth, according to Ptolemy, Kepler in his Ephemerides, Boole-Aldus, Hevelius, and Ricciolus, 59, according to Flamsteed, 59 1/3, according to Tycho, 56 1/2. To Vendelin, 60, to Copernicus, 60 1/3, to Kircher, 62 1/2, p. 391, 392, 393. But Tycho, and all that follow his tables of refraction, making the refractions of the sun and moon, altogether against the nature of light, to exceed those of the fixed stars, and that by about 4 or 5 minutes in the horizon, did thereby augment the horizontal parallax of the moon by about the like number of minutes. That is, by about the 12th or 15th part of the whole parallax. Correct this error, and the distance will become 60 or 61 semi-diameters of the Earth, nearly agreeing with what others have determined. Let us, then, assume the mean distance of the Moon 60 semi-diameters of the Earth, and its periodic time in respect of the fixed stars 27d.7 h.43 foot, as astronomers have determined it. And, by course 6, Prop. 4, a body revolved in our air, near the surface of the Earth supposed at rest. By means of a centripetal force which should be to the same force at the distance of the Moon in the reciprocal duplicate proportion of the distances from the center of the Earth, that is, as 3,600 to 1. Would, secluding the resistance of the air, complete a revolution in 1 h. 24 feet 27 inches. Suppose the circumference of the Earth to be 123249600 Paris feet, as has been determined by the late mensuration of the French, vide page 406. Then the same body, deprived of its circular motion, and falling by the impulse of the same centripetal force as before, would, in 1 second of time, describe 151/12 Paris feet. This we infer by a calculus formed upon Prop. XXXVI, and it agrees with what we observe in all bodies about the Earth. For by the experiments of pendulums, and a computation raised thereon, Mr. Huygens has demonstrated that bodies falling by all that centripetal force with which, of whatever nature it is, they are impelled near the surface of the Earth, do, in 1 second of time, describe 151/12 Paris feet. But if the Earth is supposed to move, the Earth and Moon together, by core 4 of the laws of motion, and Prop. LV, will be revolved about their common center of gravity. And the Moon, by Prop. LX, will in the same periodic time, 27d.7 h. 43 foot, with the same circumterrestrial force diminished in the duplicate proportion of the distance, describe an orbit whose semi-diameter is to the semi-diameter of the former orbit, that is, to 60 semi-diameters of the Earth. As the sum of both the bodies of the Earth and Moon to the first of 2 mean proportionals between this sum and the body of the Earth. That is, if we suppose the Moon, on account of its mean apparent diameter 31 1/2, to be about 1/42 of the Earth, as 43 to, or as about 128 to 127. And therefore the semi-diameter of the orbit, that is, the distance between the centers of the Moon and Earth, will in this case be 60 1/2 semi-diameters of the Earth, almost the same with that assigned by Copernicus. Which the Tychonic observations by no means disprove. And, therefore, the duplicate proportion of the decrement of the force holds good in this distance. I have neglected the increment of the orbit which arises from the action of the Sun as inconsiderable. But if that is subducted, the true distance will remain about 604/9 semi-diameters of the Earth. But farther, page 390. This proportion of the decrement of the forces is confirmed from the eccentricity of the planets, and the very slow motion of their apses, for, by the corollaries of Prop. XLV, in no other proportion could the circumsolar planets once in every revolution descend to their least and once ascend to their greatest distance from the Sun, and the places of those distances remain immovable. A small error from the duplicate proportion would produce a motion of the apses considerable in every revolution, but in many enormous. But now, after innumerable revolutions, hardly any such motion has been perceived in the orbs of the circumsolar planets. Some astronomers affirm that there is no such motion. Others reckon it no greater than what may easily arise from the causes hereafter to be assigned, and is of no moment in the present question. We may even neglect the motion of the Moon's apsis, p. 391, which is far greater than in the circumsolar planets, amounting in every revolution to 3 degrees. And from this motion it is demonstrable that the circumterrestrial force decreases in no less than the duplicate, but far less than the triplicate proportion of the distance. For if the duplicate proportion was gradually changed into the triplicate, the motion of the apsis would thereby increase to infinity, and, therefore, by a very small mutation, would exceed the motion of the Moon's apsis. This slow motion arises from the action of the circumsolar force, as we shall afterwards explain. But, secluding this cause, the apsis or apogee of the Moon will be fixed, and the duplicate proportion of the decrease of the circumterrestrial force in different distances from the Earth will accurately take place. Now that this proportion has been established, we may compare the forces of the several planets among themselves, page 391. In the mean distance of Jupiter from the Earth, the greatest elongation of the outmost satellite from Jupiter's center, by the observations of Mr. Flamsteed, is 8 feet 13 inches. And therefore the distance of the satellite from the center of Jupiter is to the mean distance of Jupiter from the center of the Sun as 124 to 52012, but to the mean distance of Venus from the center of the Sun as 124 to 7234. And their periodic times are 16 3/4 d. and 224 2/3 d, and from hence, according to Core 2, Prop. 4, dividing the distances by the squares of the times, we infer that the force by which the satellite is impelled towards Jupiter is to the force by which Venus is impelled towards the Sun as 442 to 143. And if we diminish the force by which the satellite is impelled in the duplicate proportion of the distance 124 to 7234, we shall have the circumjovial force in the distance of Venus from the Sun to the circumsolar force by which Venus is impelled as 13/100 to 143, or as 1 to 1100. Wherefore at equal distances the circumsolar force is 1100 times greater than the circumjovial. And, by the like computation, from the periodic time of the satellite of Saturn 15d.22h, and its greatest elongation from Saturn, while that planet is in its mean distance from us, 3 feet 20 inches, it follows that the distance of this satellite from Saturn's center is to the distance of Venus from the Sun as 922/5 to 7234. And from thence that the absolute circumsolar force is 2360 times greater than the absolute circumsaturnal. From the regularity of the heliocentric and irregularity of the geocentric motions of Venus, of Jupiter, and the other planets, it is evident, by Core 4, Prop. 3, that the circumterrestrial force, compared with the circumsolar, is very small. Ricciolus and Vendelin have severally tried to determine the Sun's parallax from the Moon's dichotomies observed by the telescope, and they agree that it does not exceed half a minute. Kepler, from Tycho's observations and his own, found the parallax of Mars insensible, even in opposition to the Sun, when that parallax is something greater than the Sun's. Flamsteed attempted the same parallax with the micrometer in the perigin position of Mars, but never found it above 25 inch, and thence concluded the Sun's parallax at most 10. Whence it follows that the distance of the Moon from the Earth bears no greater proportion to the distance of the Earth from the Sun than 29 to 10000, nor to the distance of Venus from the Sun than 29 to 7233. From which distances, together with the periodic times, by the method above explained, it is easy to infer that the absolute circumsolar force is greater than the absolute circumterrestrial force at least 229,400 times. And though we were only certain, from the observations of Ricciolus and Vendelin, that the Sun's parallax was less than half a minute, Yet from this it will follow that the absolute circumsolar force exceeds the absolute circumterrestrial force 8,500 times. By the like computations I happen to discover an analogy, that is observed between the forces and the bodies of the planets. But, before I explain this analogy, the apparent diameters of the planets in their mean distances from the Earth must be first determined. Mr. Flamsteed, page 387, by the micrometer, measured the diameter of Jupiter 40 inch or 41. The diameter of Saturn's ring 50 inch, and the diameter of the Sun about 32 feet 13 inches, page 387. But the diameter of Saturn is to the diameter of the ring, according to Mr. Huygens and Dr. Halley, as 4 to 9, according to Gelasius, as 4 to 10. And according to Hooke, by a telescope of 60 feet, as 5 to 12. And from the mean proportion, 5 to 12, the diameter of Saturn's body is inferred about 21 inch. Such as we have said are the apparent magnitudes. But, because of the unequal refrangibility of light, all lucid points are dilated by the telescope, and in the focus of the object glass possess a circular space whose breadth is about the 50th part of the aperture of the glass. It is true, that towards the circumference the light is so rare as hardly to move the sense. But towards the middle, where it is of greater density, and is sensible enough, it makes a small lucid circle, whose breadth varies according to the splendor of the lucid point, but is generally about the 3d, or fourth, or fifth part of the breadth of the whole. Let ABD represent the circle of the whole light, PQ the small circle of the denser and clearer light, C the center of both, CA, CB, semidiameters of the greater circle containing a right angle at C. ACBE the square comprehended under these semidiameters, AB the diagonal of that square. EGH and hyperbola with the center C and asymptote CA, CB, PG a perpendicular erected from any point P of the line BC, and meeting the hyperbola in G, and the right lines AB, AE, in K and F, and the density of the light in any place P, will, by my computation, be as the line FG, and therefore at the center infinite, but near the circumference very small. And the whole light within the small circle PQ is to the without as the area of the quadrilateral figure CAKP to the triangle PKB. And we are to understand the small circle PQ to be there terminated, where FG, the density of the light, begins to be less than what is required to move the sense. Hence it was, that, at the distance of 191,382 feet, a fire of 3 feet in diameter, through a telescope of 3 feet, appeared to Mr. Pickard of 8 inch in breadth, when it should have appeared only of 3/14. And hence it is that the brighter fixed stars appear through the telescope as of 5 inch or 6, in diameter, and that with a good full light, but with a fainter light they appear to run out to a greater breadth. Hence, likewise, it was that Hevelius, by diminishing the aperture of the telescope, did cut off a great part of the light towards the circumference, and brought the disk of the star to be more distinctly defined, which, though hereby diminished, did yet appear as of 5 inch or 6, in diameter. But Mr. Huygens, only by clouding the eyeglass with a little smoke, did so effectually extinguish this scattered light, that the fixed stars appeared as mere points, void of all sensible breadth. Hence also it was that Mr. Huygens, from the breadth of bodies interposed to intercept the whole light of the planets, reckoned their diameters greater than others have measured them by the micrometer. For the scattered light, which could not be seen before for the stronger light of the planet, when the planet is hid, appears every way farther spread. Lastly, from hence it is that the planets appear so small in the disk of the sun, being lessened by the dilated light. For to Hevelius, Gelasius, and Dr. Halley, Mercury did not seem to exceed 12 inch or 15, and Venus appeared to Mr. Crabtree only 1 foot 3 inches, to Horrocks but 1 foot 12 inches, though by the mensurations of Hevelius and Hugenius without the sun's disk, it ought to have been seen at least 1 foot 24 inches. Thus the apparent diameter of the moon, which in 1684, a few days both before and after the sun's eclipse, was measured at the observatory of Paris 31 feet 30 inches, in the eclipse itself did not seem to exceed 30 or 30 feet 5 inches. And therefore the diameters of the planets are to be diminished when without the Sun, and to be augmented when within it, by some seconds. But the errors seem to be less than usual in the mensurations that are made by the micrometer. So from the diameter of the shadow, determined by the eclipses of the satellites, Mr. Flamsteed found that the semi-diameter of Jupiter was to the greatest elongation of the outmost satellite as 1 to 24,903. Wherefore since that elongation is 8 feet 13 inches, the diameter of Jupiter will be 39.5, and, rejecting the scattered light, the diameter found by the micrometer 40 or 41 will be reduced to 39.5. And the diameter of Saturn 21 inches to be diminished by the light correction, and to be reckoned 20 or something less. But, if I am not mistaken, the diameter of the Sun, because of its stronger light, is to be diminished something more, and to be reckoned about 32 foot, or 32 feet 6 inches. That bodies so different in magnitude should come so near to an analogy with their forces, is not without some mystery, page 400. It may be that the remoter planets, for want of heat, have not those metallic substances and ponderous minerals with which our Earth abounds. And that the bodies of Venus and Mercury, as they are more exposed to the Sun's heat, are also harder baked, and more compact. For, from the experiment of the burning glass, we see that the heat increases with the density of light. And this density increases in the reciprocal duplicate proportion of the distance from the Sun, from whence the Sun's heat in Mercury is proved to be sevenfold its heat in our summer seasons. But with this heat our water boils. And those heavy fluids, quicksilver and the spirit of vitriol, gently evaporate, as I have tried by the thermometer. And therefore there can be no fluids in Mercury but what are heavy, and able to bear a great heat, and from which substances of great density may be nourished. And why not, if God has placed different bodies at different distances from the Sun, so as the denser bodies always possess the nearer places, and each body enjoys a degree of heat suitable to its condition, and proper for its nourishment? From this consideration it will best appear that the weights of all the planets are one to another as their forces. But I should be glad the diameters of the planets were more accurately measured. And that may be done, if a lamp, set at a great distance, is made to shine through a circular hole, and both the hole and the light of the lamp are so diminished that the spectrum may appear through the telescope just like the planet, and may be defined by the same measure. Then the diameter of the hole will be to its distance from the objective glass as the true diameter of the planet to its distance from us. The light of the lamp may be diminished by the interposition either of pieces of cloth, or of smoked glass. Of kin to the analogy we have been describing, there is another observed between the forces and the bodies attracted, page 395, 396, 397. Since the action of the centripetal force upon the planets decreases in the duplicate proportion of the distance, and the periodic time increases in the sesquiplicate thereof, it is evident that the actions of the centripetal force, and therefore the periodic times, would be equal in equal planets at equal distances from the Sun. And in equal distances of unequal planets the total actions of the centripetal force would be as the bodies of the planets. For if the actions were not proportional to the bodies to be moved, they could not equally retract these bodies from the tangents of their orbs in equal times, nor could the motions of the satellites of Jupiter be so regular. If it was not that the circumsolar force was equally exerted upon Jupiter and all its satellites in proportion of their several weights. And the same thing is to be said of Saturn in respect of its satellites, and of our Earth in respect of the Moon, as appears from Core 2 and 3, Prop. LXV. And, therefore, at equal distances, the actions of the centripetal force are equal upon all the planets in proportion of their bodies, or of the quantities of matter in their several bodies. And for the same reason must be the same upon all the particles of the same size of which the planet is composed. For if the action was greater upon some sort of particles than upon others than in proportion to their quantity of matter, it would be also greater or less upon the whole planets not in proportion to the quantity only, but likewise of the sort of the matter more copiously found in one and more sparingly in another. In such bodies as are found on our Earth of very different sorts, I examined this analogy with great accuracy, page 343, 344. If the action of the circumterrestrial force is proportional to the bodies to be moved, it will, by the second law of motion, move them with equal velocity in equal times. And will make all bodies let fall to descend through equal spaces in equal times, and all bodies hung by equal threads to vibrate in equal times. If the action of the force was greater, the times would be less; if that was less, these would be greater. But it has been long ago observed by others, that, allowance being made for the small resistance of the air, all bodies descend through equal spaces in equal times. And, by the help of pendulums, that equality of times may be distinguished to great exactness. I tried the thing in gold, silver, lead, glass, sand, common salt, wood, water, and wheat. I provided 2 equal wooden boxes. I filled the one with wood, and suspended an equal weight of gold, as exactly as I could, in the center of oscillation of the other. The boxes, hung by equal threads of 11 feet, made a couple of pendulums perfectly equal in weight and figure, and equally exposed to the resistance of the air, and, placing the one by the other, I observed them to play together forwards and backwards for a long while, with equal vibrations. And therefore, by Core 1 and 6, Prop. Ziv, Book 2, the quantity of matter in the gold was to the quantity of matter in the wood as the action of the motive force upon all the gold to the action of the same upon all the wood. That is, as the weight of the one to the weight of the other. And by these experiments, in bodies of the same weight, could have discovered a difference of matter less than the 1,000th part of the whole. Since the action of the centripetal force upon the bodies attracted is, at equal distances, proportional to the quantities of matter in those bodies. Reason requires that it should be also proportional to the quantity of matter in the body attracting. For all action is mutual, and, page 83, 93, by the third law of motion, makes the bodies mutually to approach one to the other, and therefore must be the same in both bodies. It is true that we may consider one body as attracting, another as attracted, but this distinction is more mathematical than natural. The attraction is really common of either to other, and therefore of the same kind in both. And hence it is that the attractive force is found in both. The Sun attracts Jupiter and the other planets, Jupiter attracts its satellites. And, for the same reason, the satellites act as well one upon another as upon Jupiter, and all the planets mutually one upon another. And though the mutual actions of 2 planets may be distinguished and considered as 2, by which each attracts the other, yet, as those actions are intermediate, they do not make 2 but 1 operation between 2 terms. 2 bodies may be mutually attracted each to the other by the contraction of a cord interposed. There is a double cause of action, to wit, the disposition of both bodies, as well as a double action in so far as the action is considered as upon 2 bodies, but as betwixt 2 bodies it is but one single one. It is not one action by which the Sun attracts Jupiter, and another by which Jupiter attracts the Sun, but it is one action by which the Sun and Jupiter mutually endeavor to approach each the other. By the action with which the Sun attracts Jupiter, Jupiter and the Sun endeavors to come nearer together, by the third law of motion. And by the action with which Jupiter attracts the Sun, likewise Jupiter and the Sun endeavor to come nearer together. But the Sun is not attracted towards Jupiter by a twofold action, nor Jupiter by a twofold action towards the Sun. But it is one single intermediate action, by which both approach nearer together. Thus iron draws the lodestone, page 93, as well as the lodestone draws the iron, for all iron in the neighborhood of the lodestone draws other iron. But the action betwixt the lodestone and iron is single, and is considered as single by the philosophers. The action of iron upon the lodestone is, indeed, the action of the lodestone betwixt itself and the iron, by which both endeavor to come nearer together, and so it manifestly appears. For if you remove the lodestone, the whole force of the iron almost ceases. In this sense it is that we are to conceive one single action to be exerted betwixt 2 planets, arising from the conspiring natures of both, and this action standing in the same relation to both. If it is proportional to the quantity of matter in the one, it will be also proportional to the quantity of matter in the other. Perhaps it may be objected, that, according to this philosophy, page 398, all bodies should mutually attract one another, contrary to the evidence of experiments in terrestrial bodies. But I answer, that the experiments in terrestrial bodies come to no account, for the attraction of homogeneous spheres near their surfaces are, by Prop. LXXI, as their diameters. Whence a sphere of 1 foot in diameter, and of a like nature to the earth, would attract a small body placed near its surface with a force 20 million times less than the earth would do if placed near its surface. But so small a force could produce no sensible effect. If two such spheres were distant but by of an inch, they would not, even in spaces void of resistance, come together by the force of their mutual attraction in less than a month's time. And less spheres will come together at a rate yet slower, viz., in the proportion of their diameters. Nay, whole mountains will not be sufficient to produce any sensible effect. A mountain of an hemispherical figure, 3 miles high, and 6 broad, will not, by its attraction, draw the pendulum 2 minutes out of the true perpendicular. And it is only in the great bodies of the planets that these forces are to be perceived, unless we may reason about smaller bodies in manner following. Let ABCD, p. 93, represent the globe of the earth cut by any plane AC into two parts ACB and ACD. The part ACB bearing upon the part ACD presses it with its whole weight. Nor can the part ACD sustain this pressure and continue unmoved, if it is not opposed by an equal contrary pressure. And therefore the parts equally press each other by their weights, that is, equally attract each other, according to the third law of motion, and, if separated and let go, would fall towards each other with velocities reciprocally as the bodies. All which we may try and see in the lodestone, whose attracted part does not propel the part attracting, but is only stopped and sustained thereby. Suppose now that ACB represents some small body on the earth's surface. Then, because the mutual attractions of this particle, and of the remaining part ACD of the earth towards each other, are equal. But the attraction of the particle towards the earth, or its weight, is as the matter of the particle, as we have proved by the experiment of the pendulums. The attraction of the earth towards the particle will likewise be as the matter of the particle. And therefore the attractive forces of all terrestrial bodies will be as their several quantities of matter. The forces, p. 396, which are as the matter in terrestrial bodies of all forms, and therefore are not mutable with the forms, must be found in all sorts of bodies whatsoever, celestial as well as terrestrial. And be in all proportional to their quantities of matter, because among all there is no difference of substance, but of modes and forms only. But in the celestial bodies the same thing is likewise proved thus. We have shown that the action of the circumsolar force upon all the planets, reduced to equal distances, is as the matter of the planets. That the action of the circumjovial force upon the satellites of Jupiter observes the same law, and the same thing is to be said of the attraction of all the planets towards every planet, but thence it follows, by Prop. LXAX, that their attractive forces are as their several quantities of matter. As the parts of the earth mutually attract one another, so do those of all the planets. If Jupiter and its satellites were brought together, and formed into one globe, without doubt they would continue mutually to attract one another as before. And, on the other hand, if the body of Jupiter was broke into more globes, to be sure, these would no less attract one another than they do the satellites now. From these attractions it is that the bodies of the earth and all the planets affect a spherical figure, and their parts cohere, and are not dispersed through the ether. But we have before proved that these forces arise from the universal nature of matter, page 398, and that, therefore, the force of any whole globe is made up of the several forces of all its parts. And from thence it follows, by Core 3, Prop. LXXIV, that the force of every particle decreases in the duplicate proportion of the distance from that particle, and, by Prop. LXXII and LXXV, that the force of an entire globe, reckoning from the surface outwards, decreases in the duplicate, but, reckoning inwards, in the simple proportion of the distances from the centers, if the matter of the globe be uniform. And though the matter of the globe, reckoning from the center towards the surface, is not uniform, page 398, 399, yet the decrease in the duplicate proportion of the distance outwards would, by Prop. LXXVA, take place, provided that deformity is similar in places round about at equal distances from the center. And two such globes will, by the same proposition, attract one the other with a force decreasing in the duplicate proportion of the distance between their centers. Wherefore the absolute force of every globe is as the quantity of matter which the globe contains. But the motive force by which every globe is attracted towards another, and which, in terrestrial bodies, we commonly call their weight, is as the content under the quantities of matter in both globes applied to the square of the distance between their centers, by Cr. 4. Prop. LXXVI, to which force the quantity of motion, by which each globe in a given time will be carried towards the other, is proportional. And the accelerative force, by which every globe according to its quantity of matter is attracted towards another, is as the quantity of matter in that other globe applied to the square of the distance between the centers of the two, by Cr. 2. Prop. LXXVI, to which force, the velocity by which the attracted globe will, in a given time, be carried towards the other is proportional. And from these principles well understood, it will be now easy to determine the motions of the celestial bodies among themselves. From comparing the forces of the planets one with another, we have above seen that the circumsolar does more than 1,000 times exceed all the rest. But by the action of a force so great it is unavoidable but that all bodies within, nay, and far beyond, the bounds of the planetary system must descend directly to the sun. Unless by other motions they are impelled towards other parts, nor is our earth to be excluded from the number of such bodies. For certainly the moon is a body of the same nature with the planets, and subject to the same attractions with the other planets, seeing it is by the circumterrestrial force that it is retained in its orbit. But that the earth and moon are equally attracted towards the sun, we have above proved. We have likewise before proved that all bodies are subject to the said common laws of attraction. Nay, supposing any of those bodies to be deprived of its circular motion about the sun, by having its distance from the sun, we may find, by Prop. XXXVA, in what space of time it would in its descent arrive at the sun. To wit, in half that periodic time in which the body might be revolved at 1/2 of its former distance, or in a space of time that is to the periodic time of the planet as 1:4. As that Venus in its descent would arrive at the sun in the space of 40 days, Jupiter in the space of 2 years and 1 month, and the earth and moon together in the space of 66 days and 19 hours. But, since no such thing happens, it must needs be, that those bodies are moved towards other parts, page 75, nor is every motion sufficient for this purpose. To hinder such a descent, a due proportion of velocity is required. And hence depends the force of the argument drawn from the retardation of the motions of the planets. Unless the circumsolar force decreased in the duplicate ratio of their increasing slowness, the excess thereof would force those bodies to descend to the sun. For instance, if the motion, caeteris paribus, was retarded by 1/2, the planet would be retained in its orb by 1/4 of the former circumsolar force, and by the excess of the other 3/4 would descend to the sun. And therefore the planets, Saturn, Jupiter, Mars, Venus, and Mercury, are not really retarded in their perigees, nor become really stationary, or regressive with slow motions. All these are but apparent, and the absolute motions, by which the planets continue to revolve in their orbits, are always direct, and nearly equable. But that such motions are performed about the sun, we have already proved. And therefore the sun, as the center of the absolute motions, is quiescent. For we can by no means allow quiescence to the earth, lest the planets in their perigees should indeed be truly retarded, and become truly stationary and regressive, and so for want of motion should descend to the sun. But farther. Since the planets, Venus, Mars, Jupiter, and the rest, by radii drawn to the sun describe regular orbits, and areas, as we have shown, nearly and to sense proportional to the times, it follows, by Prop. 3 and Core 3, Prop. LXV, that the sun is moved with no notable force, unless perhaps with such as all the planets are equally moved with, according to their several quantities of matter, in parallel lines, and so the whole system is transferred in right lines. Reject that translation of the whole system, and the sun will be almost quiescent in the center thereof. If the sun was revolved about the earth, and carried the other planets round about itself, the earth ought to attract the sun with a great force, but the circumsolar planets with no force producing any sensible effect, which is contrary to Cr. 3. Prop. LXV. Add to this, that if hitherto the earth, because of the gravitation of its parts, has been placed by most authors in the lowermost region of the universe. Now, for better reason, the sun possessed of a centripetal force exceeding our terrestrial gravitation 1,000 times and more, ought to be depressed into the lowermost place, and to be held for the center of the system. And thus the true disposition of the whole system will be more fully and more exactly understood. Because the fixed stars are quiescent one in respect of another, p. 401, 402, we may consider the sun, earth, and planets, as one system of bodies carried hither and thither by various motions among themselves, and the common center of gravity of all, by Cr. 4 of the laws of motion, will either be quiescent, or move uniformly forward in a right line, in which case the whole system will likewise move uniformly forward in right lines. But this is an hypothesis hardly to be admitted. And, therefore, setting it aside, that common center will be quiescent, and from it the sun is never far removed. The common center of gravity of the sun and Jupiter falls on the surface of the sun. And though all the planets were placed towards the same parts from the sun with Jupiter the common center of the sun, and all of them would scarcely recede twice as far from the sun's center. And, therefore, though the sun, according to the various situation of the planets, is variously agitated, and always wandering to and fro with a slow motion of libration, yet it never recedes one entire diameter of its own body from the quiescent center of the whole system. But from the weights of the sun and planets above determined, and the situation of all among themselves, their common center of gravity may be found, and, this being given, the sun's place to any supposed time may be obtained. About the sun thus liberated the other planets are revolved in elliptic orbits, p403, and, by radii drawn to the sun, describe areas nearly proportional to the times, as is explained in Prop. LXV. If the sun was quiescent, and the other planets did not act mutually one upon another, their orbits would be elliptic, and the areas exactly proportional to the times, by Prop. 11, and Core 1, Prop. 13. But the actions of the planets among themselves, compared with the actions of the sun on the planets, are of no moment, and produce no sensible errors. And those errors are less in revolutions about the sun agitated in the manner but now described than if those revolutions were made about the sun quiescent, by Prop. LXV, and Core Prop. LXVAI, especially if the focus of every orbit is placed in the common center of gravity of all the lower included planets, viz., the focus of the orbit of Mercury in the center of the sun. The focus of the orbit of Venus in the common center of gravity of Mercury in the sun, the focus of the orbit of the Earth in the common center of gravity of Venus, Mercury, and the Sun, and so of the rest. And by this means the foci of the orbits of all the planets, except Saturn, will not be sensibly removed from the center of the Sun, nor will the focus of the orbit of Saturn recede sensibly from the common center of gravity of Jupiter and the Sun. And therefore astronomers are not far from the truth, when they reckon the Sun's center the common focus of all the planetary orbits. In Saturn itself the error thence arising does not exceed 1 foot 45 inches. And if its orbit, by placing the focus thereof in the common center of gravity of Jupiter and the Sun, shall happen to agree better with the phenomena, from thence all that we have said will be farther confirmed. If the Sun was quiescent, and the planets did not act one on another, the aphelions and nodes of their orbits would likewise, by Prop. 1, 11, and Core Prop. 13, be quiescent. And the longer axes of their elliptic orbits would, by Prop. 15, be as the cubic roots of the squares of their periodic times, and therefore from the given periodic times would be also given. But those times are to be measured not from the equinoctial points, which are movable, but from the first star of Aries. Put the semi-axis of the Earth's orbit 100000, and the semi-axis of the orbits of Saturn, Jupiter, Mars, Venus, and Mercury, from their periodic times, will come out 953806, 520116, 152399, 72333, 38,710 respectively. But from the Sun's motion every semi-axis is increased, by prop. Lx, by about 1/3 of the distance of the Sun's center from the common center of gravity of the Sun and planet, page 405, 406. And from the actions of the exterior planets on the interior, the periodic times of the interior are something protracted, though scarcely by any sensible quantity, and their aphelions are transferred, by course 6. And 7, prop. Lxv, by very slow motions in consequentia. And on the like account the periodic times of all, especially of the exterior planets, will be prolonged by the actions of the comets, if any such there are, without the orb of Saturn. And the aphelions of all will be thereby carried forwards in consequentia. But from the progress of the aphelions the regress of the nodes follows, by core 11, 13, prop. Lxvi, and if the plane of the ecliptic is quiescent, the regress of the nodes, by core 16, prop. Lxv, will be to the progress of the aphelion in every orbit as the regress of the nodes of the Moon's orbit to the progress of its apogee nearly, that is, as about 10 to 21. But astronomical observations seem to confirm a very slow progress of the aphelions, and a regress of the nodes in respect of the fixed stars. And hence it is probable that there are comets in the regions beyond the planets, which, revolving in very eccentric orbs, quickly fly through their perihelion parts, and, by an exceedingly slow motion in their aphelions, spend almost their whole time in the regions beyond the planets. As we shall afterwards explain more at large. The planets thus revolved about the Sun, page 413, 414, 415, may at the same time carry others revolving about themselves as satellites or moons, as appears by prop. 66. But from the action of the Sun our Moon must move with greater velocity, and, by a radius drawn to the Earth, describe an area greater for the time. It must have its orbit less curve, and therefore approach nearer to the Earth in the syzygies than in the quadratures, except in so far as the motion of eccentricity hinders those effects. For the eccentricity is greatest when the Moon's apogee is in the syzygies, and least when the same is in the quadratures. And hence it is that the perigee Moon is swifter and nearer to us, but the apogee Moon slower and farther from us, in the syzygies than in the quadratures. But farther. The apogee has a progressive and the nodes a regressive motion, both unequable. For the apogee is more swiftly progressive in its syzygies, more slowly regressive in its quadratures, and by the excess of its progress above its regress is yearly transferred in consequentia. But the nodes are quiescent in their syzygies, and most swiftly regressive in their quadratures. But farther, still, the greatest latitude of the Moon is greater in its quadratures than in its syzygies. And the mean motion swifter in the aphelion of the Earth than in its perihelion. More inequalities in the Moon's motion have not hitherto been taken notice of by astronomers, but all these follow from our principles in Cr. 2, 3, 4, v, 6, 7, 8, 9, x, 11, 12, 13, prop. Lxvi, and are known really to exist in the heavens. And this may seen in that most ingenious, and if I mistake not, of all, the most accurate, hypothesis of Mr. Horrocks, which Mr. Flamsteed has fitted to the heavens, but the astronomical hypotheses are to be corrected in the motion of the nodes. For the nodes admit the greatest equation or prostaphoresis in their octants, and this inequality is most conspicuous when the Moon is in the nodes, and therefore also in the octants. And hence it was that Tycho, and others after him, referred this inequality to the octants of the Moon, and made it menstrual, but the reasons by us adduced prove that it ought to be referred to the octants of the nodes, and to be made annual. Beside those inequalities taken notice of by astronomers, page 414, 445, 447, there are yet some others, by which the moon's motions are so disturbed, that hitherto by no law could they be reduced to any certain regulation. For the velocities or horary motions of the apogee and nodes of the moon, and their equations, as well as the difference betwixt the greatest eccentricity in the syzygies and the least in the quadratures. And that inequality which we call the variation, in the progress of the year are augmented and diminished, by Cr. 14, prop. LXV, in the triplicate ratio of the sun's apparent diameter. Beside that, the variation is mutable nearly in the duplicate ratio of the time between the quadratures, by Cor. 1 and 2, Lem. X, and Cor 16, prop. 66. And all those inequalities are something greater in that part of the orbit which respects the sun than in the opposite part, but by a difference that is scarcely or not at all perceptible. By a computation, p. For 22, which for brevity's sake I do not describe, I also find that the area which the moon by a radius drawn to the earth describes in the several equal moments of time is nearly as the sum of the number 237 3 out of 10. And versed sine of the double distance of the moon from the nearest quadrature in a circle whose radius is unity. And therefore that the square of the moon's distance from the earth is as that sum divided by the horary motion of the moon. Thus it is when the variation in the octants is in its mean quantity. But if the variation is greater or less, that versed sine must be augmented or diminished in the same ratio. Let astronomers try how exactly the distances thus found will agree with the moon's apparent diameters. From the motions of our moon we may derive the motions of the moons or satellites of Jupiter and Saturn, page 413. For the mean motion of the nodes of the outmost satellite of Jupiter is to the mean motion of the nodes of our moon in a proportion compounded of the duplicate proportion of the periodic time of the earth about the sun to the periodic time of Jupiter about the sun, and the simple proportion of the periodic time of the satellite about Jupiter to the periodic time of our moon about the earth, by Cr. 16, prop. LXV, and therefore those nodes, in the space of 100 years, are carried 8 degrees 24 minutes backwards, or in antecedentia. The mean motions of the nodes of the inner satellites are to the mean motion of the nodes of the outmost as their periodic times to the periodic time of this, by the same corollary, and are thence given. And the motion of the apsis of every satellite in consequentia is to the motion of its nodes in antecedentia, as the motion of the apogee of our moon to the motion of its nodes, by the same corollary, and is thence given. The greatest equations of the nodes and line of the apses of each satellite are to the greatest equations of the nodes and the line of the apses of the moon respectively as the motion of the nodes and line of the apses of the satellites in the time of one revolution of the first equations to the motion of the nodes and apogee of the moon in the time of one revolution of the last equations. The variation of a satellite seen from Jupiter is to the variation of our moon in the same proportion as the whole motions of their nodes respectively. During the times in which the satellite and our moon, after parting from, are revolved, again, to the sun, by the same corollary. And therefore in the outmost satellite the variation does not exceed 5 inch 12 foot. From the small quantity of those inequalities, and the slowness of the motions, it happens that the motions of the satellites are found to be so regular, that the more modern astronomers either deny all motion to the nodes, or affirm them to be very slowly regressive. p. 404. While the planets are thus revolved in orbits about remote centers, in the meantime they make their several rotations about their proper axes, the Sun in 26 days, Jupiter in 9h.56 foot, Mars in 24 2/3 h, Venus in 23 h. And that in planes not much inclined to the plane of the ecliptic, and according to the order of the signs, as astronomers determine from the spots or maculae that by turns present themselves to our sight in their bodies. And there is a like revolution of our earth performed in 24 h, find those motions are neither accelerated nor retarded by the actions of the centripetal forces, as appears by Cor XXI, prop. 66. And therefore of all others they are the most equable and most fit for the mensuration of time. But those revolutions are to be reckoned equable not from their return to the sun, but to some fixed star, for as the position of the planets to the Sun is unequably varied, the revolutions of those planets from Sun to Sun are rendered unequable. In like manner is the Moon revolved about its axis by a motion most equable in respect of the fixed stars, viz., in 2070.7 h.43 foot, that is, in the space of a sidereal month. So that this diurnal motion is equal to the mean motion of the Moon in its orbit. Upon which account the same face of the Moon always respects the center about which this mean motion is performed, that is, the exterior focus of the Moon's orbit nearly. And hence arises a deflection of the Moon's face from the Earth, sometimes towards the east and other times towards the west, according to the position of the focus which it respects. And this deflection is equal to the equation of the Moon's orbit, or to the difference betwixt its mean and true motions. And this is the Moon's libration in longitude, but it is likewise affected with a libration in latitude arising from the inclination of the Moon's axis to the plane of the orbit in which the Moon is revolved about the Earth. For that axis retains the same position to the fixed stars nearly, and hence the poles present themselves to our view by turns, as we may understand from the example of the motion of the Earth, whose poles, by reason of the inclination of its axis to the plane of the ecliptic, are by turns illuminated by the Sun. To determine exactly the position of the Moon's axis to the fixed stars, and the variation of this position, is a problem worthy of an astronomer. By reason of the diurnal revolutions of the planets, the matter which they contain endeavors to recede from the axis of this motion, and hence the fluid parts rising higher towards the equator than about the poles, p. 405, would lay the solid parts about the equator under water, if those parts did not rise also, page 405, 409 upon which account the planets are something thicker about the equator than about the poles, and their equinoctial points, p. 413, thence become regressive, and their axes, by a motion of nutation, twice in every revolution, librate towards their ecliptics, and twice return again to their former inclination, as is explained in Core 18, Prop. 66. And hence it is that Jupiter, viewed through very long telescopes, does not appear altogether round, page 409, but having its diameter that lies parallel to the ecliptic something longer than that which is drawn from north to south. And from the diurnal motion and the attractions, page 415, 418, of the Sun and Moon our sea ought twice to rise and twice to fall every day, as well lunar as solar, by Core 19, XX, Prop. LXVI, and the greatest height of the water to happen before the 6th hour of either day and after the 12th hour preceding. By the slowness of the diurnal motion the flood is retracted to the 12th hour. And by the force of the motion of reciprocation it is protracted and deferred till a time nearer to the 6th hour. But till that time is more certainly determined by the phenomena, choosing the middle between those extremes, why may we not conjecture the greatest height of the water to happen at the 3rd hour? For thus the water will rise all that time in which the force of the luminaries to raise it is greater, and will fall all that time in which their force is less, viz. from the 9th to the 3rd hour when that force is greater, and from the 3rd to the 9th when it is less. The hours I reckon from the appulse of each luminary to the meridian of the place, as well under as above the horizon. And by the hours of the lunar day I understand the 24th parts of that time which the Moon spends before it comes about again by its apparent diurnal motion to the meridian of the place which it left the day before. But the two motions which the two luminaries raise will not appear distinguished, but will make a certain mixed motion. In the conjunction or opposition of the luminaries their forces will be conjoined, and bring on the greatest flood and ebb. In the quadratures the Sun will raise the waters which the Moon depresseth, and depress the waters which the Moon riseth, and from the difference of their forces the smallest of all tides will follow. And because, as experience tells us, the force of the Moon is greater than that of the Sun, the greatest height of the water will happen about the 3rd lunar hour. Out of the syzygies and quadratures the greatest tide which by the single force of the Moon ought to fall out at the 3rd lunar hour, and by the single force of the Sun at the 3rd solar hour. By the compounded forces of both must fall out in an intermediate time that approaches nearer to the 3rd hour of the Moon than to that of the Sun. And, therefore, while the Moon is passing from the syzygies to the quadratures, during which time the 3rd hour of the Sun precedes the 3rd of the Moon, the greatest tide will precede the 3rd lunar hour. And that by the greatest interval a little after the octants of the moon. And by like intervals the greatest tide will follow the third lunar hour, while the moon is passing from the quadratures to the syzygies. But the effects of the luminaries depend upon their distances from the earth. For when they are less distant their effects are greater, and when more distant their effects are less, and that in the triplicate proportion of their apparent diameters. Therefore it is that the sun in the winter time, being then in its perigee, has a greater effect, and makes the tides in the syzygies something greater, and those in the quadratures something less, caeteris paribus, than in the summer season. And every month the moon while in the perigee, riseth greater tides than at the distance of 15 days before or after, when it is in its apogee. Whence it comes to pass that two highest tides do not follow one the other in two immediately succeeding syzygies. The effect of either luminary doth likewise depend upon its declination or distance from the equator. For if the luminary was placed at the pole, it would constantly attract all the parts of the waters, without any intention or remission of its action, and could cause no reciprocation of motion. And, therefore, as the luminaries decline from the equator towards either pole, they will by degrees lose their force, and on this account will excite lesser tides in the solstitial than in the equinoctial syzygies. But in the solstitial quadratures they will raise greater tides than in the quadratures about the equinoxes, because the effect of the moon, then situated in the equator, most exceeds the effect of the sun. Therefore the greatest tides fall out in those syzygies, and the least in those quadratures, which happen about the time of both equinoxes. And the greatest tide in the syzygies is always succeeded by the least tide in the quadratures, as we find by experience. But because the sun is less distant from the earth in winter than in summer, it comes to pass that the greatest and least tides more frequently appear before than after the vernal equinox, and more frequently after than before the autumnal. Moreover, the effects of the luminaries depend upon the latitudes of places. Let APEP represent the earth on all sides covered with deep waters, C its center, P its poles, AE the equator, F any place without the equator. FF the parallel of the place, DD the correspondent parallel on the other side of the equator, L the place which the moon possessed 3 hours before, H the place of the earth directly under it, H the opposite place. K the places at 90 degrees distance, CH the greatest heights of the sea from the center of the earth, and CK the least heights. And if with the axis HH, KK, an ellipsis is described, and by the revolution of that ellipsis about its longer axis HH a spheroid HPK is formed, this spheroid will nearly represent the figure of the sea. And CF, CD will represent the sea in the places F, D. But farther. If in the said revolution of the ellipsis any point N describes the circle NM, cutting the parallels FF, DD, in any places R, T, and the equator AE and S, CN will represent the height of the sea in all those places R, S, T, situated in this circle. Wherefore in the diurnal revolution of any place F the greatest flood will be in F, at the third hour after the appulse of the moon to the meridian above the horizon. And afterwards the greatest ebb in Q, at the third hour after the setting of the moon. And then the greatest flood in F, at the third hour after the appulse of the moon to the meridian under the horizon, and, lastly, the greatest ebb in Q, at the third hour after the rising of the moon. And the latter flood in F will be less than the preceding flood in F. For the whole sea is divided into two huge and hemispherical floods, one in the hemisphere KHKC on the north side, the other in the opposite hemisphere KHKC. Which we may therefore call the northern and the southern floods, these floods being always opposite the one to the other, come by turns to the meridians of all places after the interval of 12 lunar hours. And, seeing the northern countries partake more of the northern flood, and the southern countries more of the southern flood, thence arise tides alternately greater and less in all places without the equator in which the luminaries rise and set. But the greater tide will happen when the moon declines towards the vertex of the place, about the third hour after the appulse of the moon to the meridian above the horizon. And when the moon changes its declination, that which was the greater tide will be changed into a lesser. And the greatest difference of the floods will fall out about the times of the solstices, especially if the ascending node of the moon is about the 1st of Aries. So the morning tides in winter exceed those of the evening, and the evening tides exceed those of the morning in summer. At Plymouth by the height of 1 foot, but at Bristol by the height of 15 inches, according to the observations of Colepress and Sturmey. But the motions which we have been describing suffer some alteration from that force of reciprocation which the waters, having once received, retain a little while by their vis insita. Whence it comes to pass that the tides may continue for some time, though the actions of the luminaries should cease. This power of retaining the impressed motion lessens the difference of the alternate tides, and makes those tides which immediately succeed after the syzygies greater, and those which follow next after the quadratures less. And hence it is that the alternate tides at Plymouth and Bristol do not differ much more one from the other than by the height of a foot, or of 15 inches. And that the greatest tides of all at those ports are not the first but the third after the syzygies. And, besides, all the motions are retarded in their passage through shallow channels, so that the greatest tides of all, in some straits and mouths of rivers, are the 4th, or even the 5th, after the syzygies. It may also happen that the greatest tide may be the 4th or 5th after the syzygies, or fall out yet later, because the motions of the sea are retarded in passing through shallow places towards the shores. For so the tide arrives at the western coast of Ireland at the 3rd lunar hour, and an hour or two after at the ports in the southern coast of the same island, as also at the islands Cassiterides, commonly Sorlings. Then successively at Falmouth, Plymouth, Portland, the Isle of Wight, Winchester, Dover, the mouth of the Thames, and London Bridge, spending 12 hours in this passage. But farther, the propagation of the tides may be obstructed even by the channels of the ocean itself, when they are not of depth enough, for the flood happens at the 3rd lunar hour in the Canary Islands. And at all those western coasts that lie towards the Atlantic Ocean, as of Ireland, France, Spain, and all Africa, to the Cape of Good Hope, except in some shallow places, where it is impeded, and falls out later. And in the Straits of Gibraltar, where, by reason of a motion propagated from the Mediterranean Sea, it flows sooner. But, passing from those coasts over the breadth of the ocean to the coasts of America, the flood arrives first at the most eastern shores of Brazil, about the 4th or 5th lunar hour. Then at the mouth of the river of the Amazons at the 6th hour, but at the neighboring islands at the 4th hour, afterwards at the islands of Bermudas at the 7th hour, and at Port St. Augustine in Florida at 7½ And therefore the tide is propagated through the ocean with a slower motion than it should be according to the course of the moon. And this retardation is very necessary, that the sea at the same time may fall between Brazil and New France, and rise at the Canary Islands, and on the coasts of Europe and Africa. And vice versa, for the sea cannot rise in one place but by falling in another. And it is probable that the Pacific Sea is agitated by the same laws, for in the coasts of Chile and Peru the highest flood is said to happen at the 3rd lunar hour. But with what velocity it is thence propagated to the eastern coasts of Japan, the Philippine and other islands adjacent to China, I have not yet learned. Farther, it may happen, p. 418, that the tide may be propagated from the ocean through different channels towards the same port, and may pass quicker through some channels than through others, in which case the same tide, divided into 2 or more succeeding one another, may compound new motions of different kinds. Let us suppose one tide to be divided into 2 equal tides, the former whereof precedes the other by the space of 6 hours, and happens at the 3rd or 27th hour from the appulse of the moon to the meridian of the port. If the moon at the time of this appulse to the meridian was in the equator, every 6 hours alternately there would arise equal floods, which, meeting with as many equal ebbs, would so balance one the other, that, for that day, the water would stagnate and remain quiet. If the moon then declined from the equator, the tides in the ocean would be alternately greater and less, as was said, and from hence 2 greater and 2 lesser tides would be alternately propagated towards that port. But the 2 greater floods would make the greatest height of the waters to fall out in the middle time betwixt both, and the greater and lesser floods would make the waters to rise to a mean height in the middle time between them. And in the middle time between the two lesser floods the waters would rise to their least height. Thus in the space of 24 hours the waters would come, riot twice, but once only to their greatest, and once only to their least height. And their greatest height, if the moon declined towards the elevated pole, would happen at the 6th or 30th hour after the appulse of the moon to the meridian, and when the moon changed its declination, this flood would be changed into an ebb. Of all which we have an example in the port of Bat Sham, in the kingdom of Tunkan, in the latitude of 20 degrees 50 minutes north. In that port, on the day which follows after the passage of the moon over the equator, the waters stagnate. When the moon declines to the north, they begin to flow and ebb, not twice, as in other ports, but once only every day, and the flood happens at the setting, and the greatest ebb at the rising of the moon. This tide increaseth with the declination of the moon till the 7th or 8th day, then for the 7th or 8th day following it decreaseth at the same rate as it had increased before, and ceaseth when the moon changeth its declination. After which the flood is immediately changed into an ebb, and thenceforth the ebb happens at the setting and the flood at the rising of the moon, till the moon again changes its declination. There are two inlets from the ocean to this port. One more direct and short between the island Hainan and the coast of Kwantung, a province of China, the other round about between the same island and the coast of Cochin, and through the shorter passage the tide is sooner propagated to Bat Sham. In the channels of rivers the influx and reflux depends upon the current of the rivers, which obstructs the ingress of the waters from the sea, and promotes their egress to the sea, making the ingress later and slower, and the egress sooner and faster. And hence it is that the reflux is of longer duration than the influx, especially far up the rivers, where the force of the sea is less. So Sturmy tells us, that in the river Avon, 3 miles below Bristol, the water flows only 5 hours, but ebbs 7, and without doubt the difference is yet greater above Bristol, as at Kersham or the Bath. This difference does likewise depend upon the quantity of the flux and reflux. For the more vehement motion of the sea the syzygies of the luminaries more easily overcoming the resistance of the rivers, will make the ingress of the water to happen sooner and to continue longer, and will therefore diminish this difference. But while the moon is approaching to the syzygies, the rivers will be more plentifully filled, their currents being obstructed by the greatness of the tides. And therefore will something more retard the reflux of the sea a little after than a little before the syzygies. Upon which account the slowest tides of all will not happen in the syzygies, but precede them a little, and I observed above that the tides before the syzygies were also retarded by the force of the sun. And from both causes conjoined the retardation of the tides will be both greater and sooner before the syzygies. All which I find to be so, by the tide tables which Flamsteed has composed from a great many observations. By the laws we have been describing, the times of the tides are governed, but the greatness of the tides depends upon the greatness of the seas. Let C represent the center of the earth, EADB the oval figure of the seas, CA the longer semi-axis of this oval, CB the shorter insisting at right angles upon the former, D the middle point between A and B. And ECF or ECF the angle at the center of the earth, subtended by the breadth of the sea that terminates in the shores E, F, or E, F. Now, supposing that the point A is in the middle between the points E, F, and the point D in the middle between the points E, F, if the difference of the height CA, CB represent the quantity of the tide in a very deep sea surrounding the whole earth, the excess of the height CA above the height CE or CF will represent the quantity of the tide in the middle of the CEF, terminated by the shores E, F. And the excess of the height SU above the height CF will nearly represent the quantity of the tide on the shores F of the same sea. Whence it appears that the tides are far less in the middle of the sea than at the shores. And that the tides at the shores are nearly as EF, page 451, 452, the breadth of the sea not exceeding a quadrantal arc. And hence it is that near the equator, where the sea between Africa and America is narrow, the tides are far less than towards either side in the temperate zones, where the seas are extended wider, or on almost all the shores of the Pacific Sea. As well towards America as towards China, and within as well as without the tropics. And that in islands in the middle of the sea they scarcely rise higher than 2 or 3 feet, but on the shores of great continents are 3 or 4 times greater, and above. Especially if the motions propagated from the ocean are by degrees contracted into a narrow space, and the water, to fill and empty the bays alternately, is forced to flow and ebb with great violence through shallow places. As Plymouth and Chepstow Bridge in England, at the Mount of St. Michael and town of Avranches in Normandy, and at Cambaya and Peru in the East Indies. In which places, the sea, hurried in and out with great violence, sometimes lays the shores under water, sometimes leaves them dry, for many miles. Nor is the force of the influx and efflux to be broke till it has raised or depressed the water to 40 or 50 feet and more. Thus also long and shallow straits that open to the sea with mouths wider and deeper than the rest of their channel, such as those about Britain and the Magellanic Straits at the eastern entry, will have a greater flood and ebb. Or will more intend and remit their course, and therefore will rise higher and be depressed lower. Or the coast of South America, it is said that the Pacific Sea in its reflux sometimes retreats 2 miles, and gets out of sight of those that stand on shore. Whence in these places the floods will be also higher, but in deeper waters the velocity of influx and efflux is always less, and therefore the ascent and descent is so too. Nor in such places is the ocean known to ascend to more than 6, 8, or 10 feet. The quantity of the ascent I compute in the following manner. Let S represent the Sun, T the Earth, 419, for 20, P the Moon, PAGB the Moon's orbit. In SP take SK equal to ST and SL to SK in the duplicate ratio of SK to SP, parallel to PT draw LM. And, supposing the mean quantity of the circumsolar force directed towards the Earth to be represented by the distance ST or SK, SL will represent the quantity thereof directed towards the Moon. But that force is compounded of the parts SM, LM. Of which the force LM and that part of SM which is represented by TM, do disturb the motion of the Moon, as appears from Prop. LXV and its corollaries. In so far as the Earth and Moon are revolved about their common center of gravity, the Earth will be liable to the action of the like forces. But we may refer the sums as well of the forces as of the motions to the Moon, and represent the sums of the forces by the lines Tm and Ml, which are proportional to them. The force Lm, in its mean quantity, is to the force by which the Moon may be revolved in an orbit, about the Earth quiescent. At the distance pt in the duplicate ratio of the Moon's periodic time about the Earth to the Earth's periodic time about the Sun, by Cr. 17, Prop. LXVI, that is, in the duplicate ratio of 27d.7 h.43 foot to 365d.6 d.9, or as 1000 to 178725, or 1 to 17829/40. The force by which the Moon may be revolved in its orb about the Earth in rest, at the distance pt of 60½ semi-diameters of the Earth, is to the force by which it may revolve in the same time at the distance of 60 semi-diameters as 60½ to 60. And this force is to the force of gravity with us as 1 to 60 nearly, and therefore the mean force ml is to the force of gravity at the surface of the Earth as 160½ to 60/617829/40, or 1 to 6380926. Whence the force Tm will be also given from the proportion of the lines Tm, Ml. And these are the forces of the Sun, by which the Moon's motions are disturbed. If from the Moon's orbit, p. for 49, we descend to the Earth's surface, those forces will be diminished in the ratio of the distances 60½ and 1, and therefore the force Lm will then become 38604600 times less than the force of gravity. But this force acting equally everywhere upon the Earth, will scarcely affect any change on the motion of the sea, and therefore may be neglected in the explication of that motion. The other force Tm, in places where the Sun is vertical, or in their nadir, is triple the quantity of the force ml, and therefore but 1286820 times less than the force of gravity. Suppose now Adobe to represent the spherical surface of the Earth, ADBE the surface of the water overspreading it, C the center of both, A the place to which the Sun is vertical, be the place opposite. D, E, places at 90 degrees distance from the former, ACM a right-angled cylindric canal passing through the Earth's center. The force Tm in any place is as the distance of the place from the plane DE, on which a line from A to C insists at right angles, and therefore in the part of the canal which is represented by ECLM is of no quantity. But in the other part ACLK is as the gravity at the several heights. For in descending towards the center of the Earth, gravity is, by prop LXX, everywhere as the height. And therefore the force Tm drawing the water upwards will diminish its gravity in the leg ACLK of the canal in a given ratio, upon which account the water will ascend in this leg, till its defect of gravity is supplied by its greater height. Nor will it rest in an equilibrium till its total gravity becomes equal to the total gravity in ECLM, the other leg of the canal. Because the gravity of every particle is as its distance from the Earth's center, the weight of the whole water in either leg will increase in the duplicate ratio of the height. And therefore the height of the water in the leg ACLK will be to the height thereof in the leg CLME in the subduplicate ratio of the number 1286820 to 1286820, or in the ratio of the number 2562353 to the number 2562352. And the height of the water in the leg ECLM to the difference of the heights, as 2562352 to 1. But the height in the leg ECLM is of 1961580 Paris feet, as has been lately found by the mensuration of the French, and, therefore, by the preceding analogy, the difference of the heights comes out 91/5 inches of the Paris foot. And the sun's force will make the height of the sea at A to exceed the height of the same at E by 9 inches. And though the water of the canal ACM be supposed to be frozen into a hard and solid consistence, yet the heights thereof at A and E, and all other intermediate places, would still remain the same. Let AA, in the following figure, represent that excess of height of 9 inches at A, and HF the excess of height at any other place H, and upon DC let fall the perpendicular FG, meeting the globe of the Earth in F. And because the distance of the Sun is so great that all the right lines drawn thereto may be considered as parallel, the force Tm in any place F will be to the same force in the place A as the sine Fg to the radius AC. And, therefore, since those forces tend to the Sun in the direction of parallel lines, they will generate the parallel heights FF, AA, in the same ratio. And therefore the figure of the watered Fabe will be a spheroid made by the revolution of an ellipsis about its longer axis AB. And the perpendicular height FH will be to the oblique height FF as FG to FC, or as FG to AC, and therefore the height FH is to the height AA in the duplicate ratio of FG to AC, that is, in the ratio of the versed sine of double the angle DCF to double the radius, and is thence given. And hence to the several moments of the apparent revolution of the Sun about the Earth we may infer the proportion of the ascent and descent of the waters at any given place under the equator, as well as of the diminution of that ascent and descent, whether arising from the latitude of places or from the Sun's declination. Viz., that on account of the latitude of places, the ascent and descent of the sea is in all places diminished in the duplicate ratio of the cosines of latitude. And on account of the Sun's declination, the ascent and descent under the equator is diminished in the duplicate ratio of the cosine of declination. And in places without the equator the half sum of the morning and evening ascents, that is, the mean ascent, is diminished nearly in the same ratio. Let S and L respectively represent the forces of the Sun and Moon placed in the equator, and at their mean distances from the Earth, are the radius. T and V the versed sines of double the complements of the Sun and Moon's declinations to any given time. D and E the mean apparent diameters of the Sun and Moon, and, supposing F and G to be their apparent diameters to that given time, their forces to raise the tides under the equator will be, in the syzygies, in the quadratures. And if the same ratio is likewise observed under the parallels, from observations accurately made in our northern climates we may determine the proportion of the forces L and S. And then by means of this rule predict the quantities of the tides to every syzygy and quadrature. At the mouth of the river Avon, 3 miles below Bristol, p. 450 to 453, in spring and autumn, the whole ascent of the water in the conjunction or opposition of the luminaries, by the observation of Sturmey, is about 45 feet, but in the quadratures only 25. Because the apparent diameters of the luminaries are not here determined, let us assume them in their mean quantities, as well as the moon's declination in the equinoctial quadratures in its mean quantity, that is, 23½ degree. And the versed sine of double its complement will be 1682, supposing the radius to be 1000. But the declinations of the sun in the equinoxes and of the moon in the syzygies are of no quantity, and the versed sines of double the complements are each 2000. Whence those forces become L plus S in the syzygies, and 1682/2000 L, S in the quadratures, respectively proportional to the heights of the tides of 45 and 25 feet, or of 9 and 5 paces. And, therefore, multiplying the extremes and the means, we have 5L plus 5S is equal to 15,138 divided by 2000 L minus 9S, or L equals 28,000/5138 S equals 55/11S. But farther. I remember to have been told that in summer the ascent of the sea in the syzygies is to the ascent thereof in the quadratures as about 5 to 4. In the solstices themselves it is probable that the proportion may be something less, as about 6 to 5. Whence it would follow that L is 51/6S, for then the proportion is. Till we can more certainly determine the proportion from observation, let us assume L equals 5⅓ S. And since the heights of the tides are as the forces which excite them, and the force of the sun is able to raise the tides to the height of 9 inches, the moon's force will be sufficient to raise the same to the height of 4 feet. And if we allow that this height may be doubled, or perhaps tripled, by that force of reciprocation which we observe in the motion of the waters, and by which their motion once begun is kept up for some time, there will be force enough to generate all that quantity of tides which we really find in the ocean. Thus we have seen that these forces are sufficient to move the sea. But, so far as I can observe, they will not be able to produce any other effect sensible on our earth. For since the weight of 1 grain in 4000 is not sensible in the nicest balance, and the sun's force to move the tides is 12868,200 less than the force of gravity. And the sum of the forces of both moon and sun, exceeding the sun's force only in the ratio of 6 1/3 to 1, is still 203,2890 times less than the force of gravity. It is evident that both forces together are 500 times less than what is required sensibly to increase or diminish the weight of any body in a balance. And, therefore, they will not sensibly move any suspended body. Nor will they produce any sensible effect on pendulums, barometers, bodies swimming in stagnant water, or in the like statical experiments. In the atmosphere, indeed, they will excite such a flux and reflux as they do in the sea, but with so small a motion that no sensible wind will be thence produced. If the effects of both moon and sun in raising the tides, p. 454, as well as their apparent diameters, were equal among themselves, their absolute forces would, by Cor 14, Prop. LXV, be as their magnitudes. But the effect of the moon is to the effect of the sun as about 5 1/3 to 1. And the moon's diameter less than the sun's in the ratio of 31½ to 32 1/3, or of 45 to 46. Now the force of the moon is to be increased in the ratio of the effect directly, and in the triplicate ratio of the diameter inversely. Whence the force of the moon compared with its magnitude will be to the force of the sun compared with its magnitude in the ratio compounded of 5 1/3 to 1, and the triplicate of 45 to 46 inversely, that is, in the ratio of about 57/10 to 1. And therefore the moon, in respect of the magnitude of its body, has an absolute centripetal force greater than the sun in respect of the magnitude of its body in the ratio to 57/10 to 1, and is therefore more dense in the same ratio. In the time of 27d.7 h. 43 foot, in which the moon makes its revolution about the earth, a planet may be revolved about the sun at the distance of 18,954 diameters of the sun from the sun's center, supposing the mean apparent diameter of the sun to be 321/5. And in the same time the moon may be revolved about the earth at rest, at the distance of 30 of the earth's diameters. If in both cases the number of diameters was the same, the absolute circumterrestrial force would, by Core 2, Prop. XL-XLII, be to the absolute circumsolar force as the magnitude of the earth to the magnitude of the sun. Because the number of the earth's diameters is greater in the ratio of 30 to 18,954, the body of the earth will be less in the triplicate of that ratio, that is, in the ratio of 328/29 to 1. Wherefore the earth's force, for the magnitude of its body, is to the sun's force, for the magnitude of its body, as 328/29 to 1, and consequently the earth's density to the sun's will be in the same ratio. Since, then, the moon's density is to the sun's density as 57/10 to 1, the moon's density will be to the earth's density as 57/10 to 328/29, or as 23 to 16. Wherefore since the moon's magnitude is to the earth's magnitude as about 1 to 41.5, the moon's absolute centripetal force will be to the earth's absolute centripetal force as about 1 to 29. And the quantity of matter in the moon to the quantity of matter in the earth in the same ratio. And hence the common center of gravity of the earth and moon is more exactly determined than hitherto has been done, from the knowledge of which we may now infer the moon's distance from the earth with greater accuracy. But I would rather wait till the proportion of the bodies of the moon and earth one to the other is more exactly defined from the phenomena of the tides. Hoping that in the meantime the circumference of the earth may be measured from more distant stations than any body has yet employed for this purpose. Thus I have given an account of the system of the planets. As to the fixed stars, the smallness of their annual parallax proves them to be removed to immense distances from the system of the planets. That this parallax is less than 1 minute is most certain. And from thence it follows that the distance of the fixed stars is above 360 times greater than the distance of Saturn from the Sun. Such as reckon the Earth one of the planets, and the Sun one of the fixed stars. May remove the fixed stars to yet greater distances by the following arguments. From the annual motion of the earth there would happen an apparent transposition of the fixed stars, one in respect of another, almost equal to their double parallax. But the greater and nearer stars, in respect of the more remote, which are only seen by the telescope, have not hitherto been observed to have the least motion. If we should suppose that motion to be but less than 20 inch, the distance of the nearer fixed stars would exceed the mean distance of Saturn by above 2,000 times. Again, the disk of Saturn, which is only 17 inch or 18 in diameter, receives but about 1/21000000000 the sun's light, for so much less is that disk than the whole spherical surface of the orb of Saturn. Now if we suppose Saturn to reflect about 1/4 of this light, the whole light reflected from its illuminated hemisphere will be about 1/42000000000 of the whole light emitted from the sun's hemisphere. And, therefore, since light is rarefied in the duplicate ratio of the distance from the luminous body, if the sun was 10,000 times more distant than Saturn, it would yet appear as lucid as Saturn now does without its ring, that is, something more lucid than a fixed star of the first magnitude. Let us, therefore, suppose that the distance from which the sun would shine as a fixed star exceeds that of Saturn by about 100,000 times, and its apparent diameter will be 7 v.166. And its parallax arising from the annual motion of the earth 13 inch, and so great will be the distance, the apparent diameter, and the parallax of the fixed stars of the first magnitude, in bulk and light equal to our sun. Some may, perhaps, imagine that a great part of the light of the fixed stars is intercepted and lost in its passage through so vast spaces, and upon that account pretend to place the fixed stars at nearer distances. But at this rate the remoter stars could be scarcely seen. Suppose, for example, that 3/4 of the light perish in its passage from the nearest fixed stars to us. Then 3/4 will twice perish in its passage through a double space, thrice through a triple, and so forth. And, therefore, the fixed stars that are at a double distance will be 16 times more obscure, viz. 4 times more obscure on account of the diminished apparent diameter, and, again, 4 times more on account of the lost light. And, by the same argument, the fixed stars at a triple distance will be 944, or 144 times more obscure. And those at a quadruple distance will be 16444, or 1024 times more obscure, but so great a diminution of light is no ways consistent with the phenomena and with that hypothesis which places the fixed stars at different distances. The fixed stars being, therefore, at such vast distances from one another, page 460, 461, can neither attract each other sensibly, nor be attracted by our sun. But the comets must unavoidably be acted on by the circumsolar force. For as the comets were placed by astronomers above the moon, because they were found to have no diurnal parallax, so their annual parallax is a convincing proof of their descending into the regions of the planets. For all the comets which move in a direct course, according to the order of the signs, about the end of their appearance become more than ordinarily slow, or retrograde, if the earth is between them and the sun. And more than ordinarily swift if the earth is approaching to a heliocentric opposition with them. Whereas, on the other hand, those which move against the order of the signs, towards the end of their appearance, appear swifter than they ought to be if the earth is between them and the sun. And slower, and perhaps retrograde, if the earth is in the other side of its orbit. This is occasioned by the motion of the earth in different situations. If the earth go the same way with the comet, with a swifter motion, the comet becomes retrograde, if with a slower motion, the comet becomes slower, however, and if the earth move the contrary way, it becomes swifter. And by collecting the differences between the slower and swifter motions, and the sums of the more swift and retrograde motions, and comparing them with the situation and motion of the earth from whence they arise, I found, by means of this parallax, that the distances of the comets at the time they cease to be visible to the naked eye are always less than the distance of Saturn, and generally even less than the distance of Jupiter. The same thing may be collected from the curvature of the way of the comets, page 462. These bodies go on nearly in great circles while their motion continues swift. But about the end of their course, when that part of their apparent motion which arises from the parallax bears a greater proportion to their whole apparent motion, they commonly deviate from those circles. And when the earth goes to one side, they deviate to the other, and this deflection, because of its corresponding with the motion of the earth, must arise chiefly from the parallax. And the quantity thereof is so considerable, as, by my computation, to place the disappearing comets a good deal lower than Jupiter. Whence it follows, that, when they approach nearer to us in their perigees and perihelions, they often descend below the orbits of Mars and the inferior planets. Moreover, this nearness of the comets is confirmed by the annual parallax of the orbit, in so far as the same is pretty nearly collected by the supposition that the comets move uniformly in right lines. The method of collecting the distance of a comet according to this hypothesis from 4 observations, first attempted by Kepler, and perfected by Dr. Wallace and Sir Christopher Wren, is well known. And the comets reduced to this regularity generally pass through the middle of the planetary region. So the comets of the year 1607 and 1618, as their motions are defined by Kepler, passed between the Sun and the Earth. That of the year 1664 below the orbit of Mars, and that in 1680 below the orbit of Mercury, as its motion was defined by Sir Christopher Wren and others. By a like rectilinear hypothesis, Hevelius placed all the comets about which we have any observations below the orbit of Jupiter. It is a false notion, therefore, and contrary to astronomical calculation, which some have entertained, who, from the regular motion of the comets, either remove them into the regions of the fixed stars, or deny the motion of the earth. Whereas their motions cannot be reduced to perfect regularity, unless we suppose them to pass through the regions near the earth in motion. And these are the arguments drawn from the parallax, so far as it can be determined without an exact knowledge of the orbits and motions of the comets. The near approach of the comets is farther confirmed from the light of their heads, p. 463, 465, for the light of a celestial body, illuminated by the sun, and receding to remote parts, is diminished in the quadruplicate proportion of the distance. To wit, in one duplicate proportion on account of the increase of the distance from the sun, and in another duplicate proportion on account of the decrease of the apparent diameter. Hence it may be inferred, that Saturn being at a double distance, and having its apparent diameter nearly half of that of Jupiter, must appear about 16 times more obscure. And that, if its distance were 4 times greater, its light would be 256 times less, and therefore would be hardly perceivable to the naked eye. But now the comets often equal Saturn's light, without exceeding him in their apparent diameters. So the comet of the year 1668, according to Dr. Hooke's observations, equaled in brightness the light of a fixed star of the first magnitude. And its head, or the star in the middle of the coma, appeared, through a telescope of 15 feet, as lucid as Saturn near the horizon. But the diameter of the head was only 25 inch, that is, almost the same with the diameter of a circle equal to Saturn and his ring. The coma or hair surrounding the head was about 10 times as broad, namely, 41/6 minute. Again, the least diameter of the hair of the comet of the year 1682, observed by Mr. Flamsteed with a tube of 16 feet and measured with the micrometer, was 2 feet 0 inches. But the nucleus, or star in the middle, scarcely possessed the 10th part of this breadth, and was therefore only 11 inch or 12 broad. But the light and clearness of its head exceeded that of the year 1680, and was equal to that of the stars of the first or second magnitude. Moreover, the comet of the year 1665, in April, as Hevelius informs us, exceeded almost all the fixed stars in splendor, and even Saturn itself, as being of a much more vivid color. For this comet was more lucid than that which appeared at the end of the foregoing year and was compared to the stars of the first magnitude. The diameter of the coma was about 6 foot. But the nucleus, compared with the planets by means of a telescope, was plainly less than Jupiter, and was sometimes thought less, sometimes equal to the body of Saturn within the ring. To this breadth add that of the ring, and the whole face of Saturn will be twice as great as that of the comet, with a light not at all more intense, and therefore the comet was nearer to the Sun than Saturn. From the proportion of the nucleus to the whole head found by these observations, and from its breadth, which seldom exceeds 8 foot or 12, it appears that the stars of the comets are most commonly of the same apparent magnitude as the planets. But that their light may be compared oftentimes with that of Saturn, and sometimes exceeds it. And hence it is certain that in their perihelia their distances can scarcely be greater than that of Saturn. At twice that distance, the light would be 4 times less, which besides by its dim paleness would be as much inferior to the light of Saturn as the light of Saturn is to the splendor of Jupiter, but this difference would be easily observed. At a distance 10 times greater, their bodies must be greater than that of the Sun, but their light would be 100 times fainter than that of Saturn. And at distances still greater, their bodies would far exceed the Sun. But, being in such dark regions, they must be no longer visible. So impossible is it to place the comets in the middle regions between the Sun and fixed stars, accounting the Sun as one of the fixed stars. For certainly they would receive no more light there from the Sun than we do from the greatest of the fixed stars. So far we have gone without considering that obscuration which comets suffer from that plenty of thick smoke which encompasseth their heads, and through which the heads always shew dull as through a cloud. For by how much the more a body is obscured by this smoke, by so much the more near it must be allowed to come to the Sun, that it may vie with the planets in the quantity of light which it reflects. Whence it is probable that the comets descend far below the orbit of Saturn, as we proved before from their parallax. But, above all, the thing is evinced from their tails, which must be owing either to the Sun's light reflected from a smoke arising from them, and dispersing itself through the ether, or to the light of their own heads. In the former case we must shorten the distance of the comets, lest we be obliged to allow that the smoke arising from their heads is propagated through such a vast extent of space, and with such a velocity of expansion, as will seem altogether incredible. In the latter case the whole light of both head and tail must be ascribed to the central nucleus. But, then, if we suppose all this light to be united and condensed within the disk of the nucleus, certainly the nucleus will by far exceed Jupiter itself in splendor, especially when it emits a very large and lucid tail. If, therefore, under a less apparent diameter, it reflects more light, it must be much more illuminated by the Sun, and therefore much nearer to it. So the comet that appeared December 12th and 15th, OS. Anno 1679, at the time it emitted a very shining tail, whose splendor was equal to that of many stars like Jupiter, if their light were dilated and spread through so great a space, was, as to the magnitude of its nucleus, less than Jupiter, as Mr. Flamsteed observed, and therefore was much nearer to the sun, nay, it was even less than Mercury. For on the 17th of that month, when it was nearer to the earth, it appeared to Cassini through a telescope of 35 feet, a little less than the globe of Saturn. On the 8th of this month, in the morning, Dr. Halley saw the tail, appearing broad and very short, and as if it rose from the body of the sun itself, at that time very near its rising. Its form was like that of an extraordinary bright cloud. Nor did it disappear till the sun itself began to be seen above the horizon. Its splendor, therefore, exceeded the light of the clouds till the sun rose, and far surpassed that of all the stars together, as yielding only to the immediate brightness of the sun itself. Neither Mercury, nor Venus, nor the moon itself, are seen so near the rising sun. Imagine all this dilated light collected together, and to be crowded into the orbit of the comet's nucleus, which was less than Mercury. By its splendor, thus increased, becoming so much more conspicuous, it will vastly exceed Mercury, and therefore must be nearer to the sun. On the 12th and 15th of the same month, this tail, extending itself over a much greater space, appeared more rare. But its light was still so vigorous as to become visible when the fixed stars were hardly to be seen, and soon after to appear like a fiery beam shining in a wonderful manner. From its length, which was 40 or 50 degrees, and its breadth of 2 degrees, we may compute what the light of the whole must be. This near approach of the comets to the sun is confirmed from the situation they are seen in when their tails appear most resplendent. For when the head passes by the sun, and lies hid under the solar rays, very bright and shining tails, like fiery beams, are said to issue from the horizon. But afterwards, when the head begins to appear, and is got farther from the sun, that splendor always decreases, and turns by degrees into a paleness like to that of the Milky Way, but much more sensible at first, after that vanishing gradually. Such was that most resplendent comet described by Aristotle, Lib 1, Meteor. 6. The head thereof could not be seen, because it set before the sun, or at least was hid under the sun's rays, but the next day it was seen as well as might be. For, having left the sun but a very little way, it set immediately after it, and the scattered light of the head obscured by the too great splendor of the tail, did not yet appear. But afterwards, says Aristotle, when the splendor of the tail was now diminished, the head of the comet recovered its native brightness. And the splendor of its tail reached now to a third part of the heavens, that is, to 60 degrees. It appeared in the winter season, and, rising to Orion's girdle, there vanished away. 2 comets of the same kind are described by Justin, Lib 37, which, according to his account, shined so bright, that the whole heaven seemed to be on fire. And by their greatness filled up a fourth part of the heavens, and by their splendor exceeded that of the sun. By which last words a near position of these bright comets and the rising or setting sun is intimated, page 494, 495. We may add to these the comet of the year 1101 or 1106, the star of which was small and obscure, like that of 1680. But the splendor arising from it extremely bright, reaching like a fiery beam to the east and north, as Hevelius has it from Simeon, the monk of Durham. It appeared at the beginning of February about the evening in the southwest. From this and from the situation of the tail we may infer that the head was near the sun. Matthew Paris says, it was about 1 cubit from the sun, from the 3rd, or rather the 6th, to the 9th hour, sending out a long stream of light. The comet of 1264, in July, or about the solstice, preceded the rising sun, sending out its beams with a great light towards the west as far as the middle of the heavens. And at the beginning it ascended a little above the horizon, but as the sun went forwards it retired every day farther from the horizon, till it passed by the very middle of the heavens. It is said to have been at the beginning large and bright, having a large coma, which decayed from day to day. It is described in Append. Math. Paris, History on after this manner, and Christie 1265, there appeared a comet so wonderful, that none then living had ever seen the like, for, rising from the east with a great brightness, it extended itself with a great light as far as the middle of the hemisphere towards the west. The Latin original being somewhat barbarous and obscure, it is here subjoined. Ab orient enim cum magno fulgor surgens, usque ad medium hemisphoeriae versus occidentum, omnia perlucide protrahebat. In the year 1401 or 1402, the sun being got below the horizon, there appeared in the west a bright and shining comet, sending out a tail upwards, in splendor like a flame of fire, and in form like a spear, darting its rays from west to east. When the sun was sunk below the horizon, by the luster of its own rays it enlightened all the borders of the earth, not permitting the other stars to shew their light, or the shades of night to darken the air, because its light exceeded that of the others, and extended itself to the upper part of the heavens, flaming, and, History Besant. Duc. Michigan Nepet. From the situation of the tail of this comet, and the time of its first appearance, we may infer that the head was then near the sun, and went farther from him every day, for that comet continued 3 months. In the year 1527, August 11, about 4 in the morning, there was seen almost throughout Europe a terrible comet in Leo, which continued flaming an hour and a quarter every day. It rose from the east, and ascended to the south and west to a prodigious length. It was most conspicuous to the north, and its cloud, that is, its tail, was very terrible, having, according to the fancies of the vulgar, the form of an arm a little bent holding a sword of a vast magnitude. In the year 1618, in the end of November, there began a rumor, that there appeared about sunrising a bright beam, which was the tail of a comet whose head was yet concealed within the brightness of the solar rays. On November 24, and from that time, the comet itself appeared with a bright light, its head and tail being extremely resplendent. The length of the tail, which was at first 20 or 30 degrees, increased till December 9, when it arose to 75 degrees, but with a light much more faint and dilute than at the beginning. In the year 1668, March 5, N.S., about 7 in the evening, P. Valent. Estancius, being in Brazil, saw a comet near the horizon in the southwest. Its head was small, and scarcely discernible, but its tail extremely bright and refulgent, so that the reflection of it from the sea was easily seen by those who stood upon the shore. This great splendor lasted but 3 days, decreasing very remarkably from that time. The tail at the beginning extended itself from west to south, and in a situation almost parallel to the horizon, appearing like a shining beam 23 degrees in length. Afterwards, the light decreasing, its magnitude increased till the comet ceased to be visible, so that Cassini, at Bologna, saw it, March 10, 11, 12, rising from the horizon 32 degrees, in length. In Portugal it is said to have taken up a fourth part of the heavens, that is, 45 degrees, extending itself from west to east with a notable brightness. Though the whole of it was not seen, because the head in this part of the world always lay hid below the horizon. From the increase of the tail it is plain that the head receded from the sun, and was nearest to it at the beginning, when the tail appeared brightest. To all these we may add the comet of 1680, whose wonderful splendor at the conjunction of the head with the sun was above described. But so great a splendor argues the comets of this kind to have really passed near the fountain of light, especially since the tails never shine so much in their opposition to the sun, nor do we read that fiery beams have ever appeared there. Lastly, the same thing is inferred, page 466, 467, from the light of the heads increasing in the recess of the comets from the earth towards the sun, and decreasing in their return from the sun towards the earth. For so the last comet of the year 1665, by the observation of Hevelius, from the time that it was first seen, was always losing of its apparent motion, and therefore had already passed its perigee, yet the splendor of its head was daily increasing, till, being hid by the sun's rays, the comet ceased to appear. The comet of the year 1683, by the observation of the same Hevelius, about the end of July, when it first appeared, moved at a very slow rate, advancing only about 40 or 45 minutes in its orbit in a day's time. But from that time its diurnal motion was continually upon the increase till September 4, when it arose to about 5 degrees, and therefore in all this interval of time the comet was approaching to the earth. Which is likewise proved from the diameter of its head measured with a micrometer, for, August the 6th, Hevelius found it only 6 feet 5 inches, including the coma, which, September 2nd, he observed 9 feet 7 inches. And therefore its head appeared far less about the beginning than towards the end of its motion, though about the beginning, because nearer to the sun, it appeared far more lucid than towards the end, as the same Hevelius declares. Wherefore in all this interval of time, on account of its recess from the sun, it decreased in splendor, notwithstanding its access towards the earth. The comet of the year 1618, about the middle of December, and that of the year 1680, about the end of the same month, did both move with their greatest velocity, and were therefore then in their perigees. But the greatest splendor of their heads was seen 2 weeks before, when they had just got clear of the sun's rays, and the greatest splendor of their tails a little more early, when yet nearer to the sun. The head of the former comet, according to the observations of Cysatus, December 1st, appeared greater than the stars of the first magnitude, and, December 16, being then in its perigee, of a small magnitude, and the splendor or clearness was much diminished. January 7th, Kepler, being uncertain about the head, left off observing. December 12, the head of the last comet was seen and observed by Flamsteed at the distance of 9 degrees from the sun, which a star of the third magnitude could hardly have been. December 15th and 17th, the same appeared like a star of the third magnitude, its splendor being diminished by the bright clouds near the setting sun. December 26, when it moved with the greatest swiftness, and was almost in its perigee, it was inferior to Os Pegasi, a star of the third magnitude. January 3rd, it appeared like a star of the fourth, January 9th, like a star of the fifth. January 13th. It disappeared, by reason of the brightness of the moon, which was then in its increase. January 25th, it was scarcely equal to the stars of the seventh magnitude. If we take equal times on each hand of the perigee, the heads placed at remote distances would have shined equally before and after, because of their equal distances from the earth. That in one case they shined very bright, and in the other vanished, is to be ascribed to the nearness of the sun in the first case, and his distance in the other. And from the great difference of the light in these two cases we infer its great nearness in the first of them. For the light of the comets uses to be regular, and to appear greatest when their heads move the swiftest, and are therefore in their perigees, excepting in so far as it is increased by their nearness to the sun. From these things I at last discovered why the comets frequent so much the region of the sun. If they were to be seen in the regions a great way beyond Saturn, they must appear oftener in these parts of the heavens that are opposite to the sun. For those which are in that situation would be nearer to the earth, and the interposition of the sun would obscure the others, but, looking over the history of comets, I find that 4 or 5 times more have been seen in the hemisphere towards the sun than in the opposite hemisphere. Besides, without doubt, not a few which have been hid by the light of the sun. For comets descending into our parts neither emit tails, nor are so well illuminated by the sun, as to discover themselves to our naked eyes, till they are come nearer to us than Jupiter. But the far greater part of that spherical space, which is described about the sun with so small an interval, lies on that side of the earth which regards the sun, and the comets in that greater part are more strongly illuminated. As being for the most part nearer to the sun, besides, from the remarkable eccentricity of their orbits, it comes to pass that their lower apsides are much nearer to the sun than if their revolutions were performed in circles concentric to the sun. Hence also we understand why the tails of the comets, while their heads are descending towards the sun, always appear short and rare, and are seldom said to have exceeded 15 or 20 degrees in length. But in the recess of the heads from the sun often shine like fiery beams, and soon after reach to 40, 50, 60, 70 degrees in length, or more. This great splendor and length of the tails arises from the heat which the sun communicates to the comet as it passes near it. And thence, I think, it may be concluded, that all the comets that have had such tails have passed very near the sun. Hence also we may collect that the tails arise from the atmospheres of the heads, page 487 to 488, but we have had three several opinions about the tails of comets. For some will have it that they are nothing else but the beams of the sun's light transmitted through the comets' heads, which they suppose to be transparent. Others, that they proceed from the refraction which light suffers in passing from the comet's head to the earth. And, lastly, others, that they are a sort of clouds or vapor constantly rising from the comets' heads, and tending towards the parts opposite to the sun. The first is the opinion of such as are yet unacquainted with optics. For the beams of the sun are not seen in a darkened room, but in consequence of the light that is reflected from them by the little particles of dust and smoke which are always flying about in the air. And hence it is that in air impregnated with thick smoke they appear with greater brightness, and are more faintly and more difficultly seen in a finer air. But in the heavens, where there is no matter to reflect the light, they are not to be seen at all. Light is not seen as it is in the beams, but as it is thence reflected to our eyes. For vision is not made but by rays falling upon the eyes, and therefore there must be some reflecting matter in those parts where the tails of comets are seen, and so the argument turns upon the third opinion. For that reflecting matter can be nowhere found but in the place of the tail, because otherwise, since all the celestial spaces are equally illuminated by the sun's light, no part of the heavens could appear with more splendor than another. The second opinion is liable to many difficulties. The tails of comets are never seen variegated with those colors which ever used to be inseparable from refraction. And the distinct transmission of the light of the fixed stars and planets to us is a demonstration that the ether or celestial medium is not endowed with any refractive power. For as to what is alleged that the fixed stars have been sometimes seen by the Egyptians environed with a coma or capillidium, because that has but rarely happened, it is rather to be ascribed to a casual refraction of clouds. As well as the radiation and scintillation of the fixed stars to the refractions both of the eyes and air. For upon applying a telescope to the eye, those radiations and scintillations immediately disappear. By the tremulous agitation of the air and ascending vapors, it happens that the rays of light are alternately turned aside from the narrow space of the pupil of the eye. But no such thing can have place in the much wider aperture of the object glass of a telescope, and hence it is that a scintillation is occasioned in the former case which ceases in the latter. And this cessation in the latter case is a demonstration of the regular transmission of light through the heavens without any sensible refraction. But, to obviate an objection that may be made from the appearing of no tail in such comets as shine but with a faint light, as if the secondary rays were then too weak to affect the eyes. And for this reason it is that the tails of the fixed stars do not appear, we are to consider that by the means of telescopes the light of the fixed stars may be augmented above 100-fold and yet no tails are seen. That the light of the planets is yet more copious without any tail, but that comets are seen sometimes with huge tails when the light of their heads is but faint and dull. For so it happened in a comet of the year 1680, when in the month of December it was scarcely equal in light to the stars of the second magnitude, and yet emitted a notable tail, extending to the length of 40 degrees, 50 degrees, 60 degrees, or 70 degrees, and upwards. And afterwards, on the 27th and 28th of January, the head appeared but as a star of the 7th magnitude. But the tail, as was said above, with a light that was sensible enough, though faint, was stretched out to 6 or 7 degrees in length, and with a languishing light that was more difficultly seen, even to 12 degrees and upwards. But on the 9th and 10th of February, when to the naked eye the head appeared no more, I saw through a telescope the tail of 2 degrees in length. But farther. If the tail was owing to the refraction of the celestial matter, and did deviate from the opposition of the sun, according as the figure of the heavens requires, that deviation, in the same places of the heavens, should be always directed towards the same parts, but the comet of the year 1680, December 28 d. 8½ h. p.m. at London, was seen in Pisces, 8 degrees 41 minutes, with latitude north 28 degrees 6 minutes, while the Sun was in Capricorn 18 degrees 26 minutes. And the comet of the year 1577, December 29th, was in Pisces 8 degrees 41 minutes, with latitude north 28 degrees 40 minutes. And the Sun, as before, in about Capricorn 18 degrees 26 minutes. In both cases the situation of the Earth was the same, and the comet appeared in the same place of the heavens. Yet in the former case the tail of the comet, as well by my observations as by the observations of others, deviated from the opposition of the Sun towards the north by an angle of 4½ degrees. Whereas in the latter there was, according to the observation of Tycho, a deviation of 21 degrees towards the south. The refraction, therefore, of the heavens being thus disproved, it remains that the phenomena of the tails of comets must be derived from some reflecting matter. That vapors sufficient to fill such immense spaces may arise from the comet's atmospheres, may be easily understood from what follows. It is well known that the air near the surface of our Earth possesses a space about 1,200 times greater than water of the same weight. And therefore a cylindric column of air 1,200 feet high is of equal weight with a cylinder of water of the same breadth, and but 1 foot high. But a cylinder of air reaching to the top of the atmosphere is of equal weight with a cylinder of water about 33 feet high. And therefore if from the whole cylinder of air the lower part of 1,200 feet high is taken away, the remaining upper part will be of equal weight with a cylinder of water 32 feet high. Wherefore at the height of 1,200 feet, or 2 furlongs, the weight of the incumbent air is less, and consequently the rarity of the compressed air greater, than near the surface of the Earth in the ratio of 33 to 32. And, having this ratio, we may compute the rarity of the air in all places whatsoever, by the help of Cor Prop. XX, Book 2, supposing the expansion thereof to be reciprocally proportional to its compression. And this proportion has been proved by the experiments of Hooke and others. The result of the computation I have set down in the following table, in the first column of which you have the height of the air in miles, whereof 4,000 make a semi-diameter of the Earth. In the second the compression of the air, or the incumbent weight, in the third its rarity or expansion, supposing gravity to decrease in the duplicate ratio of the distances from the Earth's center. And the Latin numeral characters are here used for certain numbers of ciphers, as 0, 17, 12, 24 for 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 2, 4, and 26,956.15 for 269560000000000000000. Airs. Height. Compression. Expansion. 0. 5. 10. 20. 40. 400. 4,000. 40,000. 400,000. 4,000,000. Infinite. 33. 17, 85, 15. 9, 67, 17. 2,852. 0, 25, 25. 0, 17, 12, 24. 0, CV. 4,465. 0, XII 1628. 0, CCX 7895. 0, XII 9878. 0, XII 6041. 1. 1. 3. 11. 136. 26,956. 73,907. 20,263. 41,798. 33,414. 54,622. 8486. 4151. 571. 83. 15. CII. Klexix. Kvi. 6. 6. But from this table it appears that the air, in proceeding upwards, is rarefied in such manner, that a sphere of that air which is nearest to the earth, of but 1 inch in diameter, if dilated with that rarefaction which it would have at the height of 1 semi-diameter of the earth, would fill all the planetary regions as far as the sphere of Saturn, and a great way beyond. And at the height of 10 semi-diameters of the earth would fill up more space than is contained in the whole heavens on this side the fixed stars, according to the preceding computation of their distance. And though, by reason of the far greater thickness of the atmospheres of comets, and the great quantity of the circumsolar centripetal force, it may happen that the air in the celestial spaces, and in the tails of comets, is not so vastly rarefied. Yet from this computation it is plain that a very small quantity of air and vapor is abundantly sufficient to produce all the appearances of the tails of comets. For that they are indeed of a very notable rarity appears from the shining of the stars through them. The atmosphere of the earth, illuminated by the sun's light, though but of a few miles in thickness, obscures and extinguishes the light not only of all the stars, but even of the moon itself. Whereas the smallest stars are seen to shine through the immense thickness of the tails of comets, likewise illuminated by the sun, without the least diminution of their splendor. Kepler ascribes the ascent of the tails of comets to the atmospheres of their heads, and their direction towards the parts opposite to the sun to the action of the rays of light carrying along with them the matter of the comet's tails. And without any great incongruity we may suppose that, in so free spaces, so fine a matter as that of the ether may yield to the action of the rays of the sun's light. Though those rays are not able sensibly to move the gross substances in our parts, which are clogged with so palpable a resistance. Another author thinks that there may be a sort of particles of matter endowed with a principle of levity as well as others are with a power of gravity. That the matter of the tails of comets may be of the former sort, and that its ascent from the sun may be owing to its levity. But, considering the gravity of terrestrial bodies is as the matter of the bodies, and therefore can be neither more nor less in the same quantity of matter, I am inclined to believe that this ascent may rather proceed from the rarefaction of the matter of the comet's tails. The ascent of smoke in a chimney is owing to the impulse of the air with which it is entangled. The air rarefied by heat ascends, because its specific gravity is diminished, and in its ascent carries along with it the smoke with which it is engaged. And why may not the tail of a comet rise from the sun after the same manner? For the sun's rays do not act any way upon the mediums which they pervade but by reflection and refraction. And those reflecting particles heated by this action, heat the matter of the ether which is involved with them. That matter is rarefied by the heat which it acquires, and because by this rarefaction the specific gravity, with which it tended towards the sun before, is diminished, it will ascend therefrom like a stream, and carry along with it the reflecting particles of which the tail of the comet is composed. The impulse of the sun's light, as we have said, promoting the ascent. But that the tails of comets do arise from their heads, page 488, and tend towards the parts opposite to the sun, is farther confirmed from the laws which the tails observe. For, lying in the planes of the comet's orbits which pass through the sun, they constantly deviate from the opposition of the sun towards the parts which the comet's heads in their progress along those orbits have left. And to a spectator placed in those planes they appear in the parts directly opposite to the sun, but as the spectator recedes from those planes, their deviation begins to appear, and daily becomes greater. And the deviation, ceteris paribus, appears less when the tail is more oblique to the orbit of the comet, as well as when the head of the comet approaches nearer to the sun. Especially if the angle of deviation is estimated near the head of the comet. Farther, the tails which have no deviation appear straight, but the tails which deviate are likewise bended into a certain curvature. And this curvature is greater when the deviation is greater, and is more sensible when the tail, ceteris paribus, is longer, for in the shorter tails the curvature is hardly to be perceived. And the angle of deviation is less near the comet's head, but greater towards the other end of the tail, and that because the lower side of the tail regards the parts from which the deviation is made, and which lie in a right line drawn out infinitely from the sun through the comet's head. And the tails that are longer and broader, and shine with a stronger light, appear more resplendent and more exactly defined on the convex than on the concave side. Upon which accounts it is plain that the phenomena of the tails of comets depend upon the motions of their heads, and by no means upon the places of the heavens in which their heads are seen. And that, therefore, the tails of the comets do not proceed from the refraction of the heavens, but from their own heads, which furnish the matter that forms the tail. For as in our air the smoke of a heated body ascends either perpendicularly, if the body is at rest, or obliquely if the body is moved obliquely, so in the heavens, where all the bodies gravitate towards the sun, smoke and vapor must, as we have already said, ascend from the sun, and either rise perpendicularly, if the smoking body is at rest, or obliquely, if the body, in the progress of its motion, is always leaving those places from which the upper or higher parts of the vapors had risen before. And that obliquity will be less where the vapor ascends with more velocity, to wit, near the smoking body, when that is near the sun, for there the force of the sun by which the vapor ascends is stronger. But because the obliquity is varied, the column of vapor will be incurvated. And because the vapor in the preceding side is something more recent, that is, has ascended something more lately from the body, it will therefore be something more dense on that side, and must on that account reflect more light, as well as be better defined. The vapor on the other side languishing by degrees, and vanishing out of sight. But it is none of our present business to explain the causes of the appearances of nature. Let those things which we have last said be true or false, we have at least made out, in the preceding discourse, that the rays of light are directly propagated from the tails of comets in right lines through the heavens, in which those tails appear to the spectators wherever placed. And consequently the tails must ascend from the heads of the comets towards the parts opposite to the sun. And from this principle we may determine anew the limits of their distances in manner following. Let S represent the sun, T the earth, Sta the elongation of a comet from the sun, and Atb the apparent length of its tail. And because the light is propagated from the extremity of the tail in the direction of the right line Tb, that extremity must lie somewhere in the line Tb. Suppose it in D, and join ds cutting Ta in C. Then, because the tail is always stretched out towards the parts nearly opposite to the sun, and therefore the sun, the head of the comet, and the extremity of the tail, lie in a right line, the comet's head will be found in C. Parallel to Tb draw Sa, meeting the line Ta in A, and the comet's head C must necessarily be found between T and A, because the extremity of the tail lies somewhere in the infinite line Tb. And all the lines Sd which can possibly be drawn from the point S to the line Tb must cut the line Ta somewhere between T and A. Wherefore the distance of the comet from the earth cannot exceed the interval Ta, nor its distance from the sun the interval Sa beyond, or St on this side the sun. For instance, the elongation of the comet of 1680 from the sun, December 12, was 9 degrees, and the length of its tail 35 degrees at least. If, therefore, a triangle TSA is made, whose angle T is equal to the elongation 9 degrees, and angle A equal to ATB, or to the length of the tail, viz. 35 degrees, then SA will be to ST, that is, the limit of the greatest possible distance of the comet from the sun to the semi-diameter of the orbis magnus, as the sine of the angle T to the sine of the angle A, that is, as about 3 to 11. And therefore the comet at that time was less distant from the sun than by March 11 of the earth's distance from the sun, and consequently either was within the orb of Mercury, or between that orb and the earth. Again, December 21, the elongation of the comet from the sun was 32 2/3 degree, and the length of its tail 70 degrees. Wherefore as the sine of 32 2/3 degree to the sine of 70 degrees, that is, as 4 to 7, so was the limit of the comet's distance from the sun to the distance of the earth from the sun, and consequently the comet had not then got without the orb of Venus. December 28, the elongation of the comet from the sun was 55 degrees, and the length of its tail 56 degrees. And therefore the limit of the comet's distance from the sun was not yet equal to the distance of the earth from the same, and consequently the comet had not then got without the earth's orbit. But from its parallax we find that its egress from the orbit happened about January 5, as well as that it had descended far within the orbit of Mercury. Let us suppose it to have been in its perihelion December the 8th, when it was in conjunction with the Sun, and it will follow that in the journey from its perihelion to its exit out of the Earth's orbit it had spent 28 days. And consequently that in the 26 or 27 days following, in which it ceased to be farther seen by the naked eye, it had scarcely doubled its distance from the Sun. And by limiting the distances of other comets by the like arguments, we come at last to this conclusion, that all comets, during the time in which they are visible by us, are within the compass of a spherical space described about the Sun as a center, with a radius double, or at most triple, of the distance of the Earth from the Sun. And hence it follows that the comets, during the whole time of their appearance unto us, being within the sphere of activity of the circumsolar force, and therefore agitated by the impulse of that force, will, by Cor. I, Prop. 12, Book I, for the same reason as the planets, be made to move in conic sections that have one focus in the center of the Sun, and by radii drawn to the Sun, to describe areas proportional to the times. For that force is propagated to an immense distance, and will govern the motions of bodies far beyond the orbit of Saturn. There are 3 hypotheses about comets, page 466. For some will have it that they are generated and perish as often as they appear and vanish, others, that they come from the regions of the fixed stars, and are seen by us in their passage through the system of our planets. And, lastly, others, that they are bodies perpetually revolving about the Sun in very eccentric orbits. In the first case, the comets, according to their different velocities, will move in conic sections of all sorts. In the second, they will describe hyperbolas, and in either of the two will frequent indifferently all quarters of the heavens, as well those about the poles as those towards the ecliptic. In the third, their motions will be performed in ellipses very eccentric, and very nearly approaching to parabolas. But, if the law of the planets is observed, their orbits will not much decline from the plane of the ecliptic. And, so far as I could hitherto observe, the third case obtains, for the comets do, indeed, chiefly frequent the zodiac, and scarcely ever attain to a heliocentric latitude of 40 degrees. And that they move in orbits very nearly parabolical, I infer from their velocity. For the velocity with which a parabola is described is everywhere to the velocity with which a comet or planet may be revolved about the Sun in a circle at the same distance in the subduplicate ratio of 2 to 1, by Cor 7, Prop. 16. And, by my computation, the velocity of comets is found to be much about the same. I examined the thing by inferring nearly the velocities from the distances, and the distances both from the parallaxes and the phenomena of the tails. And never found the errors of excess or defect in the velocities greater than what might have arose from the errors in the distances collected after that manner. But I likewise made use of the reasoning that follows. Supposing the radius of the orbis magnus to be divided into 1,000 parts, let the numbers in the first column of the following table represent the distance of the vertex of the parabola from the Sun center, expressed by those parts, and a comet in the times expressed in col. 2, will pass from its perihelion to the surface of the sphere which is described about the Sun as a center with the radius of the orbis magnus, and in the times expressed in col. 3, 4, and 5, it will double, triple, and quadruple, that its distance from the Sun. Table I. The distance of a comet's perihelion from the Sun's center. The time of a comet's passage from its perihelion to a distance from the Sun equal to the radii of the orbis magnus, to its double, to its triple, to its quadruple, 0, 5, 10, 20, 40, 80, 160, 320, 640, 1280, 2560, D. H. 271112, 271607, 272100, 280640, 290132, 301325, 330529. 371346. 370949. D. H. 771628. 772314. 780624. 782013. 792334. 820456. 861026. 932338. 1050128. 1060635. D. H. 1421714. 1440319. 1531608. 2000643. 1472231. D. H. 2191730. 2210854. 2321220. 2970346. 3000603. This table, here corrected, is made on the supposition that the Earth's diurnal motion is just 59, and the measure of 1 minute loosely 0.2909. In respect of the radius 1000. If those measures are taken true, the true numbers of the table will all come out less. But the difference, even when greatest, and to the quadruple of the Earth's distance from the Sun, amounts only to 16h.55. The time of a comet's ingress into the sphere of the orbis magnus, or of its egress from the same, may be inferred nearly from its parallax, but with more expedition by the following. Table 2. The apparent elongation of a comet from the Sun. Its apparent diurnal motion in its own orbit. Its distance from the Earth in parts, whereof the radius of the orbis magnus contains 1000. 60 degrees. 65. 70. 72. 74. 76. 78. 80. 82. 84. 86. 88. 90. Direct. 2 degrees 18 minutes. 2 degrees 33 minutes. 2 degrees 55 minutes. 3 degrees 7 minutes. 3 degrees 23 minutes. 3 degrees 43 minutes. 4 degrees 10 minutes. 4 degrees 57 minutes. 5 degrees 45 minutes. 7 degrees 18 minutes. 10 degrees 27 minutes. 18 degrees 37 minutes. Infinite. Retrog. 0 degrees 20 minutes. 0 degrees 35 minutes. 0 degrees 57 minutes. 1 degree 9 minutes. 1 degree 25 minutes. 1 degree 45 minutes. 2 degrees 12 minutes. 2 degrees 49 minutes. 3 degrees 47 minutes. 5 degrees 20 minutes. 8 degrees 19 minutes. 16 degrees 39 minutes. Infinite. 1000. 845. 684. 618. 651. 484. 416. 347. 278. 209. 140. 70. 00. The ingress of a comet into the sphere of the orbis magnus, or its egress from the same, happens at the time of its elongation from the Sun, expressed in col. 1, against its diurnal motion. So in the comet of 1681. January 4, os the apparent diurnal motion in its orbit was about 3 degrees 5 minutes, and the corresponding elongation 71 2/3 degree, and the comet had acquired this elongation from the Sun Jan. 4, about 6 in the evening. Again, in the year 1680, November 11th, the diurnal motion of the comet that then appeared was about 4 2/3 degree, and the corresponding elongation 79 2/3 happened November 10th, a little before midnight. Now at the times named these comets had arrived at an equal distance from the Sun with the Earth, and the Earth was then almost in its perihelion. But the first table is fitted to the Earth's mean distance from the Sun assumed of 1,000 parts. And this distance is greater by such an excess of space as the Earth might describe by its annual motion in 1 day's time, or the comet by its motion in 16 hours. To reduce the comet to this mean distance of 1,000 parts, we add those 16 hours to the former time, and subduct them from the latter, and thus the former becomes January 4d. 10h, afternoon, the latter November 10th, about 6 in the morning. But from the tenor and progress of the diurnal motions it appears that both comets were in conjunction with the Sun between December 7th and December 8th, and from thence to January 4d.10h. Afternoon on one side, and to November 10d.6h. Of the morning on the other, there are about 28 days. And so many days, by Table 1, the motions in parabolic trajectories do require. But though we have hitherto considered those comets as two, yet, from the coincidence of their perihelions and agreement of their velocities, it is probable that in effect they were but one and the same. And if so, the orbit of this comet must have either been a parabola, or at least a conic section very little differing from a parabola, and at its vertex almost in contact with the surface of the Sun. 4. By tab. 2. The distance of the comet from the Earth, November 10th, was about 360 parts, and January 4th, about 630. From which distances, together with its longitudes and latitudes, we infer the distance of the places in which the comet was at those times to have been about 280, the half of which, viz. 140, is an ordinate to the comet's orbit, cutting off a portion of its axis nearly equal to the radius of the orbis magnus, that is, to 1,000 parts. And, therefore, dividing the square of the ordinate 140 by 1,000, the segment of the axis, we find the latus rectum 19, 16, or in a round number 20, the fourth part whereof, 5, is the distance of the vertex of the orbit from the Sun's center. But the time corresponding to the distance of 5 parts in tab 1 is 27d.16h.7 foot. In which time, if the comet moved in a parabolic orbit, it would have been carried from its perihelion to the surface of the sphere of the orbis magnus described with the radius 1000, and would have spent the double of that time, viz., 55d.814 h. In the whole course of its motion within that sphere, and so in fact it did, for from November 10d. 6h of the morning, the time of the comet's ingress into the sphere of the orbis magnus, to January 4d. 10h. Afternoon, the time of its egress from the same, there are 55d. 16h, the small difference of 7 3/4 h. In this rude way of computing is to be neglected, and perhaps may arise from the comet's motion being some small matter slower, as it must have been if the true orbit in which it was carried was an ellipsis. The middle time between its ingress and egress was December 8d.2h. Of the morning, and therefore at this time the comet ought to have been in its perihelion. And accordingly that very day, just before sunrising, Dr. Halley, as we said, saw the tail short and broad, but very bright, rising perpendicularly from the horizon. From the position of the tail it is certain that the comet had then crossed over the ecliptic, and got into north latitude, and therefore had passed by its perihelion, which lay on the other side of the ecliptic, though it had not yet come into conjunction with the Sun. And the comet, see more of this famous comet, page 475 to 486, being at this time between its perihelion and its conjunction with the Sun, must have been in its perihelion a few hours before. For in so near a distance from the Sun it must have been carried with great velocity, and have apparently described almost half a degree every hour. By like computations I find that the comet of 1618 entered the sphere of the Orbis Magnus December 7, towards sunsetting, but its conjunction with the Sun was November 9, or 10, about 28 days intervening, as in the preceding comet. For from the size of the tail of this, in which it was equal to the preceding, it is probable that this comet likewise did come almost into a contact with the Sun. For comets were seen that year of which this was the last. The second, which made its first appearance October 31, in the neighborhood of the rising sun, and was soon after hid under the sun's rays, I suspect to have been the same with the fourth, which emerged out of the sun's rays about November 9. To these we may add the comet of 1607, which entered the sphere of the Orbis Magnus September 14, OS and arrived at its perihelion distance from the Sun about October 19, 35 days intervening. Its perihelion distance subtended an apparent angle at the Earth of about 23 degrees, and was therefore of 390 parts. And to this number of parts about 34 days correspond in Tab 1. Farther, the comet of 1665 entered the sphere of the Orbis Magnus about March 17, and came to its perihelion about April 16, 30 days intervening. Its perihelion distance subtended an angle at the Earth of about 7 degrees, and therefore was of 122 parts, and corresponding to this number of parts, in Tab 1, we find 30 days. Again, the comet of 1682 entered the sphere of the Orbis Magnus about August 11, and arrived at its perihelion about September 16, being then distant from the Sun by about 350 parts, to which, in Tab I, belong 33½ days. Lastly, that memorable comet of Regiomontanus, which in 1472 was carried through the circumpolar parts of our northern hemisphere with such rapidity as to describe 40 degrees in one day, entered the sphere of the Orbis Magnus January 21. About the time that it was passing by the pole, and, hastening from thence towards the Sun, was hid under the Sun's rays about the end of February. Whence it is probable that 30 days, or a few more, were spent between its ingress into the sphere of the Orbis Magnus and its perihelion. Nor did this comet truly move with more velocity than other comets, but owed the greatness of its apparent velocity to its passing by the Earth at a near distance. It appears, then, that the velocity of comets, p. 471, so far as it can be determined by these rude ways of computing, is that very velocity with which parabolas, or ellipses near to parabolas, ought to be described. And therefore the distance between a comet and the Sun being given, the velocity of the comet is nearly given. And hence arises this problem. Problem. The relation betwixt the velocity of a comet and its distance from the Sun's center being given, the comet's trajectory is required. If this problem was resolved, we should thence have a method of determining the trajectories of comets to the greatest accuracy. For if that relation be twice assumed, and from thence the trajectory be twice computed, and the error of each trajectory be found from observations, the assumption may be corrected by the rule of false. And a third trajectory may thence be found that will exactly agree with the observations. And by determining the trajectories of comets after this method, we may come, at last, to a more exact knowledge of the parts through which those bodies travel, of the velocities with which they are carried, what sort of trajectories they describe, and what are the true magnitudes and forms of their tails according to the various distances of their heads from the Sun. Whether, after certain intervals of time, the same comets do return again, and in what periods they complete their several revolutions. But the problem may be resolved by determining, first, the hourly motion of a comet to a given time from 3 or more observations, and then deriving the trajectory from this motion. And thus the invention of the trajectory, depending on one observation, and its hourly motion at the time of this observation, will either confirm or disprove itself. For the conclusion that is drawn from the motion only of an hour or two and a false hypothesis, will never agree with the motions of the comets from beginning to end. The method of the whole computation is this. Lemma I. To cut two right lines or, TP, given in position, by a third right lint RP, so as TRP may be a right angle. And, if another right line SP is drawn to any given point S, the solid contained under this line SP, and the square of the right line or terminated at a given point O, may be of a given magnitude. It is done by linear description thus. Let the given magnitude of the solid be m superscript 2n, from any point R of the right line or erect the perpendicular. RP meeting TP in P. Then through the point SP draw the line SQ equal to. In like manner draw 3 or more right lines S2Q, S3Q, and K. An irregular line Q2 Q3Q, drawn through all the points Q2 Q3Q, and K, will cut the right line TP in the point P, from which the perpendicular PR is to be let fall. QEF. By trigonometry thus. Assuming the right line TP as found by the preceding method, the perpendiculars TR, SB, in the triangles TPR, TPS, will be thence given, and the side SP in the triangle SBP, as well as the error. Let this error, suppose D, be to a new error, suppose E, as the error 2P2Q plus or minus 3P3Q to the error 2P3P, or as the error 2P2Q plus or minus D to the error 2PP, and this new error added to or subducted from the length TP, will give the correct length TP plus or minus E. The inspection of the figure will shew whether we are to add to or subtract, and if at any time there should be used for a farther correction, the operation may be repeated. By arithmetic thus. Let us suppose the thing done, and let TP plus E be the correct length of the right line TP as found out by delineation, and thence the correct lengths of the lines or BP and SP will be or E BP plus E, and whence, by the method of converging series, we have, and K. For the given coefficients, putting F, and carefully observing the signs, we find, and whence, neglecting the very small term, E comes out equal to, G. If the error is not despicable, take. And it is to be observed that here a general method is hinted at for solving the more intricate sort of problems, as well by trigonometry as by arithmetic. Without those perplexed computations and resolutions of affected equations which hitherto have been in use. Lemma 2. To cut 3 right lines given in position, by a 4th right line that shall pass through a point assigned in any of the 3, and so as its intercepted parts shall be in a given ratio one to the other. Let AB, AC, BC, be the right lines given in position, and suppose D to be the given point in the line AC, parallel to AB draw DG meeting BC. In G, and, taking GF to BG in the given ratio, draw FDE, and FD will be to DE as FG to BG. QEF. By trigonometry thus. In the triangle CGD all the angles and the side CD are given, and from thence its remaining sides are found, and from the given ratios the lines GF and B are also given. Lemma 3. To find and represent by a linear description the hourly motion of a comet to any given time. From observations of the best credit, let 3 longitudes of the comet be given, and, supposing ATR, RTB, to be their differences, let the hourly motion be required to the time of the middle observation TR. By Lem 2, draw the right line ARB, so as its intercepted parts AR, RB, may be as the times between the observations. And if we suppose a body in the whole time to describe the whole line AB with an equal motion, and to be in the mean time viewed from the place T, the apparent motion of that body about the point R will be nearly the same with that of the comet at the time of the observation TR. The same more accurately. Let Ta, TB, be 2 longitudes given at a greater distance on one side and on the other, and by Lem 2 draw the right line ARB so as its intercepted parts AR, RB may be as the times between the observations ATR, RTB. Suppose this to cut the lines TA, TB, in D and E. And because the error of the inclination TRA increases nearly in the duplicate ratio of the time between the observations, draw FRG, so as either the angle DRF may be to the angle ARF, or the line DF to the line AF. In the duplicate ratio of the whole time between the observations ATB to the whole time between the observations ATB, and use the line thus found FG in place of the line AB found above. It will be convenient that the angles ATR, RTB, ATA, BTB, be no less than of 10 or 15 degrees, the times corresponding no greater than of 8 or 12 days, and the longitudes taken when the comet moves with the greatest velocity. For thus the errors of the observations will bear a less proportion to the differences of the longitudes. Lemma 4. To find the longitudes of a comet to any given times. It is done by taking in the line FG the distances RR, RO, proportional to the times, and drawing the lines TR, TRO. The way of working by trigonometry is manifest. Lemma V. To find the latitudes. On TF, TR, TG, as radiuses, at right angles erect FF, RP, GG, tangents of the observed latitudes, and parallel to FG draw PH. The perpendiculars RP, ρ, meeting PH, will be the tangents of the sought latitudes to TR and TRO as radiuses. Problem I. From the assumed ratio of the velocity to determine the trajectory of a comet. Let S represent the Sun, T, tau, 3 places of the Earth in its orbit at equal distances. P, as many corresponding places of the comet in its trajectory, so as the distances interposed betwixt place and place may answer to the motion of 1 hour. PR, ρ, perpendiculars let fall on the plane of the ecliptic, and RRP the vestige of the trajectory in this plane. Join SP, S, SR, ST, TR, tau ρ, TP, and let TR, tau ρ, meet in O, TR will nearly converge to the same point O, or the error will be inconsiderable. By the premised lemmas the angles ρ, are given, as well as the ratios PR to TR, PR to TR, and ρ to tau ρ. The figure 2 is likewise given both in magnitude and position, together with the distance st, and the angles str, ptr, stp. Let us assume the velocity of the comet in the place P to be to the velocity of a planet revolved about the Sun in a circle, at the same distance sp, as v to 1. And we shall have a line pp to be determined, of this condition, that the space p, described by the comet in 2 hours, may be to the space vt tau, that is, to the space which the Earth describes in the same time multiplied by the number v, in the subduplicate ratio of st, the distance of the Earth from the Sun, to sp, the distance of the comet from the Sun. And that the space pp, described by the comet in the first hour, may be to the space p, described by the comet in the second hour, as the velocity in p to the velocity in p. That is, in the subduplicate ratio of the distance sp to the distance sp, or in the ratio of 2 sp to sp plus sp, for in this whole work I neglect small fractions that can produce no sensible error. In the first place, then, as mathematicians, in the resolution of affected equations, are wont, for the first essay, to assume the root by conjecture, so, in this analytical operation, I judge of the sought distance tr as I best can by conjecture. Then, by Lem. 2, I draw rρ, first supposing rr equal to rρ, and again, after the ratio of sp to sp is discovered, so as rr may be to rρ as 2 sp to sp plus sp, and I find the ratios of the lines p, rρ, and or, one to the other. Let m be to vt tau as or to p, and because the square op is to the square of vt tau as st to sp, we shall have, x equal, or superscript 2 to m superscript 2 as st to sp, and therefore the solid or superscript 2 sp equal to the given solid m superscript 2 st. Whence, supposing the triangles STP, PTR, to be now placed in the same plane, TR, TP, SP, PR, will be given, by Lem. I. All this I do, first by delineation in a rude and hasty way, then by a new delineation with greater care. And, lastly, by an arithmetical computation. Then I proceed to determine the position of the lines rρ, p, with the greatest accuracy, together with the nodes and inclination of the plane sp to the plane of the ecliptic. And in that plane sp I describe the trajectory in which a body let go from the place p in the direction of the given right line p would be carried with a velocity that is to the velocity of the Earth as p to vt tau. QEF. Problem 2. To correct the assumed ratio of the velocity and the trajectory thence found. Take an observation of the comet about the end of its appearance, or any other observation at a very great distance from the observations used before, and find the intersection of a right line drawn to the comet. In that observation with the plane SP, as well as the comet's place in its trajectory to the time of the observation. If that intersection happens in this place, it is a proof that the trajectory was rightly determined. If otherwise, a new number v is to be assumed, and a new trajectory to be found. And then the place of the comet in this trajectory to the time of that probatory observation, and the intersection of a right line drawn to the comet with the plane of the trajectory, are to be determined as before. And by comparing the variation of the error with the variation of the other quantities, we may conclude, by the rule of 3, how far those other quantities ought to be varied or corrected, so as the error may become as small as possible. And by means of these corrections we may have the trajectory exactly, providing the observations upon which the computation was founded were exact, and that we did not err much in the assumption of the quantity v. For if we did, the operation is to be repeated till the trajectory is exactly enough determined. QEF. End of the system of the world.